Hello, everyone. Good morning, good afternoon, wherever you are in the world. I hope you're keeping safe and healthy. Thank you so much for joining us today for the annual fall conference of the Stanford Institute of Human-Centered AI, or HI. The title of our conference today is Triangulating Intelligence, Melding Neuroscience, Psychology, and AI. Personally, intelligence that reflects the diversity of human perception, cognition, and experience is a topic very near and dear to my heart. The intersection of neuroscience and computer science is something that I've worked on since graduate school, and I've devoted much of my professional life to it. So it is very central to the work we do here, also at HAI, the research that aims to develop novel technologies inspired by the depth and versatility of human intelligence. This includes AI inspired by neuroscience, cognitive science, and psychology, novel, unsupervised, semi-supervised, self-supervised, or supervised methods for diverse data types, knowledge, and semantics. The big bet in developing AI is seeking a new synthesis, a meeting of the minds between cognitive science, neuroscience, and AI, which is what we're going to discuss today. This conference exemplifies some of the most cutting edge research happening in this area of research worldwide. We hope to inspire new developments in this area. And thank you so much for being with us, and please enjoy your day. With that, I'd like to turn it over to the co-organizers of this conference, Professors Chris Manning and Surya Ganguly.
Good morning, everyone. Thank you for joining us today. We had nearly 7,000 RSVPs for this event, and we're really excited to have you all here, or at least all of you who have woken up so far, and to have so many of you interested in a deeper dive into human and machine intelligence. I'm Christopher Manning, an Associate Director here at the Stanford Institute for Human-Centered Artificial Intelligence. I'm also a Professor of Linguistics and Computer Science at Stanford University, and I'm the Director of the Stanford Artificial Intelligence Laboratory. This is an event that brings together multiple groups at Stanford, and we'd like to thank our co-sponsors for this event, the Stanford Wu Tsai Neuroscience Institute, the Stanford Department of Psychology, and the Stanford Symbolic Systems Program. Let me now introduce my co-organizer, Surya Ganguly, Associate Professor of Applied Physics, Neurobiology, Electrical Engineering, and Computer Science here at Stanford. Hello, Surya.
Hey, thanks, Chris. Welcome, everyone. So, of course, we had originally hoped to hold this conference in person last spring, but a few things happened along the way. But this is the third large virtual conference that we've hosted this year, so we're hopefully starting to get the hang of it. And we're pleased that all our keynote speakers have joined us today, and we have a great lineup for you.
Before we begin, a couple of quick logistical items. Please do bear with us if there are any technical glitches during our time together. Unless speakers finish their talks early, you will hear time checks for speakers. And if they go on too long, we may have to cut them off so that we stay on time. If by any chance networking goes down for us or you, please do go to hai.stanford.edu and look for alternative ways to view the conference. Today we have two sessions, the first one with 3 speakers and the second one with 4 speakers. And we'll have an extended discussion section live with Q&A following each session. And then we'll wrap up the day by hearing a bit more about the broader Stanford context for AI, cognitive science, and neuroscience in a final discussion at the end of today's event. We want you to be involved in the discussion. Please go to the conference page on our website. Just go to hai.stanford.edu and click the link for the conference. And there you can type in your questions. We'll try to get to as many of your questions as possible during the discussion periods. For this event, we're also going to use the Twitter hashtag #NeuroHI, NEUROHAI, all one sequence of letters. If you tweet about talks, we encourage you to use this hashtag so that the Stanford HAI team notice. We'll aim to take brief breaks between the 3 sessions today and try our best to stay on schedule. Human-centered artificial intelligence is about the connection between people and intelligent machines. There are many different aspects of that, including shaping the impacts of AI on society in a positive direction. But today we're going to focus in on the opportunities for synergy between understanding human and machine learning and intelligence. Before we hear from our presenters today, I'd like to let Surya tell us a little bit more about our vision here.
Okay, let's see. Thanks, Chris. Okay, hopefully you can see my slides. So yeah, I just wanted to set up the intellectual themes of this conference. So it's useful to start at the very beginning. Like, how did we all get here today, right? So our story kind of, at least the story of our brain, started kind of 500 million years ago when the first vertebrate brains appeared on this planet. And then about 2 million years ago, the first glimmers of human-like intelligence appeared on our planet. And modern humans in their sort of final evolved form appeared about 100,000 years ago. And this is a really remarkable achievement, right? Because, you know, currently we have 0 engineering design principles that can explain how a complex communication, control, sensing, memory, and power distribution network like our brains could continuously scale in size and performance over 500 million years without skipping a beat, without ever losing function. We are so far from understanding the theoretical principles governing this amazing feat. So we really have a lot to learn from evolution, even despite the incredible success that machine learning has had in industry as of today. Right, so just to set the stage, let's zoom in an order of magnitude discrepancies between what machines and humans can do, right? So, oops, sorry. Sorry, hold on 1 second. I need to share my desktop, I think. Sorry, okay. Sorry, this worked right when I was testing it, so let me try something different. Okay, there we go. So, so one major discrepancy is, of course, the robustness of humans versus machines. We all know about adversarial examples where artificial networks in vision, speech, language, and reinforcement learning can be fooled by illusions that simply don't fool humans. So why do these exist? How does our brain avoid them? How do we make AI more robust? Another order of magnitude discrepancy is energy expenditure, which is becoming very important in industry, right? Modern supercomputers spend about megawatts, 10 megawatts of energy, whereas the human brain spends 20 watts of energy. So our supercomputers consume 10 million times more power than our brain, but cannot do what we can do. A likely problem is that supercomputers are extremely fast and precisely control the flips of digital bits, but the laws of thermodynamics exact a powerful energy cost for every precise and fast bit flip. In contrast, biology is slow and noisy, but just good enough. And so there's, I think, powerful principles that we can glean from biology to create more energy efficient AI. Credit assignment is a major open problem. So just to state it dramatically, here's one of my favorite tennis players from my youth, Ivan Lendl. Let's say, for example, you hit a tennis ball incorrectly. You have 100 trillion synapses. Which one screwed up? How does the brain figure out how to fix the wrong synapses? How does it rewire itself? Neither theoretical neuroscience nor AI can solve this problem adequately at the moment. So, you know, a major open question is, can synaptic physiologists, theoretical neuroscientists, and AI engineers work together to solve this foundational problem? Data hungriness is a major issue. If you look at recent successes in industry, sort of early, and you translate the amount of data that these systems used into human terms, early speech recognition systems use the equivalent of 16 years of someone reading you text 2 hours a day for every day. AlphaGo practiced 450 games a day every day for 30 years. And visual answering question sets are equivalent to receiving answers to about 100 questions about images every day for 274 years. Right? So it's clear that humans use much less data to achieve what they do. And so we need better algorithms for learning from unlabeled data, extrapolating information from other tasks to solve a new task. And of course, humans have set up a system of culture and curriculum design to teach humans using carefully sequenced tasks. And we need better ways of doing that in artificial systems as well. Babies also learn very, very differently from humans. There's a famous experiment where if a baby is given, say, two objects, one that in a video magically, when you drop it, it doesn't fall, and another object on a video where magically, if you move it through a solid surface, it can move through that surface. Then you let the baby play with those two objects. The object that didn't fall, it will specifically throw it off the edge of the crib to see if it really doesn't fall. The object that went through solid surfaces, it'll specifically bang it against the crib, right? So this is remarkable. This is saying that even babies, they build complex internal models of how our world evolves. They pay attention to events that violate their world model. They perform active experiments to test their model and gather their own data. They don't just passively receive data. They use the world model to plan and imagine alternate futures. And as they grow up, they can take actions to bring about these alternate futures into being, into reality, right? We're so far from doing that in artificial systems, though you'll see some examples in our talks today, okay? So an oft-quoted trope in arguing for why we should ignore biology in creating artificial machines is the analogy, for example, between birds and planes. Now that we have jet planes, it seems almost like folly to build airplanes designed upon the operating principles of birds. But if you unpack this analogy a little bit, you realize that there's multiple problems that need to be solved in making objects fly. Two primary problems are lift and thrust, keeping something up and moving something forward. Of course, airplanes and birds solve the problem of thrust in very, very different ways. Jet engines for airplanes and wings for birds. But the problem of lift is solved in exactly the same way, an aerodynamic wing that creates low pressure on the top and high pressure on the bottom. In fact, our artificial gliders behave very much like gliding birds. So just as there exist laws of aerodynamics that govern all flying objects, whether biological and artificial, and woe unto the object that tries to violate the laws of aerodynamics because it will fall out of the sky, what we'd really like to pursue is an understanding of the fundamental laws and principles that govern how high-level cognition and behavior can emerge from nonlinear distributed dynamical circuits, whether biological or artificial. Of course, AI systems may do some things differently from humans to achieve their end objectives, but there are likely common laws that govern intelligent systems, just as there are common laws that guide flying objects. All right. So if you're interested in more info and thoughts, I actually wrote a blog post titled The Intertwined Quest for Understanding Biological Intelligence and Creating Artificial Intelligence, which you can find on our blog. And there's much more detailed understanding of some of the things that I talked about here. Just to give you an overview of the topics we'll discuss today. So in our morning session, we have an amazing speaker lineup. So in our morning session, we'll start with Matthew Botvinick from DeepMind, who will talk about really melding AI, psychology, and neuroscience. We'll have Dan Yamins talking about alternate methods for learning, especially self-supervised learning from unlabeled data, which was one of the ideas that I mentioned, for visual representations and also other representations. And Dan works both in psychology and in AI. Chelsea Finn has done beautiful work in robotics and meta learning, and she'll tell us how not to create a robot's mind. Knowing not what to do is a very powerful way to zoom in on what to actually do. And then after that, we'll have a panel discussion. Chris and I will have a panel discussion with the speakers. And by the way, we're relying on you for your participation. This is a QR code, which if you scan, you'll be able to go directly to our website, which is right here. And you can write in your own questions. You can vote up or down questions throughout the entire morning and afternoon, and we will see all of your questions, and we'll ask as many of the interesting questions as we can. Okay, in our afternoon session, we'll have a theorist, Sanjeev Arora, talk to us about how we can use deep learning to implement a very serious human value, which is privacy. Yejin Choi, who's done beautiful work on natural language processing and common sense reasoning, we'll talk about common sense intelligence, cracking the longstanding challenge in AI. Ade Oliva will talk about incorporating lessons from cognitive science into AI. And Josh Tenenbaum will talk about some of the scaling issues in terms of how much data we need by looking at alternate algorithms like probabilistic programs, and talk about models or game engines in our brain that might govern the way we think about physics and reasoning. And then we'll have another panel discussion with these speakers where, again, we'll take your questions that we'll accumulate and vote upon, that you guys will vote upon throughout the day. And then we'll end with an overall panel discussion. We'll have two very important visitors, Bill Newsom, from our co-sponsors, Bill Newsom, who's the director of the Wu Tsai Neurosciences Institute at Stanford and also a member of the Department of Neurobiology, and Michael Frank, who's a director of the Symbolic Systems Program and also the Department of Psychology. And Chris and I will join them in sort of an overview of a future-looking view of how neuroscience and psychology and AI can work together, and just general thoughts about the day. This should be a lot of fun. Okay, so that's my last slide. So without further ado, I will introduce Matthew Botvinick, who is coming to us from DeepMind, and he will give us our first talk. Thanks.
Great. Hopefully you can hear me. Can you hear me? I can't hear anybody confirming.
I can hear you.
Yeah.
Okay, good. And you can see my slides now?
Yep.
Fantastic. Okay, well then I'll just dive right in. Thanks so much for the opportunity to participate today, and I'm honored to be kicking things off. I wish I could have been there in person with everybody on the farm. That's my alma mater, but I'll take what I can get. And I'm going to give a presentation today that I hope will set the table for a lot of subsequent talks, because I'm just going to speak very broadly about my perspective on AI, psychology, and neuroscience, this triangle that the meeting's about. Like Feifei, this triangle has been sort of definitive of my intellectual life ever since I was at Stanford, and I feel like I've spent most of my life now kind of swimming around in this triangle from corner to corner and thinking about how they might all interrelate. I started doing that in academia at Penn and then at Princeton, but over the last 4 years, I've been working, I have one foot in academia at University College London, but I spend most of my time at an AI company called DeepMind, which is in London. I haven't actually physically been to London since the COVID thing began, but I'm looking forward to going back there someday and stopping the telecommute that we're all doing. So for those of you who don't know DeepMind, it's an AI company that's involved in a rather diverse set of research activities, but it's perhaps best known for something called deep reinforcement learning, which is a combination of deep learning or artificial neural networks on the one hand and reinforcement learning or reward-driven learning on the other. The first high-profile product of this line of research was in a paper that DeepMind published in Nature in 2015, where they showed how deep reinforcement learning could be used to learn how to play classic Atari games at superhuman levels. And the basic idea is pretty simple. You just take a multi-layer neural network and give it a screenshot, ask it to output an action that one could execute on a joystick, and then you train the whole thing using reward signals, which are based on the points in the game. And this basic approach has been elaborated, quite dramatically and in many ways since then, both at DeepMind and beyond. Some of you may know DeepMind's recent work applying deep reinforcement learning to the much more complicated video game of StarCraft, which was reported in Nature last year. And also work augmenting the deep reinforcement learning formula that I've briefly described already with model-based tree search to attain superhuman performance on complex board games like Go and chess. Further work augmenting deep reinforcement learning with particular kinds of memory systems so that they can engage in structured inference, as in this differentiable neural computer work that was reported in Nature in 2016. And then quite recently, extending deep reinforcement learning to the multi-agent setting in work that we reported last year. This is deep reinforcement learning agents learning to collaborate and compete in visually enriched environments in the game of Capture the Flag. So that's just a taste of the kind of AI research that goes on at DeepMind. And DeepMind is an AI company. The group that I lead, the members of which are shown here, is nicknamed the Neuroscience Team. And we're the one place at DeepMind where neuroscience and cognitive science, psychology research is going on as part of the mix. And we have most of the people involved in the team are doing kind of mainstream AI research most of the time, but there's a little bit of a difference of culture in the sense that most of the people on our team come originally from a background in neuroscience or cognitive science, and a lot of what we do is sort of informed by that background. We've written a few things just generally laying out a perspective on how one might bring these fields together, especially in order to support AI. When I first arrived at DeepMind, I teamed up with the CEO, Demis Hassabis, and a couple of other amazing colleagues to write a position paper for Neuron about neuroscience-inspired AI. And then much more recently, we wrote a review looking at how this paradigm of deep reinforcement learning can be used as a kind of basis for translating phenomena between neuroscience and AI in general. What I want to do is say a few words about the kind of working philosophy that we've arrived at in my group, and give you a quick whirlwind tour of some of the work that approach has led to. So it's been about 4 years of experimenting and thinking about the right way to pursue this virtuous circle among neuroscience, psychology, and AI. And I guess the way that I would summarize the approach we've landed on is that it's fairly opportunistic. It's based on an ongoing dialogue between neuroscience and psychology on the one hand, and AI on the other, without really worrying too much from moment to moment which field you're standing in. Importantly, we try to set things up so that there are a lot of bilingual people working on our neuroscience projects and on our AI projects, so that it's not the transfer of insights is not between people in every case, but sometimes it's happening within one brain. I think that's important. One thing that I want to emphasize is that I believe that the transfer of insights between fields is often subconscious. We tend to focus on a schema of an insight, a concrete insight from one field being transposed to another field. But I think what often happens is that instead, a familiarity with neuroscience will kind of give analogical support for a new idea in AI or vice versa. And sometimes it's even hard to track the origins of these connections. And finally, and this is really the point I want to start with in delving into some specifics, the kind of synergy that we're after between these fields is really just a continuation of something that's been going on ever since AI originated as a field. So let me say something about that. So if you look carefully at the montage of people in my group, you'll have noticed that they're all quite young. And that, as far as I can tell, is true of the general population of people doing AI research these days. And what I've noticed is it means that people aren't always vividly aware of the history of the field in which they're working. So it turns out that a lot of people that I interact with at DeepMind, I get the impression that they think that AI research began in 2012. Which of course is when neural networks came roaring back with a victory on image classification tasks. And one thing I'd like everybody to have more awareness of is that in fact, this kind of explosion of work with deep learning since 2012 really is just the tip of a historical iceberg. And looking at that, like what's underneath the water there, the deeper history of deep learning research makes extremely vivid how the synergy among these fields can play out. So if you go back to the very earliest papers that describe computer implementations of neural networks, they're very explicitly motivated by ideas from neuroscience and observations from neuroscience. If you look at the earliest paper that describes a learning algorithm for artificial neural networks, same thing. It's basically a psychology or neuroscience paper. If you look at the first high-profile report of the epoch-making backpropagation algorithm, which we all use in deep learning research ubiquitously to this day, the first author is a psychologist. And the first explorations of the implications of backpropagation in neural networks were reported in these historically important books called the Parallel Distributed Processing volumes, which were written largely from a cognitive science and neuroscience point of view. And I just want to give a shout out to Jay McClelland, who was one of the key authors in these volumes and of course is a Stanford professor. One reason that I think a lot of young people believe that AI research and deep learning research began in 2012 is that there was in fact a quiet period in neural network research leading up to that. Neural network research used to be referred to as connectionist research, and there was something that some of us refer to as the connectionist winter, where it became very difficult to publish neural network research because other computational paradigms became much more popular. In fact, I have to laugh because this is from a meeting in 2013 where a famous connectionist researcher named Mark Seidenberg presented, and he entitled his talk, "I Remember Connectionism," sort of sardonically. But if you look at the issues that came to the fore, even during that connectionist winter, you see again that they were inspired not only by psychology, but in fact by the same neural network ideas that had been popular just years before. So if you go to Judea Pearl's pivotal book on structured Bayesian inference, which set the scene for a lot of Bayesian cognitive science that took center stage during that connectionist winter, not many people are aware that in fact Pearl's work was inspired by connectionist research by Rummel Hart and McClellan. And of course, in 2012, when neural networks did come roaring back, especially in engineering, neuroscience again played a pivotal background role. So if you look at convolutional neural networks, which were responsible for triggering this renaissance in deep learning, those of us who know the history are aware that in fact they were very directly based on earlier work by Fukushima and others, which proposed neural network architectures that were directly inspired by knowledge about visual cortex in the brain. The same kind of connections exist in deep reinforcement learning. So if you look at the reinforcement learning algorithms that are brought to bear in this work, and in particular temporal difference learning, which is one of the most important, the originators of that algorithm, Sutton and Bartow, started out thinking very specifically about animal learning. This was not a computer science project per se. They were trying to figure out how animals learn in the ways that they empirically do. And of course, temporal difference learning, as many of the people in the audience will know, has since been tracked back into neuroscience as an account of how the dopaminergic system works. One more point along those lines, one of the main things that allowed deep reinforcement learning to work, practically speaking, in the Satari project is something called experience replay, which is a replay of memories and further learning based on that replay that was directly inspired again by neuroscience based on observations about what happens in the hippocampal formation. Very recently, those who keep up on the AI literature will be very aware of something called a transformer model that's been applied in language modeling to great effect recently by multiple groups. And here again, even though these breakthroughs in language modeling are happening very much in a computer science or AI context, if you just go back a little bit, you'll see that the original approach to exactly the same problem was pioneered by a cognitive scientist, Jeff Ellman, who really started the work that's now bearing such amazing fruit in this recent research. So anyway, all of that is just my kind of cranky old man version of a historical perspective. And I like the people that I work with to know that we're just carrying on a tradition. But having given you that historical background, let's talk about what's going on now and the way and in the background of what I'm about to describe. I think you'll see this three-part strategy. Let me tell you about some of the work that we've been doing in my group at DeepMind. Again, kind of trawling these waters, these triangular waters among neuroscience, psychology, and AI. So this is going to be a bit of a whirlwind tour, and I apologize if it's superficial, but I'd rather everybody get a kind of bird's eye view of the range of things that we've been doing and the flavor of our approach rather than the details of any one project. So let's start with a paper that we published in Nature Neuroscience in 2018, which is closely connected with a review that we published last year in Trends in Cognitive Science, which is about something called meta-reinforcement learning. Here we started with an observation about recurrent neural networks. So a recurrent neural network is just a deep neural network that has connections among its internal units, which allows the system to have memory in its activations, very much like working memory in the brain. What we observed is that if you train a recurrent neural network of this kind using reinforcement learning, that's what the red arrow stands for, you use reward prediction errors to train the network's connection weights. And you train it to go from visual observations to actions in the standard reinforcement learning way, along with some auxiliary inputs and outputs that we can ignore for the moment. Something very interesting happens if, in addition, you train the system not just on one task, for example, a two-armed bandit problem, but instead a family of interrelated tasks. What happens in that context is that after the system has enough experience with that family of tasks, you can turn off the reinforcement learning algorithm. You can freeze the connection weights in this network. And then when you present the system with a new problem from the same family, it can solve it, even without synaptic changes. So this is just an illustration of a network with frozen weights solving a two-armed bandit task. You can see it exploring left and right actions in an easy problem and a hard problem. And this is just a regret curve showing that the system is doing pretty well on this bandit problem compared to off-the-shelf bandit algorithms that form a gold standard for comparison. So that meta reinforcement learning principle was purely an AI. It was purely an AI observation. But because the people that were involved in this research were bilingual in the way that I mentioned earlier, some of us got to thinking about potential analogies to brain function. And we thought, well, if we know that the dopamine system appears to act in a way that's analogous to this reinforcement learning algorithm we're applying, and we know that the prefrontal cortex has highly recurrent connectivity, lots of loops, then maybe we can think of this recurrent network that we're training as a model of the prefrontal system as it's trained up by reinforcement learning. Maybe the working memory functions of the prefrontal cortex are trained by the synaptic changes that are driven by dopamine. And that's what the paper's about. We show things, for example, like this. If you train a recurrent neural network on a task that has been used in studies with monkeys, you find behavior in the neural network that closely resembles the behavior of the monkeys. And then if you look inside the neural network at what the internal units are coding for, you find a profile of codes that closely resembles what you see in the neuroscience study when electrodes have been placed in prefrontal neurons and their receptive fields have been measured. That's just a quick taste of this work. I encourage you to look at the Nature Neuroscience paper if you're interested in more details. I'll just mention that we've carried forward this work. We have a paper on arXiv that characterizes this meta-learning process in Bayesian, in terms of amortized Bayesian inference. And we're continuing to partner with neuroscientist collaborators in order to show that meta-RL actually provides a better explanation for prefrontal function than some standard reinforcement learning models. That's work that we're preparing to submit soon. But for the moment, let me move on and tell you quickly about another project in which we've kind of trawled these waters between neuroscience and AI. And this is a paper that we published earlier this year in Nature, which is about distributional reinforcement learning and dopamine. So in the AI world, there's been a lot of interest in something called a distributional reinforcement learning algorithm. The idea here is, in reinforcement learning, an important component is making predictions about how much reward you can expect in the future, given where you are now. And the standard approach is to represent that future prediction as a single number. But the distributional approach says, well, what if instead we represent the future expectation in terms of a full probability distribution? So an agent playing an Atari game might say, well, I might make this many points and I might make that many points. Or a humanoid jumping over a chasm might think, oh, well, I might make it over and get a lot of reward, or I might fall in and get less reward. And that distribution evolves over time. What's been found in AI work is that this distributional approach has very dramatic payoffs for performance in reinforcement learning systems. And in the work that we did, we decided to ask again, drawing our kind of bilingualism here, gee, I wonder whether the dopamine system might use a similarly distributed code. Long story short, we found strong evidence in a study that we did in collaboration with Naochita's lab at Harvard that, in fact, you can find parallels. So we studied dopamine activity in a task where mice were given probabilistic juice rewards, and the rewards were drawn from a distribution that was multimodal, shown here in gray. And we were able, using just the activities of the dopamine neurons that were recorded from these animals, to decode or infer the full distribution of rewards that the animals were experiencing. This is something that you shouldn't be able to do. In modeling work, you shouldn't be able to do this if the dopamine system were operating in a classical fashion. But of course, if it's operating in a distributional fashion, then you should be able to decode this, this distribution of rewards. And that's one of the things that we found. Again, many more details in that Nature paper, but in the spirit of this whirlwind tour, let me move on to another example. This is work that actually we just put on arXiv. It hasn't been published yet. I think it'll connect closely with what I anticipate Dan Yamins will be talking about in his presentation. So I'm excited to kind of put it on the table here alongside the cool work that he'll describe. And this is work that was led by Irina Higgins at DeepMind in collaboration with Doris Tsao at Caltech. the basic idea here is to draw on an unsupervised learning architecture that's been of great interest in AI recently, called a beta variational autoencoder, or beta VAE. And the short story here is that this learning architecture uses an objective function that encourages an internal representation that discovers disentangled features. So if you train it on pictures of chairs, and a single internal unit in the system will end up coding for the type of the legs on the chair. And a different internal unit will code for the overall type of chair. And a different internal unit will code for the rotation of the chair. And these disentangled features depend very much on the nature of the data on which the system is trained. So if you train it on faces, it'll discover disentangled features for faces, for example, hair color and so forth. So again, in this kind of using our bilingualism, we decided to ask, gee, I wonder whether the visual system in actual brains might discover disentangled features of this kind. And since we have this AI model, we can do a direct comparison to the codes that are observed in visual neurons in a primate brain on the one hand, and individual units in a beta VAE on the other. Long story short, we find a close correspondence. So looking at neural activity in face patch in macaques, we find that the activity of individual neurons tracks very closely with individual units in a beta VAE trained on exactly the same visual data. And in fact, the one-to-one matching using a variety of ways of measuring this is much closer for the beta VAE for many other deep learning models, including both unsupervised or self-supervised and supervised varieties. Again, no time to go into the details, but hopefully some of you will check out the archive paper. So the work that I've described so far is very much about taking ideas from AI and dragging them into neuroscience. Let me talk very briefly about a couple of projects where we've gone the other direction and taken insights from psychology and neuroscience and tried to bring them into AI. And I'll be very brief and superficial here because I only have limited time. But again, the purpose is to give you an overall flavor. So one thing we have a pretty good idea of from psychology and neuroscience is that the visual system carves the world, the visual world, up into discrete objects. So very strong evidence for this was shown in classic work by Egli, Driver, and Rafal, using an attentional cueing paradigm. Many of the psychologists in the audience will be familiar with this classic work. In neuroscience, it's received convergent support from studies by Ralphsma and others in the primary visual cortex, showing that entire objects are selected by attention as wholes and in parallel. We have the opportunity to experiment with whether this might help in our AI systems now, because we have new unsupervised learning algorithms that can pick out discrete objects in visual data. For example, a system called Monet that's come out of our group at DeepMind, but now there are a variety of algorithms that can do this. And in the work I'll briefly describe, we take this ability to carve out discrete objects, and we combine it with another insight from cognitive psychology, which is that visual scenes are represented not only in terms of objects, but in terms of relations among those objects. And here we have the benefit of recent deep learning architectures that are relational in nature, like these transformer architectures that represent ordinarily words given their larger context. But what we can do is we can combine that relational representation and apply it. We can combine it with object identification and apply it not only to language data, but now to visual data as well, putting in objects instead of just words into those slots. So I'll briefly describe in 3 minutes 2 projects where we've used this strategy. One is a project led by Luis Pilato, which is about intuitive physics. Here we were inspired by developmental psychology, where an understanding of intuitive physics in young children is probed by looking at what surprises them, basically showing them magic tricks that violate the laws of physics and seeing whether they're surprised as a way of telling whether they understand what should have happened based on the ordinary laws of physics. And what we did was we created a data set that's very much like the violation of expectations videos that are, or events that are shown in these developmental studies. For example, showing ordinary physical events, illustrating something like directional inertia, and then also magic tricks for comparison. We wanted a system that would be more surprised by the magic tricks. Another phenomenon that we studied in this work is something called continuity, again, drawing on developmental psychology work. Here's an ordinary physical event in our data set. Here's the magic trick, which we want to be surprising. Object persistence, dropping a board on an object. And in the magic trick, the board goes all the way to the ground. Again, drawing on classic findings from developmental psychology. We trained our system on free-form physics data. So we didn't train it on these phenomena. We trained it on a much more general set of videos. And we use this strategy of carving the visual data up into objects using unsupervised learning, and then using a relational architecture in order to represent those objects in a context-dependent way. I won't go into the details of the architecture, but suffice it to say that that was the overall strategy. And what we find is that using this approach, we get very robust surprise effects across 5 phenomena or concepts that have been studied in the developmental literature. And that's what the bars in green here show the results from Lewis's architecture, which he nicknamed Plato. But importantly, a set of very closely matched baseline models that did not use an object-based representation showed much less clear surprise effects, suggesting again that an object-based representation, like the one we see in the brain, is useful for learning intuitive physics. Okay, 1 more minute, and I'll just briefly give you a sense of another study that we've just recently completed, which uses a similar approach to do visual question answering. This is based on a very cool data set just published by Josh Tenenbaum, Pushmeet Kali, one of my colleagues at DeepMind, and others. And the work on our side was done by David Ding and some other colleagues who are truly amazing. The data set involves videos and a variety of questions that the system has to learn to answer. Some of these are descriptive, some are explanatory, some are predictive, and some are counterfactual. What would have happened if? The work that originally reported this data set used a very elaborate architecture that has a Python module that executes programs that generate the data in order to do inference. And what they showed was that baseline models had a lot of difficulty with counterfactual questions and predictive questions, but their neurosymbolic system did a bit better. What we showed briefly in the work that I'm going to just wrap up describing right now is that when we use an object-based and relational deep learning model without a symbolic component beyond that, we actually do much better. So again, deep learning based on objects and relational representations as inspired by neuroscience and psychology does really well in these structured domains. Okay, one final word with going over 30 seconds with your indulgence. Hopefully I've given you a sense of the approach that we're taking trawling these waters. I just want to add one more point, which is that we're getting excited about not only exploring neuroscience and psychology, but also social science. So we've published a bunch of papers lately looking at multi-agent reinforcement learning, comparing it to what happens in human groups in things like sequential social dilemmas. And we're beginning to think that this is a very important area of study if we want to understand how AI systems are going to interact with humans when they're deployed in the real world. Obviously, something that's very central to the HAI paradigm at Stanford. So looking forward to talking about that maybe a bit more in the discussion. And that's it. Thank you.
Hey, all. Thanks so much, Matt. So we're going to take a couple of minutes break, and we're going to switch the video to YouTube because I think it will improve a lot of people's video quality. So just hold on a bit, and the live stream should be up again in a couple of minutes. All right. Thank you very much. Okay, welcome back, everyone. So sorry for the glitches that we had. So we've switched to YouTube. I just encourage you all, just to be safe, to refresh your browser. Without further ado, I would like to introduce our next speaker, Daniel Yamins. He's an assistant professor here at Stanford of computer science, and also he's a faculty scholar of the Woodside Neurosciences Institute. So Dan, please unmute yourself and share your presentation and take it away.
Hi, everybody. Thanks so much for having me. I'll also say that I'm a member of the psychology department at Stanford as well. So that's an important part of our triangle here, neuroscience, psychology, and AI. And in fact, in the Stanford Neuro AI Lab, which I direct, we work on sort of these two mutually reinforcing goals. One is the idea that understanding brains and human cognition will allow us to build better AI and machine learning techniques, and vice versa, that those techniques will in turn allow us to make better models of cognition in the brain. So in practice, what that means is we build neural networks to solve challenging cognitive problems and then use those models to make quantitative predictions about brain data. My talk will be in two parts. Part one, we'll talk about AI helping neuroscience, and part two, we'll talk about the other direction. So let's work on first on AI helping neuroscience. A core problem in cognition is the very simple problem, it seems, of visual understanding, basically being able to take input images in and understand what's in them. The brain areas that are thought to support this are part of what's called the ventral cortical pathway. So images come in on the retina, they get processed through a series of hierarchically arranged brain areas like V1, V2, V4, IT, and by virtue of doing that, support high-powered visual cognition by the time the data hits in inferior temporal cortex, or IT, at the top of this pathway. As a result, from a computational neuroscience point of view, a very natural idea is to build a quantitative model of neurons in that system. It's no news to anyone at this point that a natural way to do that is to use convolutional neural networks, which were actually originally built so as to condense the rough neuroanatomy of the ventral stream, both in terms of its being hierarchical and its being retinotopic. So of course, how do you actually produce a convnet that looks like the brain? Well, the natural strategy that we have found so particularly useful is to optimize the network for performance on a task, like say, 1000-way ImageNet categorization, and then compare it to the brain on a unit by unit basis. And it turns out that if you do this, neural responses in the brain, in this case, this is to a face neuron, a neuron that responds high to face images, that's the black line, is well predicted by the neurons in the top hidden layer of a neural network that is solving a categorization task. So this neuron is one among many, but if you actually look at among a lot of neurons, you see that these kind of task optimized convolutional neural networks are today's by far best models of neural responses in the visual system. And you know, when you take a model that's appropriately deep with about the right number of areas to actually match the progression of visual areas in the brain, that not only do you see that higher cortical areas are matched by higher layers of the model, where high level of abstractions are done, intermediate cortical areas are matched by intermediate layers of the model in this kind of amazing way that these layers in the middle that are hard to understand what they actually do. Nobody really knows what the features are in English, but nonetheless, these intermediate layers are matched by the functionally optimized models. And early cortical areas, which are thought to compute such things as edges, are matched by the earliest layers. So there's really this very strong correspondence between both sort of the neuroanatomical or virtual neuroanatomical structure and the features that come out of these deep neural networks. Now, of course, you might say the deep neural networks are kind of like black boxes, but I push back on that by saying that there's really some key principles in this kind of goal-driven modeling idea. One of them is that you start with an architecture class, you have a task or objective, there's a data set, and a learning rule. Our theory of the visual system, in some sense, at this point, is to say that the correct architecture class is the set of convnets, convolutional neural networks of reasonable depth. The task or objective is something like multi-way object categorization. The data set is something like ImageNet images, and the learning rule is some combination of evolutionary architecture search and filter learning through something like gradient descent. And those is a way of a machine learning way of saying it, but each of these ideas can also be given a neuroscience idea, with the idea of thinking of the architecture class as a kind of circuit neuroanatomy, the task or objective as a kind of ecological niche, the data set as something like the environment, and the learning rule is something like a combination of natural selection and synaptic plasticity, with this flow being that essentially you pick the right architecture class so that you can solve the ecological niche situated in the proper environment and update parameters that change the system according to the learning rule. So, this principle has been really useful at thinking about lots of things in terms of not just the visual system, but auditory system, and parts of the motor system. It's been very successful, actually, in a certain sense. But it actually has some very substantial problems, which drive a lot of the ways in which I think that future progress is happening. And many of these relate to what Surya and Matt have talked about. So on the one hand, there's something wrong in the architecture class, which is that everybody knows that the visual system has lots of recurrence and feedback. That's definitely not present in the feed-forward models that I've showed you. But why? What are those connections for? Maybe an even bigger problem is that too much labeled data is required in training object categorization like tasks. That's one Surya certainly mentioned. So the task or objective is somehow broken. Of course, these things are trained in data sets like ImageNet, not on the real noisy video data streams that real organisms have. And finally, backpropagation is well known to be non-biological in a variety of ways. So what I'm going to do is talk about solutions to some of these problems as part of the way that AI has been able to really, I think, help us get a better handle on neuroscience, going beyond just the basic equation of CNNs and the visual system. So as I mentioned a moment ago, real neural networks, that is to say, the ones in the brain, are full of feedback, both long-range recurrence and local recurrence. On the other hand, feed-forward structures can't produce non-trivial dynamics. Basically, they can just make square waves. But real IT population dynamics in the brain, in the part of the brain called IT, actually are useful. In other words, they are able to show that different images are solved at slightly different times. And the reason for this is that essentially hard images get solved late, whereas easy images or control images get solved earlier, right? So what this really suggests, all these things together suggest, is that we should convert from convnets to convolutional recurrent networks, not just feed-forward, but have some kind of recurrence. And that recurrence should be both short local, as in the green arrows, and long-range feedbacks from area to area, as in the red arrows. And if you do this, it turns out that if you build a sort of shallow feed-forward network with about the right number of areas as the brain, you do so well on ImageNet performance, that's fine. If you make the model a lot deeper, which is definitely not how we think the brain does it, you can improve performance a lot. With standard forms of recurrence, such as LSTMs, you can do okay at augmenting performance, although in this case, most of the performance is due to having additional parameters. But if you have the right types of local recurrent structures and the right types of long-range feedback, so reciprocal gated units and long-range feedbacks, you can actually very effectively convert space into time and make shallow recurrent networks that have about the same performance as substantially deeper feed-forward networks. So of course you can then ask, okay, do those local recurrences and long-range feedbacks, do they not only give you improved image performance, do they also give you better predictions of neural dynamics in the visual system? So I mentioned these sort of challenge images and easy images before. The challenge images are the ones that are hard to solve for computer vision systems, and they get solved later by the brain, about 20 or 30 milliseconds later by a macaque. The question is, how well do conv-RNNs do at making predictions about when the images are solved? It turns out on this plot of fraction of the hard images solved versus ability to predict IT neural dynamics, that convolutional recurrent networks are by far better there, even than the deepest feed-forward networks. Deep feed-forward networks can solve challenge images, but they have a hard time correctly predicting when those challenge images are going to get solved the way that the real brain does. And the convolutional recurrent networks do well at that. And in particular, the way they do well at that is that unlike shallow feed-forward networks, which don't do well in performance, or deep feed-forward networks, which do well in performance, but have a large number of units, convolutional recurrent networks are this really good sweet spot between having very high performance, but doing so with a very small number of units. So that is to say, they can actually fit in the head. The idea being that recurrence is being used to achieve this trade-off between performance and practically being able to be physically managed. So, results like this, among many others, say that we're perhaps not okay. We haven't quite nailed down this very deep problem, but I think we're getting towards okay-ish, which means that models are being harder to reject out of hand. Of course, that doesn't address these other problems, so I'll talk a little bit about that now. The second of these problems, which is really about the supervision problem, Surya mentioned, others mentioned, this is a very deep problem because there's really just no way that creatures like this receive millions of high-level semantic labels during training. Right, so some form of semi or self or unsupervised loss functions have to be produced that are realistically costly, but that actually, solve the task. Right, so like to put this more succinctly, imagine you had like head cam data from a child, right, like infants age say 6 to 32 months, such as data from the SACAM data set from Mike Frank's group here at Stanford and others. Data that's just like recording what they're hearing and seeing. How would you use a data set like this to learn a representation, right? That's a really challenging problem because there's no labels associated with that. There's a long history of unsupervised learning, autoencoders among them, which basically have the ability to take inputs in, produce those inputs out. And it turns out that if you build a shallow version of this with a sparseness penalty on the intermediate layer, you get things that look a bit like V1 area in the brain. But unfortunately, it's really hard to use autoencoding in general because you're constantly fighting sort of triviality. And in general, it's very difficult to produce deep networks that have wide range of good features for this for large numbers of categories of objects. There's other types of approaches to unsupervised learning, like things basically using the ability to project out information and then fill it back in. Like, for example, predicting context in images or learning features by inpainting, or one of my favorites is image colorization. You essentially take a grayscale image and color it. You knew what the colors were, so you could do that. And this forces representations to actually be pretty good, because to be able to say, get the right color, you have to know where the boundaries are, and you kind of have to know what the objects are to get the colors in the right place. But these methods have also been limited in terms of their ability to really predict, produce deeper networks and be able to take advantage of those structures to improve performance to anything like supervised levels. More recently, there's been some really serious progress in this in the last 2 years or so in the domain known as contrastive embeddings. Essentially, what these contrastive embeddings do is they have something like the ConvNet, but instead of training them to solve categorization problem, what they do is in various different ways try to train the networks to produce embeddings that push similar things closer together and not quite so similar things further apart. Various methods here have done quite well, producing unsupervised structures and embeddings that learn things that look like sort of proto-categories. And in fact, today's state-of-the-art unsupervised results on ImageNet produce transfer to ImageNet that are substantially better than, say, supervised AlexNet, which was one of the things that kicked off when it's supervised the deep learning revolution. But in fact, now with unsupervised methods, we can do substantially better than even the supervised AlexNet. So that's very powerful, and it works by not only increasing from these deep contrastive embeddings ability to do things like categorization, but also other tasks like object position or object size or things like that, where in fact you can actually see that because of their generality and non-task specificness, then when asked on transfer tasks to non-categorization tasks, unsupervised networks can do as well or better than the category supervised networks. So that's really powerful. Of course, it then raises the question of how well these match neural data, and you can use the same types of techniques I briefly mentioned earlier to compare to categorization-based networks. And there it turns out that if you do this, the older unsupervised techniques, which performed less well, do not so well at predicting neural response patterns, but these more recent deep contrastive embeddings do quite well here. And in fact, the best of these is better at predicting neural response patterns even than supervised categorization-based networks. So finally, really being able to build quantitatively accurate unsupervised models of a higher brain area. And this is true not just in, say, IT, but across the visual system. So predicting models of V1, V4, IT throughout the entire ventral hierarchy. Of course, you would like to operate these things not just on ImageNet. The things I just showed you were in ImageNet, not with the labels, but with the images of ImageNet, which is a strong data set. But really what you get is data that looks more like this, where objects are not framed, and really what you have is the real visual experience of children. And it turns out that if you build a video version of contrastive learning on the types of data that come from something like the SACAM data set, this head-mounted infant data set, that actually now we can start to really build networks that achieve almost the same ability as on framed data, like ImageNet, but with these completely naturalistic, noisy data streams. So that's really beginning to say that at this point, you know, not only are we able to make unsupervised models that predict neural responses, we can actually do so from the real data streams the organisms get. And by virtue of that, maybe begin to have a possible reasonable model for actual developmental trajectories. Of course, that's a big thing to ask off in the future. But what I would say here is that sort of taking together these second and third problems, the issue of not needing mega labels and being able to do so on real videos from real developmental data streams, that these big problems in thinking about the visual system have started to become basically okay-ish, if not exactly okay. So, you know, I think that means that AI has really been able to help us nail down some of the biggest problems in trying to build links between, stronger links between neuroscience and, you know, and computational techniques. I'm not going to talk about the learning rule. That's something, that's a discussion for another day entirely. But what I would say is to take away here is that there's been a lot of progress in terms of using better AI and ML techniques to understand brains in this much more realistic way. So I'm going to now shift gears and spend the rest of the time talking about the opposite direction. So thinking about how cognitive science can help us build better AI, and then maybe eventually better models of neuroscience. So the underlying idea here is very similar to what Matt was talking about, which is essentially you've got an agent in an environment. That agent can be a baby or it can be a machine, whatever. Of course, it takes in and does perception of information from the environment and it acts back out on it. In that context, one of the key things that you want to be able to do is understand how the agent can build a world model. That is to say, learn how, given if I take a given action or given what I see in front of me, even if I don't take an action, what's going to happen next? Okay. And of course, you might wonder why you should learn models, but I think that learning world models is something that obviously is useful from a whole variety of points of view, like having compact abstractions of high bandwidth sensory inputs or the ability to plan across long temporal horizons. This is just a very clearly useful thing to be able to do. In other words, in some way, what you'd like to be able to do is minimize a loss function where you're predicting the future given the current state. But of course, pixel prediction, that's a very natural thing to do, is very hard. I mean, there's been some progress made by folks like Chelsea, and I'm sure she'll tell you about some new stuff there. But it's challenging to do. So for example, you know, a very natural method, some of the most recent methods on this, if you have some trouble. So if you basically show them a scene of this where you've got a couple of objects, this blue low resolution objects in this simple room, acted on and you move your head, the ground truth of what you should see looks like this. You basically, one of the action objects goes out of the frame and the frame moves around. But what predictions will often look like is like this. So essentially quite good at some aspects of it, but losing some of the key things like the objects themselves, right? And so, you know, in work that we have started to do, we've started to really try to tackle how to think about this in a more naturalistic, cognitively reasonable way. So in particular, you know, principles coming out of cognitive science tell us that infants are very good at object permanence. In other words, they understand that if you see an object that's going to continue and it's going to be there even if it's behind something, that turns out to be really hard to train sort of standard convolutional 2D structures to do, even if they have some kind of memory in the form of RNNs. They have real trouble learning object permanence. 3D structures may be a little bit better, but they're very inefficient. And so an alternative that's maybe a little bit more cognitively salient is to build things in the form of graph-based priors. And so there's been a lot of work at using graph-based priors to represent objects. These are still kind of convolutional in nature, but now the convolutional is on the graph. And so as I say, these have been used to do some simple physical prediction problems like 2D bouncing balls. Of course, one would really like to be able to produce much more complicated things such as scenes of objects with complicated objects. And we've done work to try to push the you know, graph-based metaphor towards that. So in particular, scenes where you think about the nodes as corresponding to particles between the objects and edges corresponding to the relationships between them. Of course, humans don't think about all the particles at once in a scene. So what you really have is a hierarchicalization where nodes at higher levels represent kind of composites of things at lower levels. And that graph convolution is replaced with hierarchical graph convolution to allow you to mostly ignore low levels when doing the high level interaction computations. I won't get into the details of how to think about intuitive physics as a kind of graph computation, but what I will say is that if you build hierarchical relation networks, and train them to predict the future given the current state, they can learn very good representations of how physics actually works in a way that is comports with, you know, something about the way what humans can predict. So things like the ability to predict like a bouncing cone, or, you know, a complex rigid object interacting with the world, you know, or a rigid sphere rolling out of a bowl. This is a sort of complex interaction between objects, or, you know, a floppy teddy bear bouncing off the floor and recovering. Each of these is a comparison of a ground truth to the prediction of a kind of hierarchical relation network and thinking about things in the world, you know, knocking over an unstable block tower or folding cloth. The idea being here that basically for a whole variety of material types, interactions of various kinds can be represented, and you know, make good predictions about the future in a way that sort of naturally builds in object permanence, because after all, the nodes of the graph are the objects. Of course, while that's quite successful, it leaves the big old computer vision problem of how you actually extract a graph description of that kind from real world video, right? So that's an obviously big computer vision problem, and we've begun to do work on that with colleagues in trying to learn physical graph representations from visual scenes. So, of course, at the end of the day, what this means is taking images like the one on the left and being able to produce descriptions of what's going on there in some kind of graphical and 3D integrated way. So like a scene that will have a floor and the walls, as well as the cone and the ball. And that's what we do with things like the physical scene graph, or PSG net. So that not only should it be able to have a representation of the objects, but also of low-level things such as the 3D graph structure. And when you have this graph structure, what you can do with it is a lot. Like you can go back and segment the image, or you could produce a semantic description, or indeed predict intuitive physics, much like I was describing in the previous work. And to do this requires, you know, some substantial additions to the convolutional domain. So in particular, we start with the convolutional RNNs, like I mentioned a bit earlier, use the features from that to do graph construction, that is to build the graphical model of the world, and then learn it in a self-supervised way by rendering back those structures onto the world. I don't have time to talk about the details of the feature extraction, but as part of this graph construction process, there are a couple of key new kind of operations there, including a learnable graph pooling operation, which basically takes in convolutional recurrent features and figures out how to bind things together, and a learnable vectorization that summarizes the properties of objects so that over a wide range of points, they can become single nodes that are bound together. So one key fact about this type of PSG net structure is that not only can it work on kind of synthetic images, but actually allows us to produce very substantial improvements on real world photographic images in terms of self-supervised scene understanding. So that's the sort of key thing, is that it's not just limited to very synthetic domains. It can produce really powerful scene understanding on real world images, as well as being sort of compositional in nature. So, you know, given an input, you can do things like delete an object or move an object around or scale or rotate it by operating on the latents. Of course, in the long run, what we want to do is bring this back to, from an engineering point, back to making models in physics. And from a neuroscience point of view, what we would like to do is make comparisons back to parts of the brain that we currently do not. So in other words, in the long run, build a sort of integrated dorso-ventral model beyond just the ventral stream that I've talked about. I'll just wrap up on the last bit by talking briefly about the idea that in addition to wanting to build a system that solves the world model, what we really would like to do is solve both the world model and the policy problem of how do you actually gather good data, right? So in work with some colleagues here, what we have done is build models that have two basic components. So not just the world modeling system that learns to predict the environment, but also a self model that learns to predict the own world model. And by virtue of that, embody a kind of curiosity or intrinsic motivation principle. And then this intrinsic motivation principle, the self model directs the agent towards interesting actions, which in turn allow it to learn better world models and therefore have better curiosity. And if you implement this in a context of a baby agent playing in the world, and build and learn neural networks for each of the components that I mentioned a moment ago, actually what turns out is that a whole series of standard but powerful developmental phases arise. So in particular, the agent first learns about its own motion, the consequences of its own motion, but eventually gets bored, and by virtue of being bored, starts to play with objects in the environment, noticing and playing with the objects, and looking at them more, even though no notion of object was built in. And by virtue of this, gets much better at solving world modeling problems, and also, in fact, developing simple planning behavior, like if the object is not in view, turning to find one, if it's too far, moving toward it, and finally staying with it. And it turns out that if you do these kinds of things, not only do you do better at solving the world model prediction problem with these kinds of curious-based policies, but you also start to generate very interesting behavior, like the agents learning to bring objects together so you can bang them, which is a very natural baby-based kind of behavior. In the long run, what we really want to do is capture intuitive physical play through a series of systems: the computer vision system, the dynamics prediction, and the coupling in of the curiosity-driven policy, and eventually bring those back to how to learn, more robust robotics models, with the idea of being building, better working forward predictors, better models of early childhood physical play, and better ingredients for robotic-based, model-based control and planning. I won't have a chance to tell you as much about social or multi-agent interactions, but I'll just leave you with the idea that it's possible to also apply these kinds of curious intrinsic motivations to learning how agents pick up on animacy and interact with other agents. Essentially the idea being that animate attention is something that arises from a young age. How is this happening? How do the organisms learn to compute this? Our hypothesis that we've done work on recently is that static stimuli that are not agents are sort of boring. Random stimuli are too complicated and pointless to predict, but animate stimuli are kind of in this sweet spot in the middle that allows intrinsic motivations that seek to measure and maximize progress, that is improvement over time, to both be interested in animacy and also good at predicting agent behavior. And I won't have time to tell you about the whole thing there, but what I will just leave you with is the idea that one can start to begin to apply these techniques not only to making better systems for automatically generating animacy, but also comparing them to real human gaze experiments in terms of which types of things humans spend time on and thereby learn about, in particular that they're much better at detecting animate stimuli. So I will wrap up with just reminding you that, what we do in our group here is we try to build better AI systems and have those in turn make better models of cognition and neuroscience. And we've also really started to repurpose ideas from cognitive science to make better models of artificial intelligence. So thanks a lot.
Okay, great. Thanks so much, Dan, for a very interesting talk. I'd just like to again remind everyone that you can submit questions for any of our speakers by going to the event page on our website. And our next speaker is Chelsea Finn. She's an assistant professor of computer science and electrical engineering at Stanford. We're very lucky to have her here. Welcome, Chelsea, and it looks like you've unmuted yourself and you shared your presentation. All right, take it away, thanks.
Thank you for the introduction, Surya. So today I'm going to be talking about how not to create a robot's mind. And I'd like to actually start with a bit of a story of recent history. Like Matt mentioned, there's a deep history of deep learning, including in robotics, but success was limited to relatively simple problems. So I'll start my story in 2015, which is when I worked on the first project that tried to use deep learning to allow robots to learn complex manipulation tasks from scratch through trial and error. And here's kind of the final learning algorithm that we developed. In particular, we were aiming to train a neural network that mapped directly from images taken by the robot's camera to torques applied at the robot's joints. And what you can see here is at the beginning of the learning process, the robot hadn't learned, didn't really know anything about the world, was starting from scratch, and so forth. And over time, through trial and error, the robot is able to improve and make progress on this task of placing this red block into the shape sorting cube, and ultimately figure out how to solve the task for different positions of the cube. And here's an example of the final policy where you could also see the first person view point of the robot shown in the bottom right. So we succeeded at our goal of learning end-to-end a neural network that can map from images to torques. And we were really excited about this, not because we had a robot that could play with a toddler's toy, but because we had what we thought was a general purpose reinforcement learning algorithm that could enable a robot to solve a wide range of tasks. The robot could use the same algorithm to place the claw of a toy hammer underneath a nail. It could use that algorithm to screw a cap onto a bottle. And a slight extension of this method could also enable a robot to use a spatula to lift an object into a bowl. Now, and this last task is actually quite challenging because the robot has to fairly aggressively maneuver the spatula underneath the object. Not only were we really excited about what we were able to accomplish, but it was also at the forefront of the press, with the New York Times writing that it represented a significant advance in robot learning to train a two-armed robot machine to match human dexterity and speed in performing these tasks. And the new approach included a powerful artificial intelligence technique known as deep learning. Further, beyond the press, not only were we excited about this, but part of the research community was also excited about it, building upon the algorithm to allow their own robots to learn other tasks, like hitting a puck into a goal, like opening a door, and throwing an object to hit a target. Also, like Matt mentioned, there was also simultaneously work on applying the same flavor of deep reinforcement learning algorithms to video games, board games, and simulated legged robots. So I would argue that this is where the state of the art was in 2016 for developing intelligent embodied systems. And at the time, it also seemed like to many that these systems had the potential to have a substantial real-world impact. But we have a big problem. The problem is that the robot didn't learn how to use spatulas to lift objects, and it didn't learn how to hit pucks into goals. The robot learned how to use that spatula to lift that object into that bowl. And if you gave it a different spatula, or if you changed the tablecloth, the robot wouldn't be able to succeed. The entire universe of that robot was that one environment with that one spatula. You may say, okay, maybe we can just give the robot more spatulas and it may be able to generalize more broadly. And in many ways you would be true, but this is perhaps missing the point. These systems are analogous essentially to training a baby to use a spatula before they've learned anything else about how the world works. And from this standpoint, it seems ridiculous to think that we would get an intelligent robot mind as a result of this training process. So clearly, if we're aiming to develop intelligent robots, we need to go back to the drawing board and fundamentally rethink our approach. So how do we do this? Well, one way to look at our problem, our current problem, is from a machine learning perspective, is that our training data distribution looks something like this on the left, and ultimately we want our distribution to look more like what's on the right, something broader. For example, we're currently training our robots in a lab environment, and we want our robots to be able to generalize and operate in the real world. So how do we try to bridge this gap? One natural reaction is, well, I know a lot about spatulas. I know how to use spatulas in a variety of different ways. I know how to operate in the real world. Can I build my knowledge into the algorithm to help the robot? For example, can I build in my knowledge of physics, my notion of objects, develop certain architectures and so forth? And I think that this might not be quite the right approach. And this is for a couple of reasons. While we humans are good at generalizing, we don't know exactly how we do it. There's kind of the whole field of neuroscience and cognitive science is devoted to this, and hopefully we'll learn more from the talks today about how we do this. But even if we do know how we generalize, we also don't know how to program that knowledge into these AI systems. That's the approach of symbolic AI that has kind of a long history of not being quite as successful at these kinds of problems. So can we do better? I think that another way to approach this problem and to look at this problem and to actually learn from the way that humans learn is to instead look at kind of a higher level. We know that humans accumulate and learn from broad data and broad experiences by exploring the world, interacting with many different objects, trying out many different things. And so if we want robots to be able to develop more general levels of intelligence, perhaps we should also take some inspiration from humans in this way. And in particular, if we want robots to generalize broadly, maybe we should train them with equally broad data. Maybe we should train them in the real world, experiencing a wide range of situations, not in a lab environment. So today I'll be talking about, first, how can robots acquire broad and diverse experiences? And second, once we acquire those broad and diverse experiences, how can we develop algorithms that can learn from such data? So first, let's talk about how we can actually get, how we can allow robots to actually get broad and diverse experiences. So one first approach that we could imagine taking is have the robot collect data with random actions. This would look something like this. And we actually get surprisingly diverse and interesting interactions in this way. You can also give the robot some towels and program these same random actions. And you also get some interesting interactions as well. And the really nice thing about collecting data in this way is that we can collect a lot of data this way. The robots can run overnight, they can collect data and explore with these random actions 24/7. But the downside of this data, of course, is that it still has limited utility. The data is largely going to be limited to learning relatively simple tasks. So how might we try to collect a little bit more interesting data? One approach to collecting more interesting data would be to have a human provide some demonstrations of what interesting things to do are. For example, by guiding the robot arm through various motions. This is great because we can get pretty interesting and useful data this way. But we can't get a lot of this data because it requires a human to collect all of the data. Another approach might be to look at novelty-seeking methods. So there's actually a long history of studying exploration and curiosity in cognitive science and AI. And we took one of the state-of-the-art methods called Plan to Explore that was developed actually and was published this year. Our goal was to get the robot to open one of these drawers, and specifically this drawer right here. And what we found is that if we ran this algorithm on the robot, it was able to figure out how to put its arm in kind of a diverse range of configurations, but it actually never really figured out how to interact with all the objects in the environment. It interacted with them very rarely. And with this in mind, one way to think about this is, well, when babies are kind of in environments with humans, they aren't just kind of exploring on their own. They can also see what their parents are doing, for example. And so it's reasonable to not consider a completely self-supervised approach for this problem. And so the question that we asked is, how can a person help the robot, but ideally help the robot in a way that doesn't require that person in the loop of the exploration process itself, like in the demonstration scenario? So to approach this problem, we kind of have a two-step process. First, a person shows examples of interesting states to the robot. For example, states where the robot is opening this drawer in varying configurations. This is kind of teaching the robot what are some of the interesting things that you can do in the environment. And then simultaneously, training a classifier to classify interesting examples versus data that the robot explored itself. And second, training the robot to explore to find images that are classified as interesting. So the way that this works is we basically just are kind of alternating between training this classifier and trying to explore to find the interesting things. And after less than 3 minutes of human guidance to show some examples of interesting things and running autonomous exploration, we get a policy that that kind of first moves towards the drawer very quickly and eventually learns how to interact with the drawer and play with the drawer in different ways. So this is kind of a lot more interesting behavior. And we also see that if we actually mathematically, quantitatively count the number of episodes in which the robot touches the handle or moves the drawer, it's substantially larger with this more directed approach than with the approach that I mentioned previously. And really the kind of the takeaway here is that a small amount of human guidance can go a long way if the algorithms are specifically aiming to kind of leverage both their own exploration and their own autonomous experience in combination with that human guidance. Okay, So that's the kind of first step of how we can acquire broad and diverse experiences through autonomous data collection. Now, how can algorithms actually learn from this kind of data? One of the things that you may have noticed is that with this kind of data, in contrast to robots learning how to use spatulas, there's no notion of progress or success from this data. So we can't just apply reinforcement learning out of the box to this kind of data. And this is perhaps a good thing. And in particular, we aren't going to try to learn one very narrow task. We're going to try to learn something that can be used much more broadly from this data. So in particular, what we're going to do is we're going to, after we've collected this data, we're going to learn how to predict what will happen in the future. This is akin to the world models that Dan was mentioning. So we'll learn predictive models that can predict what the future will look like based on the actions the robot takes. And for different action sequences, the robot will predict the future. And in contrast to the task learning approaches that I mentioned before, these models capture general purpose knowledge about the world, about physics, about objects, and they use all of the available supervision signal. And also, because we're actually learning these models directly in pixel space, there's no assumption about task representations or about objects, which means that it's very easy to readily apply these models towards deformable objects like towels, for which there's no clear representation. Finally, the thing that I'd like to emphasize with these models is that this sort of prediction is inherently a supervised learning problem. And so you're training a neural network to predict, to kind of output future images, given the current image in your sequence of actions. And by nature of being a supervised learning problem, this means that larger models with more data will lead to better predictions. And for example, in this recent work by Ruben Villegas, he showed that if you really start scaling up these video prediction models, you can get pretty remarkable predictions from these models that are able to fairly accurately predict how these shorts will deform as you try to pick them up, and how this towel will deform as you pick it up and move it to a certain position. So I think that these models are something that's going to be particularly scalable. Now, how do we actually use these models to accomplish tasks? What we do is we plan. We come up with plans based on our model of the world that we think will achieve our desired outcomes. And this procedure for this is quite simple. So first we consider a number of potential action sequences. Then we predict the future for each action sequence by running that action sequence through the model. Then lastly, we execute the best plan. We can optionally also replan at each time step and kind of refine the plan that we came up with before, especially if something unexpected happened. Okay, so overall, we collect data, learn a predictive model, and then plan using that model. How well does this approach work? So we took a single model. In this case, we're just going to train it on the random data that I showed before. It's a pretty large amount of random data. And we're going to plan with this single video prediction model to try to accomplish different tasks that are given to the robot at test time. So for example, one task shown here is to try to lift this stuffed animal upward. And we see that the robot can figure out how to do that using its model. Another task is to move the sleeve of this shirt over to the right. The robot can also figure out how to do this task. We can give it a task like picking up an apple and putting it onto a plate while keeping the plate stationary. And the robot can also predict the future and use its predictive model to figure out how to solve this task. And we can also give it tasks that use deformable objects, like trying to roughly move a part of the shorts upward to fold the leg of the pant. It can figure out how to maneuver an object to a different position. And it can also figure out how to cover an object using the towel. So while these skills are a lot coarser than the more complex skills like using a spatula that I showed at the beginning of the talk, and the success rate is also a bit lower, the important takeaway here is that by leveraging broader data and figuring out how to learn from broader data, we can get substantially broader generalization to many different kinds of tasks and also many different kinds of objects. So a number of these objects shown here were actually held out during the data collection process, and it's able to generalize to those because the model that is trained isn't specific to one object and because it's trained on much broader data. Now, what if we have a little bit more interesting data than just random data? We can incorporate this into the process as well. So we can, for example, take the demonstration data that I showed before. This is diverse demonstration data of many different kinds of tasks, specifically using tools in different ways. We can incorporate this into the data to improve the model, the data for training the model, but we can also incorporate it into the other two steps as well. So what we'll do is we'll learn a model of the kinds of actions that the human would perform. We'll use this to collect additional data along the lines of kind of more interesting interactions. And we'll also use it to guide the planning process to consider both a range of actions that the robot considers, as well as actions from this model that might look a little bit more like what the human would have done. And by incorporating demonstrations into the model and into the planning process, we can do more interesting tasks. So we can solve new tasks that the robot didn't see in the demonstration data, such as sweeping these objects into a dustpan. We can also allow the robot to figure out how to reach an object that isn't within its reach. So in this example, we restricted the robot's arm to the green rectangle and told it to try to bring the blue object closer to itself. And it figured out that in order to accomplish that task of bringing the blue object closer to itself, it has to pick up the hook and use it to solve the task. It can also use unseen objects as tools of some sort. So it had never seen a sponge before, but it's able to figure out that by picking up the sponge and wiping it across the plate, it can use this, it can accomplish the task of moving these two red pieces off of the plate. I can also use objects such as water bottles as tools, which wouldn't conventionally be seen as a tool. And lastly, the robot can decide when to use a tool, such as when it needs to move two objects, and when not to use a tool, if it's just more efficient to move a single object that's commanded to the desired position. And the thing I'd like to emphasize here is that in all of these tasks, the robot isn't explicitly told that it should use an object as a tool. It figures that out on its own, and it figures out that the fastest way to accomplish the task that is given are to use a tool, or in the last example, not to use a tool. So the takeaway here is that with more sophisticated data, this enables more sophisticated behaviors, but also without sacrificing generality. We're still able to accomplish a wide range of tasks with a single model, with a single planning procedure. Okay, so to wrap up, kind of main takeaway that I'd like to convey is that if we want robots to generalize broadly, we should think about training them with equally broad data, something that's a little bit closer to the kinds of experiences that a human experiences when they are developing. I talked about how robots can acquire broad and diverse experiences, and how a small amount of guidance and teaching from a human can go a long way. And I also talked about how we can develop algorithms that can learn from such data by learning models of the world and using those models to plan. We saw that broader data led to broader generalization, and more sophisticated data led to more sophisticated behavior. These takeaways shouldn't be kind of anything too surprising, but we can find that they actually hold in practice, and it suggests that we should be training robots on broader and more sophisticated data. And most importantly, these are steps towards robots that can generalize rather than training a robot on a single task. Now, looking to the future, I'm really interested in moving towards AI systems that can more broadly understand their world that they're in. And so I think that there's two kind of important directions towards this goal. In the context of robot learning, we've really barely scratched the surface of data scalability. I showed examples of robots learning from data with many different objects, with many different kinds of interactions. But we can still really take this substantially further by training robots in different environments with different camera viewpoints and so forth. And so towards this goal, we started to develop an open database called the RoboNet database that we want to kind of allow us to accumulate and share data across institutions, across robots. It already contains data from more than 4 institutions, data from 7 different robot platforms, and has 15 million frames in it. beyond kind of sharing data within the robotics community, we've also started to develop algorithms that can learn by watching videos of people. Videos of people is a source of data that's just widely available on the internet and in various data sets. And if we can figure out how to learn from videos of people doing things, then we could substantially expand the sources of data that robots can learn from. And then beyond robot learning in AI more broadly, I think that we also need to be thinking about whether we can generalize beyond the data distribution. So far, one of the predominant techniques in AI is machine learning. In machine learning, we typically make this assumption that our training and test distributions are going to match, and that our data is going to be drawn IID from this distribution. And this assumption is actually pretty strong. And I think that we can actually develop different assumptions that may allow us to generalize beyond the data distribution. And we've started to explore these kinds of assumptions by developing algorithms that are robust to distribution shift and are robust to new environments by being able to quickly adapt to these new environments. Okay, and that's it. I'd like to thank my students. All the students here played a really substantial role in the work that I presented. Also, if you're interested in learning more about generalization, multitask learning, and meta learning, which I didn't actually talk too much about today, all the slides are available for the course that I teach at Stanford, CS 330. Thank you.
Okay, great. Thanks so much, Chelsea, for a fascinating talk. So please stay on, and I'd like to welcome back Chris, Matthew, and Dan so that we can begin our panel discussion and take some of your questions. Again, questions can be submitted on the event page of our website. Chris, Matthew, and Dan, if you can turn your video and mic on.
My video's on, but it looks like I'm frozen in my little window. Am I moving in yours?
We can hear you, Matt. That is Matt, right? Yeah. Okay.
Yeah, but no video?
I don't see a video of you. Okay, now I see a video of you.
Oh, okay. Now, yeah, I just started moving on my own screen. Good.
Okay, I think we're good to go. So I'll start by asking the first question, which is a kind of I think a question for each of the panelists. I'll allow each of you to opine on this question. It's a very big picture question, and maybe a slightly adversarial question, right? Is if we define the moon as trying to approach general human-like intelligence, are current deep learning or other learning approaches akin to climbing a tree to get to the moon? If so, what do you think are the most important ingredients that we're missing? And if not, why do you think existing methods, maybe with slight modifications, might actually scale up to getting to general intelligence? So I think I'll let each one of you give your thoughts on that, and then we'll dive into more concrete questions. Should I call on someone?
Looks like you've stumped them already.
Yeah, I don't know the
I want to
answer.
hear what the other speakers have to say. They're going to give great answers.
Well, let's just keep it most. What do you think is the most important ingredient that we're missing at the moment, or that we need to expand on to get to more versatile artificial intelligence systems?
Can I answer that in a way that's going to turn into a question for Chelsea?
Sounds great.
So Chelsea, you ended your lovely talk by referring to richer models of the world as an objective for us now, and you talked about prediction, and oftentimes, I mean, there are some cool examples of how you can go beyond this, but oftentimes in machine learning prediction, for video is pixel level prediction, but a deeper understanding of the world seems to suggest something that isn't tied to pixels. The example that I often think of is, I know if I throw a brick at a window, it'll break, but my knowledge of that is not encoded in visual simulations of where every shard of glass would fall. So these kinds of abstractions, these kind of conceptual abstractions, they seem important. Maybe we can get by without them, or maybe they'll sort of emerge without our having to worry about them if we have enough diverse data and the right kind of architectural biases. But it seems like something worth discussing. So that's a question for both you, Dan, and you, Chelsea. Like, are these kinds of abstractions important, and how do we get them?
So I can take a shot at responding to this, to I guess both of your questions. I think that in terms of getting to the moon, I feel like we haven't exited the atmosphere yet. I don't know if we're climbing a tree, but I feel like we kind of made some progress, but are not maybe through the most important milestone there. I think that, I guess, well, first, I don't know, but I can, of course, speculate on both of these problems. I think that there are fundamental aspects of machine learning that obviously aren't going to take us all the way. One is the IID assumption that I was touching on at the very end. I think that humans can obviously, it seems like we don't have this IID assumption, and both of you know a lot more about humans than I do, but it seems like we're going to need to figure out how we can generalize beyond our training distribution in some way, and figuring out what assumptions will allow us to do that. And perhaps getting at Matt's question, I do feel like it does seem like we need better abstractions. There are certainly things about these pixel prediction models that don't work quite as well. It does seem like we haven't yet hit the limit of these models yet. Even if you make these models bigger, we get better and better predictions, and we can still substantially increase the data that we're training these models on as well. And if you take lessons from computer vision, for example, we know that as you accumulate data, or language at this point, as you accumulate data and as you train bigger models, you'll get better and better predictions and so forth. So I think that we have a lot of progress that we can continue to make with these kinds of models, but I also think that we need to figure out what will allow us to move beyond the training distribution. And abstractions may be an aspect of that.
Okay. Chris, do you want to ask a question?
Okay. I was thinking a bit about, it seemed like there was some kind of core that tied all three parts of your work together. And maybe they didn't all quite come together, but it seemed like both Dan and Matt were talking about the importance of recurrence and feedback loops, and Matt was certainly talking about meta-learning and how it could be implemented in the brain, which sort of also then connects very closely to a lot of Chelsea's main work. And so I thought maybe we could talk a bit more about the center of that interaction. I mean, if I start with a sort of an easy giveaway for Dan, I mean, you mentioned the importance of having recurrent networks with your making recurrent vision networks, that there was a little box on the slide at one point saying not an LSTM, but you didn't really say anything about what kind of model of recurrence was successful and important for your visual system. So you could maybe concretely say a little bit more about that. And then sort of thinking more to Chelsea and Matt. I mean, Matt, you touched on the work about how it seems like brains will both learn quickly for fast understanding and then learn much more slowly with sort of slower reorganization. And well, you can sort of make an analogy to that, to how meta-learning systems work with an inner loop and an outer loop, but I'm kind of not really convinced that current meta-learning algorithms are working on the same kind of scale as what we're talking about when psychologists talk about human brains learning on two scales. So maybe Dan first, and we can talk about this.
Right. Well, so yeah, no, I mean, I would say recurrence is probably important. I did start with it. And it is true that, circuits that, in a recurrent circuit, it turns out there's sort of basically two things that are important to make it integrate well into a deep convolutional stack. One is that it be gateable, kind of like an LSTM. That is to say, it's sort of multiplying things by, numbers between 0 and 1 in a kind of learnable way. But it should also be, be such that in the 0 state, it actually doesn't screw up the computation the way that an LSTM does. So the LSTM 0 state essentially doesn't pass through the data. And so it feeds, if you push it in, it sort of screws up the feed forward pass. So there are a couple of
So you
things
essentially
do
want
with
an
the principle.
LSTM with a residual connection, and then
Yeah,
you'd be happy.
it's a little bit like that, except that there's a class of things that make them work that seem to work. But you know what, I would actually say that I think that I'm much less impressed with the importance of recurrence than I am with something that sort of came up a little bit toward the end of Chelsea's answer to Matt's question, which is, or to Surya's question, one or the other, which is like, what are the things that actually need to be built in to actually be able to, like, say, learn prediction with like reasonable amounts of data, and like what are the right latents that you're going to use to make predictions work that are not going to be pixels. And so, you know, in the part of the work that I talked about that I probably went over too fast, I apologize for that. What I think is most important perhaps in this is this sort of physical scene graph idea, you know, where you can have a sort of unified, like 3D, it's somewhere between a unified 3D computer vision problem and a symbolic computation. Like, how do you represent scenes with objects in them in such a way that you can have the richness that Chelsea was asking for while having them be learnable in a flexible way and not be sort of bound to particular very kind of like hokey, like toy concepts of objects. And I think that figuring out what those intermediates are such that you get good latents for forward prediction is really one of the key missing things. And, you know, I feel like, you know, if I were to pick between the importance of recurrence and the importance of physical scene graphs and methods for understanding those, I would actually be much more bullish about the importance of the second one. Although it is actually true that you do need or seem to benefit a lot from recurrent computation in computing the scene, because basically you really would like to combine high resolution, low level features and abstract high level features and together to get good understandings of the objects and the way they're related to each other. And of course, that is well expressed by a recurrent network, convolutional recurrent network. You know, so I mean, recurrence comes in there.
Okay, maybe we should get a few thoughts from Matt or Chelsea.
Oh, sorry, I just want to say one thing about space.
Okay.
We are climbing a tree, and we should be, because we should be climbing the evolutionary tree.
Oh,
Good twist.
Matt, can I just add to that, because I mainly want to agree, and then I think I'm going to bring up something that may represent a difference of opinion between Dan and me on the one hand and Chelsea on the other. So I'm going to throw this to Chelsea. Recurrence. I want to kind of double down on what Dan was saying about the role of recurrence in something like graph representation. Of course, graph nets are recurrent networks. What recurrence is doing there is not what it's traditionally done in most applications of LSTMs, which is temporal integration, integrating across like words in a sentence, or it's integrating across elements that might exist simultaneously in a display or in a graph-like structure. And to me, this is holy grail stuff, because I'm one of these people who thinks that compositionality is really essential to cognition, and looking for ways that deep learning systems can compute in a compositional manner seems totally fundamental. I'm a big fan of transformers because they have a kind of built-in scheme of individual elements that are then modulated by their context.
Can
and of course, you can.
Yeah,
go ahead.
For a fine point here, I mean, you know, from a formal theory point of view, there's this shift from true recurrence, where it's infinite, it keeps on going along, and regardless of whether you're looking at typical things like graph convolutional neural networks and graph neural network or transformers, we're saying, oh, forget about that. Providing you can do a few steps of integration, you can do pretty well. So is that sort of the position you're advocating?
You know, I don't know. Maybe there's an approximation story here that will get us where we want to go. So I don't know. I'd like to hear what Dan has to say about that.
Well, like, I mean, basically, you know, it's a very complicated. Let me put it this way. I do think that the key question is which particular bias you should be using, and the bias you have when you build an recurrent network in the sort of standard sense is like something like, let's say, I don't know, maybe LSTMs, and the bias when you're building, graph network is like something that like basically does adjacency matrix computations, and then when you're building a transformer, it is indeed a kind of RNN but with a different kind of bias, and so I don't know that I would say that like I have a clear opinion of which one is the right one in every context. I think that's really going to shake out based on how things perform, and if it turns out that there's one structure that's good for everything, well, that would be really cool to find out. And this goes back to the question of how you climb the evolutionary tree, because you really want something to not be too complicated, right? It's got to be able to arise by climbing a tree, right? That actually has to happen in a way. Maybe one thing that I would add is that graph networks are very interesting to me, and transformers are very interesting. And I think they've allowed us to get some very powerful results in the sort of physical scene graph domain, and others obviously as well. One thing that is true is that if you're going to make the map to the brain, you have to have a fixed number of units, because the brain doesn't change the number of neurons with different scenes, right? So at the end of the day, there's got to be like a physical machine that has like a fixed number of units that sit there that is actually doing the thing. And so at the end of the day, even if it's a graph network, a graph neural network is in some sense not a neural network, right? Because like it allows you to have like different numbers of nodes on different inputs, which is very, very excellent from an abstraction point of view. It's excellent, but it's terrible from the point of view of actually making a brain mapping, because you break this basic principle that like the units should correspond kind of to the units, right? And so there has to be a way of titrating it so that you end up with a thing with a fixed number of units that actually computes the abstraction. And of course, in a certain sense, whenever you implement a graph neural network on a GPU, you're doing that. There's like an operation like indexing, which basically squeezes out the zeros to the end, and like those are not the nodes.
And you could say that the transformer networks are like that, right? Because they are a fixed structure, not the graph neural network idea.
Exactly. So I think that's what I was winding up to, is that we need to be probably biased towards things that have that property to them.
Okay, shall we get a few thoughts from Chelsea? Or Matt wanted to jump in. Matt.
I just wanted to say we might be able to gain some insight from neuroscience and psychology here, because there's plenty of evidence that, from multi-object tracking studies, that the human brain is capable of tracking a very limited number of objects, and maybe that's a reflection of how many. It's not a reflection of a limited number of neurons. It's a functional level limitation, and maybe that's a good bottleneck for us to have. The question I was going to ask Chelsea was: it sounds like she's not on board for this graph representation. Chelsea, some of the things you said made it sound like you don't want to build systems that are endowed with some a priori notion of what objects are. You want enough data that'll emerge spontaneously. Is that how you think about it?
I am not. I guess I don't like being dogmatic about these sorts of things. We haven't yet seen evidence that like the more object-centric approaches really scale to diverse scenes, to complex objects and interactions and so forth. If there was more evidence for that, then I would be all on board with using them. I think I'm a very kind of empirical, or I like to see what works and go with that. And it seems like whenever we try to impose a certain representation on top of neural networks, it seems like so far that hasn't really panned out to big successes in comparison to approaches that try to recover the representation themselves.
Well, we'll hear from Josh Tenenbaum at the end of the day. So yeah, we might get new perspectives on that as well there. Actually, this is all this discussion is pertinent to a question that was asked by the audience, and I'll expand on. Basically, the question was, how do attention-based models compare with recurrent neural networks from a biological perspective? And just to expand on it, so for example, transformers are doing very well in language. Very recently, they're doing quite well in vision. So is there good performance alone an argument for comparing representations of transformer architectures to representations of the brain? And more generally, what would you conclude if they match even better than recurrent networks? And more generally even, are there sort of criteria other than performance and representational match that we should use to ascertain the success of whether a machine can compare accurately to a brain? I think this might be more for Matt and Dan, because you spend more time comparing machines to brains.
Dan, all you.
I actually second the idea of not being dogmatic in the sense that, like, as long as there's some way to define a mapping class where units look like units, then I'm willing to try whatever approach and see which one best matches the brain, essentially. You know, like, so I mean, I don't know how to separate in some clear line test way, like biological recurrence or from, you know, transformers, from RNNs. Like, they're all related to each other in a kind of computational way, and in some sense there may even be computational universality that allows you to say always recast one in terms of the other. Really, the questions are like quantitative, like, you know, given a certain amount of training data and a certain task, like, you know, and a given amount of data used to make the mapping between the brain and the model, how well do they match on new instances? And it's really an empirical question. You know, the one thing I would say is that, like, whatever the model is, it's got to be able to actually stand in relationship to the brain the way any other brain does. So that's my bottom line, is that the mapping between the model and the brain should resemble in form, should be computable on the same data as data recorded from another animal of the same species, let's say, right? So in the case of like neural recordings, electrophysiology, it's like you've got a data matrix, which is like stimuli by neurons or neural sites in the recording. And, you know, you have data that come tensorial shape that come out like that from a neural network, if it's indeed a real fixed size neural network. And you can, ask, do mappings that map one brain to another using the same mapping class. How well do you do in trying to map the brain with a neural network? And, as long as you have that there, you can compare them, and maybe it'll turn out that one or the other structure is better. And presumably the core thing will be, are the structures that perform best, and on what do they perform best, are also the ones that match the brain best? That's the big question, right? Do those things coincide? Therefore, I guess I would say the only criteria is, can you actually write down the mapping in the same way as you would if you were mapping an animal to animal? And that's where I think the discussion somewhere between transformers and RNNs is a little more natural than, say, just graph neural networks as such. Although graph neural networks are easy for us to think about as programmers in a sense. But yeah, at the end of the day, it's got to work on the real world tasks. And I think that point emerging from our previous discussion is actually super critical. If we're going to impose structure, they better not be so ornery in their nature that you can't get them to work and in fact surpass the other things on real world tasks. That's the critical point. Chelsea has high standards, and we should meet those standards with our new structures. That's the key thing.
Okay.
I'll just quickly add, I think there's a paper from Ev Fedorenko's lab on bioarchive specifically looking at whether representations from transformers do a better job than baseline models on fMRI data. I think that group reached a positive conclusion. I haven't read that paper in detail yet, though.
Yeah,
Dan,
that's great work. That's led by Martin Schrimpf and there. And I think that they found that for looking at basically language areas, GPT-2, they didn't test GPT-3, but GPT-2 is substantially better than alternatives. And it's also better at the task. So again, those things seem to go together. It's like we're climbing the evolutionary tree, Surya, right? That's what we're doing.
Let me ask a follow-up question, which is in a way staying on the same theme, since transformers and GPT-2-3 have already come up. And maybe I'll start this one with Chelsea. So, I mean, you had some more sophisticated messages in your talk, but the most simplistic message was, we just need to train our systems on much broader data. And I think, in some sense, that's a difference between necessarily something like robotics, where the sort of starting point is you've got one robot that you're training to do one thing, and natural language processing, which is where I spend my life, because, long before neural nets became cool again, right? That there's at least 40 years of history that everyone knows that the best way to produce some natural language component, whether it's doing question answering or something simple like parsing, if you want it to perform well in general, you want to train it on broad data, because that just gives you an easy generalization. But I mean, if we try and like, how much is that the solution? I mean, if we try and connect it back to child learning again, I mean, one of the things that child psychologists have noted is that actually kids are learning these skills not on broad data, right? Depending on the family, most families might only have 2 spatulas, or you've only got one set of colored blocks to play with in your pen, and yet somehow that's a way that kids can generalize. So what does that say about what we should be doing for building our AI learning systems?
Yeah, so I think that you're absolutely right in that fields like natural language processing and computer vision have already figured out how to use really broad data sets. I think that in this respect, robotics and embodied learning is very far behind other aspects of machine learning because we haven't yet figured out how best to actually collect large data sets and learn from those large data sets. And I think it's a message that the reinforcement learning community really needs to hear, because if you look at the kinds of environments that people train on, they're like this little like half cheetah thing in a 2D world with it's just like a plane is like the entire world. And we need to be thinking more fundamentally about like, can we bring robotics and embodied learning into the kind of modern ages of machine learning and deep learning and figure out how to actually generalize and train these in more interesting and complex and diverse environments. So I think that in many ways, just robotics and reinforcement learning is very far behind and needs to catch up a bit. I also agree that it's not just a matter of scaling up. I think that the failure cases of GPT-3 suggest that even when you scale up to large data, large models, and so forth, there are still cases where these models fail in unintuitive ways that are different from how humans fail. And that gets into my last point about figuring out how to go beyond the data distribution and figuring out what sort of assumptions we can bring into the machine learning process and into the system that will allow it to generalize broadly. And I think that's where most of machine learning needs to go.
But you know, if I push a little bit more on that, I mean, isn't perhaps, you know, couldn't you make an argument that actually no, there isn't a, it's not that robotics learning is way behind, you're actually where you should be, right? Because I mean, I think the facts are for kids, you know, if I think slightly bigger kids than babies, you know, if I have my 5, 7, 9-year-old and I take anything that they haven't seen before, you know, whether it's this is how you flip a pancake or this is how you use a corkscrew to open a wine bottle, though they shouldn't be opening wine bottles at the age of 7 and 9. You know, I can demonstrate that with, you know, one pan and one spatula, and well, okay, they need to try pancake flipping slightly subtle, so they need to practice a few times before they can do it well. But it's not that what they need practice flipping, but then they don't need practice of having to learn with different spatulas, right?
Yeah, and I will argue, like, I guess my message isn't to train these robot systems on 1,000 spatulas. And the systems that we were training on the end, they aren't, they're trained on kind of a really diverse range of objects. Like we just buy a bunch of objects on Amazon or at the dollar store or whatever and give them to the robots. We don't give it like 100 spatulas and 100 whatever. It's more kind of like the transpose of that, where we give it a lot of objects and a few instances per object. So I think that in general, even in the direction that we're moving towards is still towards the kinds of experiences that human children have. The kind of where we were, I think 5 years ago, was it was literally one or two objects, one environment, one like viewpoint, one room, which is like, I mean, it may be kind of unthinkable from people who aren't in robotics, but that's kind of where we were. And I think that we're moving towards something that looks more like where the kinds of data that children experience.
Okay.
Actually,
yeah.
I have a question that relates to this. This also comes from the audience. They actually asked, you know, how do you teach machines to generalize to out of sample distributions? A common one in robotics in your world, Chelsea, of course, is that, you know, it's hard to train robots in the real world. So there's a lot of effort in training robots in simulated environments and then transferring the control policies from simulation to the real world. And that's an important sort of transfer where a lot of algorithms fail and it's sort of out of distribution. What's your take on those approaches? What specifically do you think are sort of promising approaches to deal with out of sample distribution training or testing, and especially in the transfer from simulation to real world?
Yeah, so a lot of the work that we're doing is trying to avoid the simulation to real transfer. I think that in some ways it's a fairly pathological problem because there's a really substantial shift between our simulators and the real world, just because we actually don't have great models of physics. Physics is really complicated, and that's kind of one. And second, actually building rich simulated worlds takes a lot of effort in engineering. And in contrast, we can get a really interesting, rich and interesting world by just putting robots in our real world, right? And so if we can figure out how to store data, how to allow robots to collect experience and learn from that experience, then we don't have to solve the sim to real transfer problem. That said, of course, there is there's still this problem of handling distribution shift. The robot will enter a new room, it will encounter new objects, it will want to do something new that it hadn't done before. I think there are promising approaches in the robustness literature and the domain adaptation literature that tries to solve this problem. It's also an area that we're actively working on ourselves, where instead of trying to be robust to distribution shift, we try to really quickly adapt to distribution shift. But it's really an extremely active area of research, and a couple of the works that I mentioned on my last slide are trying to go in that direction.
Matt, do you have any thoughts about how we do more human-like out of distribution transfer?
Well, I mean, I think meta learning or some of the principles that come up in meta learning are relevant. You can learn how to generalize, and of course, there's plenty of work from images to continuous control taking that kind of strategy. And ultimately, it's hard to answer this question without kind of defaulting to bland statements about priors and how we need priors. There is one problem that I thought of, Chelsea, as you were making your comments, and something about the way you phrased your original question, Chris, which is about continual learning. And this might have been actually on Surya. You had that very nice list in your opening comments of like open problems where we might gain some insight from neuroscience because we just don't know how to do anything relevant in AI. And I think this is one additional case. The ability that humans have to learn something new, to utilize that information immediately, and also to retrieve it much later. So, a child, I don't know whether children still play with these things, but when I was a kid, the jack in the box was a very common object, and the first time you see somebody turn that crank and then the whatever it is comes out the top, you just need to experience that once and you'll be able to predict what's going to happen the next time you see that thing, even if it's 5 days later. So there's a really deep stability plasticity problem that the brain is solving there, integrating dramatically new information without disrupting long-term knowledge. I simply don't think we are even grappling with this in our machine learning projects much. We still cling to this kind of train test paradigm, which is just there's no such separation in human intelligence.
I completely agree with that. I think that in AI, we feel like we're in this paradigm where we're just going to deploy a static model. That's it. Like it's done. But in the real world, you can't do that. And actually, in industry, people don't actually do that either. They are continuously training their models at various companies because they need to grapple with distribution shift. And we need to, in the machine learning research and AI research field, we need to actually keep that in mind when we're developing algorithms and move out of this train test regime towards something that's like a continuously evolving test set.
Yeah, I absolutely agree. I think that's continual learning is a fundamental problem, I think. Let's see. So along those lines, another question that came from the audience, and I'll expand upon it. Oftentimes when we're trying to create models of the brain, we obtain our networks through learning rules that are not necessarily biologically plausible, like backpropagation, though Matthew, you work on reinforcement learning. And these networks aren't subject to biological constraints. So how do we think about comparing those networks to the brain? What are the ways forward to bake in more biological constraints What are the ways forward to more biologically plausible learning rules, and might they help with these issues of continual learning? You know, is there a bridge that we can construct from our knowledge of biological learning rules to continual learning?
Well, you know, I mean, that was the one thing that I punted on in my list of 4 problems: architecture, task, data set. You know, those are the things actually we've mostly talked about as a group of speakers here. There's that 4th thing, which is the actual procedure for how do you update your parameters given the things you've seen. So I would say that, like, figuring out more biologically correct versions of learning rules is an important computational and theoretical neuroscience problem. I actually basically think it will not change anything from an AI perspective. I think biology has been particularly unproductive, and neuroscience has been particularly unable to provide insight into better learning rules. It's been great, we're pretty good on architecture. Cognitive science has been great on task. It tells us a lot about what the data should be, although, as Chelsea said, you know, it's challenging to actually get the robot into the environments, but it's clear what should be done there, kind of. But where I think neuroscience has been actually quite poor is telling us learning rules that are helpful at all. I mean, like the standard stuff coming out of neuroscience is just totally failure, it seems to me. You know, in terms of actually making learning rules that are good. So, you know, my bet is that, like, if there's going to be better learning rules that work, they're not going to be coming from an obvious place of biological insight. Although making learning rules that are more biologically plausible is a real theoretical neuroscience and computational neuroscience problem. But I doubt it will. My bet is that will not add to the AI conversation much at all.
Why do you think that is? I mean, you know, I'm speaking as maybe the person who knows the least about neuroscience, but, you know, brains seem pretty good at learning. You don't think that there's something useful to discover there?
I think it's incredibly.
I mean, yeah, when Matt was talking about how effective the dopamine was for implementing learning, right? I don't know.
I think it's incredibly difficult to observe the events taking place that are equivalent to, say, learning parameters in the visual system or something. So the biology is especially black box there. You know, it's like people complain about neuroscience, about deep nets being black boxes, but actually it's the brain that's the black box. And where is the box worst? Where is the darkness hardest to see through? In architecture, you can kind of see, you know, from anatomy what it looks like, and, you know, in the task you observe the behavior, right? But learning rules is the place where it's like the most inscrutable. How you would ever know what is going on by watching the changes. It's just really difficult to do that. And so, you know, I think that's like a functional reason why neuroscience has been so bad at actually telling us good learning rules. That's the part that really did come from, you know, if ConNets came from thinking about the visual system, I think that is probably partially true. You know, and if ImageNet came from thinking about cognition, you know, as Fei talks about, that's clearly true. But, like, you know, the backprop really didn't come from vision, and all the biologists are screaming about how unright it is from a biology point of view, but the alternatives that they present are just trash.
All we got is Hebbian learning. Yeah. What do you think, Matt? Are you similarly pessimistic there, or?
Not quite so pessimistic. I'm not holding my breath for biology to yield insights into learning that will immediately revolutionize AI. I do wish I knew what learning rule the brain uses, and I'm a little bit more optimistic than it sounds like Dan is, mainly because of the revolution in methods that's occurred recently in neuroscience. I just feel like the kind of limitations on what we've learned about synaptic learning rules in brains are partially a reflection of the limited tools that neuroscientists have had up until recently to actually probe what's happening during learning. But with the advent of, you know, calcium imaging and optogenetics and all sorts of crazy new things that people can do in neuroscience, it seems to me like maybe we can take the next step to understanding what's going on, at least in rodent brains. It would be great if we could study human brains. That frustrates me a lot that we can't. But the one thing I'll add is that I feel like on many fronts, if AI is gonna benefit from neuroscience, it's gonna have to prime the pump. people from AI are going to have to go to people in neuroscience and say, this is what we really wish we knew. And because in many cases, those questions are very interesting to neuroscientists. The neuroscientists just haven't thought about it, because especially the ones who are working on these crazy new methods, because they're busy being methods engineers. So these kinds of partnerships can be incredibly powerful. And it's one thing that we're trying to pursue in my group at DeepMind. So I started off thinking about neuroscience-inspired AI, but these days I often think about AI-inspired neuroscience inspired AI, that we're going to have to go to neuroscience, give them questions that they can pursue that are also of neuroscientific interest. And that's how we'll get answers back that may be useful in AI.
Yeah,
just a speculation.
Yeah, I wanted to totally agree here and chime in. I mean, one of the methods that's actually I find quite exciting that an experimental collaborative of mine is actually working on is voltage imaging of multiple synapses in the hippocampus while the mouse is learning, right? So we can start to do systems identification of how multiple synapses change during learning. And I do think that both neurobiologists have been hamstrung by their methods, but also machine learning people have been hamstrung or seduced by the allure of backpropagation, right? We know that learning in the brain is much more local, and there might be completely different theoretical frameworks that are much harder to deal with. For example, you might have different modular subsystems where individual synapses in different subsystems undergo different learning rules, but they work together, say through the framework of differential games, where each one is solving its own little interacting game, and then the whole system comes to a Nash equilibrium. And that mathematics is much more difficult to understand. And so because we've been seduced by backpropagation, we in AI are not going in that direction. And synaptic physiologists are not thinking about game theory. And so this dialogue needs to happen, right? I think the truth is much stranger than what we actually kind of currently understand. And so I really like this idea of, and I've talked about this before also, AI-inspired neuroscience inspiring AI, right? We have to go backwards where AI people really talk to neuroscientists and influence the experiments that they do, right?
Yeah.
That's important.
Look, don't get me wrong. I think that the question of figuring out what's going on and learning in the brain is very interesting. Like I say, I think there's a great experimental, theoretical, computational neuroscience question there. I think that's really true. Where I would say I'm particularly skeptical is that what's going to come out of that is going to be in the short term, or maybe even the medium term, enough better than first order methods that we currently have, that like it's going to really help us do better in AI. Like in AI, the problem that we're having is not really an optimization problem, right? Like if there was a huge freaking optimization problem, then totally, there would maybe be a big space for the new thing to come in and like totally revolutionize something. But actually we're not having an optimization problem, right? We're having an architectural bias problem. We're having a question of what is the task and the environment.
Just to interject really quickly, Dan, because it's on point. I agree with you, we're not having an optimization problem, but we are having a generalization problem, right? And
but again, is that going to be something that
modular biological architectures with limited learning rules, those limitations may actually help with generalization.
So one other thing I'd like to add here is I agree that we have pretty good optimizers and learning rules, but one thing, at least from the embodied learning and robotics standpoint, that we have kind of not a lot of idea, and I'd love to hear insights from neuroscience, is what should the learning signal be beyond the learning rule? So we have things like curiosity and so forth, but like what sort of supervision should we be providing to AI systems? How should I communicate with my robot? How should I tell it what I want it to learn, what tasks it should do, like beyond exploration and so forth? How can it figure out how to do a variety of useful tasks and complete those tasks and so forth? On the robotics side, there's kind of no clear answer to this problem. And also in the machine learning standpoint, like we have supervised learning, we have self-supervised learning, but still we don't really know what the learning signal should be.
Oh yeah, but figuring out totally agree. And that's my point, is that like, there's a big space open in terms of what should the learning signal be. From the point of view of how, once you know what the signal it is, to convert it into changes on the parameters to get the system to do it. That's the learning rule. I think there's not that's not the big pressing gap from an AI perspective. It's a great theoretical neuroscience question. How does the brain do that? But from on the AI side, I think that the gap is smaller there. It's more like what you're saying is like, what should the signal be? And, I'm all for, I think that that's going to be where a huge amount of progress is made on the AI side, and maybe inspired in many cases by cognition. So I mean, I think there's a good loop there.
Yeah, just to give an example, like one place where we thought we had made a lot of progress was sort of reward prediction error and reinforcement learning being a learning signal, and we see a signature of it in dopamine. But then the story is getting much, much more complex, right? Matt touched on it with distributional reinforcement learning. That field is heating up in the fly system, where they show that the dopamine signals coming into the analog of the basal ganglia of the fly signals almost every single aspect of task performance. And that may be better understood through a multitask learning signal that's very high dimensional as opposed to a very low dimensional reward signal. And so I think neuroscience is starting to progress there. But again, the onus is upon us to talk to neuroscientists and say, like Chelsea, say, hey, this is the problem we're having. What could the learning signal be? Matt, you probably have ideas on this because you've thought about reinforcement learning and so forth.
Well, my thoughts on this lead in a somewhat different direction, which is connected with the very last thing I said in my presentation about social science and human-centered AI. So, deep reinforcement learning research started off with games, and there's a reason for that, which is that we know what the reward function is in a game. What's the reward function for Atari? Points. What's the reward function for Go? Win. What happens when you try to move beyond the world of games? It becomes much more difficult to specify the reward function. So if you want to do reinforcement learning, you've got a big problem specification challenge. And by the way, this comes up even in tasks like the ones that you might want a robot to perform. For example, imitation. What counts as a good imitation? I'm not the first person to ask that. There are whole literatures on this. But I think if you sit with this problem long enough and kind of like honest with yourself, the only answer that makes any sense is human preference. Like a good imitation is whatever a human thinks is a good imitation. And I think in the end, the answer that I'm interested in when it comes to the question of where does the feedback come from, I think humans are really the only reasonable source. But that leads to all sorts of other problems. Human feedback's hugely expensive. Chelsea, you pointed that out. And human preferences are notoriously complicated and contradictory. And God forbid you should have to satisfy more than one human when those humans might disagree. So this is one reason that I'm really interested in things like social choice theory now, behavioral economics. I think what's waiting for us, down the line in the path where we're at the top of the tree that we're climbing is that kind of problem specification problem, which is going to lead us back to human feedback. That's just my
way that makes sense. I think that one question along those lines too is beyond kind of human feedback for specifying like things we want it to do, what sort of human interaction can support and structure the learning process itself? So when children learn, there are parents and so forth that can help them learn about the world beyond their own experiences. And so there's the things that like your parents want you to do, but there's also the things that your parents do that help you learn and help you develop. So what are the things that are helpful? We can't just have a robot kind of on its own learning. It probably needs some sort of parents to structure that learning process and scaffold it. And so I think that that's also another open question is what sort of interactions, what sort of world do these agents need to live in order to develop appropriately into intelligent beings?
The idea of needing robot parents seems a very interesting one. But before we quite get to the robot parents, for what kind of world do these robots need to live in? I thought I could ask a bit more about that. You already, Chelsea, earlier in a previous answer said the word embodied. So looking at that a bit, I mean, so you mentioned at the end of your talk the RoboNet database that you've been involved in, and maybe this is a bit crude to say, but my impression is that if I look around at places like sort of vision and robotics groups, that at the moment everybody is building some kind of network world simulator, something to be able to have these bigger supplies of data and do more. But I mean, what's actually necessary for that to be useful? So like a couple of the questions I don't actually know much about RoboNet, but a couple of questions you could wonder is, how much do we need more of the rich multisensory experience of our embodied biological agents? Can you let someone asked in the questions, can you grasp the concept of water without feeling water? And then secondly, I mean, for little kids learning, clearly, manipulating stuff themselves is super, super important, all the evidence suggests. And that leads to this the famous idea of the scientist in the crib, right? That if you can manipulate, you can do your own experiments and learn about things like causality. So, is it actually useful collecting up a huge amount of footage of robots doing things? Is it sufficient to have a virtual world? What do we actually need?
I think that from the data standpoint, we don't know. And I think that we are kind of simultaneously developing data sets and algorithms and figuring out how the algorithms can learn from these large data sets, what sort of data sets they thrive from, and so forth. I think it's kind of a developing question, an open question, and so forth. With regard to your question of the importance of being embodied, it seems like this is probably going to be pretty important, at least from my standpoint. I think that one of the ways that we may be able to get beyond the train test, like assuming that the train test distribution have to be the same in machine learning, is by being able to probe your environment and be able to run experiments and seeing what outcomes that leads to. And it seems like basically when you're actually are making the assumption that you have an embodied agent in the world, there are various assumptions like experimentation and so forth that may allow you to generalize beyond your training distribution. And one very natural thing that you could do there is just you can control your data distribution essentially, and so you can structure your data distribution in a way that more reflects the kinds of things that you might see going forward. This also connects to continual learning, like we were talking about before, where you're just continuously collecting new data and learning from it.
Yeah,
I mean, I think there's a big part of this that has to do with what is the policy of the agent gathering the data. When we talk about babies like playing with objects, like you mentioned, Chris, like, it's a very non-random set of things that they do when they're interacting with the objects to learn how they're going to operate. And then actually, I think that in the context of the kind of imitation learning that Matt was talking about, it's even more important. Like, is how do you get a baby to actually know that what it should pay attention to in the world is the interesting stuff that its parents are doing, right? I mean, that's like a very non-trivial policy for the baby to intrinsically know how to execute, is how to separate all the stuff that's irrelevant from the stuff that isn't, given the utter infinitude of possible things that it could actually do and ways that it can allocate its attention, essentially. And so, I think we shouldn't forget, it's not just about embodying them in the environment, that there's a real policy and like intrinsic motivation data gathering problem there. And, all three of us talked about various approaches to that we've been working on in different ways, but that especially becomes important, I think, in the multi-agent social context. What is the intrinsic motivation underlying social interaction?
Yeah, actually, this connects. So I completely agree. I think it's a profound observation, of course, that babies actively decide their data distribution in interesting ways that may be guided by innate evolution initially. But related to this, actually, Bill Newsom asked this question specifically to you, Dan. I think you had mentioned at some point that the agent gets bored, and Bill wanted to ask you, what does it mean when you say the agent gets bored? What is boredom in a digital agent? And also, you didn't get a chance to get into this, but how does curiosity, this is kind of a second follow-up question, how does curiosity aid social interactions among multiple agents? But let's start with the boredom one.
Yeah, boredom just means that the distribution of actions that the agent decides to take is shifting. So, essentially what you see in those kinds of systems is a kind of stage-like progression where the data distribution shifts fairly quickly and stays with something for a while. And boredom is essentially the time when that shift occurs, because, for example, its loss has gotten too low. If your loss function is something like, I'm going to do things that are going to challenge me, then when you're doing things that have become, when you're first doing those things, they're challenging and they're quote interesting, you'll keep doing them. But at some point, if the system is working right, and it's hard to get them to work right, but if they do work right, then you get to the point where, you've essentially juiced the thing that you're doing, and you need to look for something that's going to take you to the next step. And that's where I put quotes around boredom, because this is a digital agent and who knows what anything really is. But it's sort of intuitively, in a vague sense, the idea that you want to shift your actions to get to something that's going to teach yourself something more, right? So those are the moments when I think it looks bored, basically. Although of course you have to discount that for the fact that we very naturally want to anthropomorphize the systems we build. At least that's a challenge, and all of us have to prevent.
Next time he tells me he's bored, I'll tell him just shift the distribution of your inputs. We'll see how that goes. He's 5 years old. We'll see.
Does Matt have a final thought? He wants to contribute to this.
I agree with almost everything that's been said. I'm wrestling a lot with the embodiment question right now. That's something that DeepMind has kind of operated on, that has had that as the default, maybe because vision was one of the first things that kind of worked in deep learning. But the recent progress in language modeling has a lot of us discussing, well, how far could you get just with symbolic data, and what more do you get from embodied action? And I think the answer to that is simply language refers to a world, and a world is a different observation and action space. And if you want to gain knowledge through the experimental method and actually acquire new knowledge through that channel, you have to have access to that world to which language is referring. But I think we're in a spot now where a lot of people are asking, well, how much knowledge can we nonetheless inject into even our embodied agents, given language? Gosh knows, humans have a lot of knowledge injected through that channel. So I think it's an interesting new discussion.
Yeah.
Sounds good. So we're at our break points. I just wanted to thank all our speakers for fantastic talks, a scintillating discussion. We're going to take a half-hour break, and we're going to restart on another Zoom. We're going to restart the live stream at 12 p.m. Pacific time, and we'll have another set of speakers and 2 panel discussions after that. Thanks, everyone.
Thank you.
everyone. Welcome back to the Stanford HAI Fall Conference on Triangulating Intelligence, Melding Neuroscience, Psychology, and AI. We had great talks and discussion this morning and are ready for our next lineup of super speakers for the afternoon. I'd like to remind everyone that you can submit questions for any of our speakers on the event page on our website down that right column where there's both opportunities for questions and for just chat comments. And on Twitter, you can use the hashtag #NeuroHAI, NEUROHAI. But without further ado, I'd now like to introduce our first speaker, Sanjeev Arora, Professor of Computer Science at Princeton University. Welcome, Sanjeev. Please unmute yourself and turn your video on, and we're really looking forward to your presentation.
Good afternoon. Today's talk is titled How to Allow Deep Learning on Your Data Without Revealing Your Data. But after some consultation with the organizers, they thought it would be useful to add some thoughts on mathematical understanding of deep learning, which will be the first few minutes of the talk. So this introductory section concerns the ongoing effort towards mathematical understanding of deep learning. And given the complexities of deep learning, you may well wonder if that is the oxymoron of the day. So in the next few slides, I'll try to give you a very brief taste of this growing area and give you 3 reasons or motivations I think it will be essential in the long run. And then in the rest of the talk, I will talk about how to do deep learning on your data without revealing your data. Just to lay all my cards at the table, I believe that at its best, theory should surprise and challenge practitioners instead of just formalizing their entrenched intuitions using some epsilons and deltas. So without further ado, the 3 motivations why we need mathematical understanding of deep learning. Motivation 1, to get very far in AI using deep learning, we need better mathematical understanding of properties of the trained nets. And the main reason we lack such understanding right now is the current black box approach or viewpoint of deep learning. All you need to do deep learning is to settle upon an architecture, define a loss function, and start doing gradient descent on this loss. But we lack any significant insight into what happens during this gradient descent, which in turn means that we lack any insight into the final solution that this gradient descent produces, namely the trained net. In other words, this trained net is a black box to us, and this whole process is a black box to us. Now, if you began to understand something about what gradient descent is doing, you might start getting some of the good stuff that we want, like explainability and interpretability of the net's behavior, and some properties that we can't just verify using held out data, such as robustness to distribution shift or adversarial perturbations, something that some people call strong generalization beyond the training data. And this theory is now starting up. To explain further how the black box view of deep learning is holding us back, let me give you an example. You have all seen language models like GPT-3, which have caused a revolution in natural language processing in recent years. The training loss of these consists of performing well on what you can think of as fill-in-the-blank tasks. The model is given a partial sentence like, Rob went to the cafe and ordered a blank. And it is trained to produce a distribution on missing words that predicts the next word well, such as this distribution, like probability of latte is 15%, probability of Danish is 10%, and probability of dog is 0.01%, which is very unlikely. Okay. So I'm assuming you've seen language models before, and the phenomenon I'm interested in is the following: that the same model, which is producing these distributions of next words, is also along the way giving us very powerful semantic representations of text. which are helpful for all kinds of other NLP tasks and revolutionized NLP in recent years. So specifically, when you input this piece of text into the model, its internal workings involve a vector representation of the text. And this vector representation is extremely useful as a representation of the text in dozens of downstream tasks. Now, to a practitioner, this doesn't seem very surprising because, of course, the language model is pretty darn good. And so it makes sense that it must have developed good understanding of the text. But at a mathematical level, this is not clear at all. And for example, one could wonder, why is the representation so broadly useful? Is it something to do with something special about language modeling, this predicting the next word? Or mathematically, it arises from some property of current deep architectures being used? And as you can imagine, one can't make a whole lot of progress on such basic questions, given that deep learning is a black box. So now people are starting to open this black box. And in a recent paper with two students, Nikun Sonshi and Sadika Maladi, which is now in archive, we give a mathematical exploration for why such representations from such models are useful in downstream tasks. And turns out the answer is that both of those are important. The fact that it's language modeling and that it's also a property of gradient descent and local optimality in there. Okay, so that was the first motivation for why we need mathematical understanding of deep learning. The second motivation for mathematical understanding is that, surprisingly enough, deep learning doesn't fit traditional optimization theory, meaning the stuff that we've been taught in courses for decades. Now, this basic optimization theory is something that both theorists and practitioners know, but it turns out that it can be quite misleading when you drill deep down into deep learning. And let me illustrate today by showing that something even as simple as learning rates in optimization behave very differently in today's deep learning than what we learned in optimization classes. So learning rate is this parameter eta in gradient descent. How far do you step in the direction of negative gradient? That's the learning rate or the step size. And the usual classes have taught us that you should start with high learning rate and slowly make it lower. But in a new paper last year, we show that actually this traditional understanding is, it does not fit today's state-of-the-art deep net models at all. And by state-of-the-art, I mean those that use some form of normalization at layers. So what this paper with grad student Jeon Lee showed was that these state-of-the-art nets can be trained using exponentially increasing learning rate. In other words, at every iteration of gradient descent, you multiply learning rate by 1 plus c for some constant c bigger than 0. Now, all of you know what exponential increase means. So this indeed means, because it's being done at every iteration, that very soon the learning rate is in the millions or trillions. It's gigantic. You're making gigantic steps, but it still works. And the reason we came up with this crazy idea was that we had a mathematical proof that it would work. We were exploring the mathematics of learning rates, and that's what we came up with. We had a proof that existing training can be done with exponential learning rates, and therefore the experiment was natural, and it works. So after this surprise, we continued to explore learning rates and role of learning rates. And in this new paper that we just put on archive, we tackle another widely held belief, which is that, as you see in this figure, the learning rate, the belief is that learning rate needs to start out high and then it slowly should be decayed, and that this is actually not just needed for optimization, but also for good generalization. And the story vaguely is that the loss landscape is non-convex, it has hills and valleys, and this large initial learning rate leads to some kind of a Langevin diffusion process, which is fairly stochastic, and it helps explore this loss landscape, the hills and valleys, and finds a broad valley or minimum. So that's roughly the theory. And In this paper, we show that this intuition is actually also incorrect for state-of-the-art nets. So you don't need large initial learning. So, okay, so in the previous paper, we show exponentially large learning rates are fine too. And now we're showing that actually you don't need large initial learning rate or large learning rate at all. And it still trains to good accuracy. And we don't find any evidence of this diffusion theory. And in fact, we show that going forward, what we should look at is function spaces. And we start developing a theory for that. Okay, and now the third motivation for why we need a mathematical understanding of deep learning. And this is maybe a little bit speculative. And I'm suggesting here that current learning paradigms may not be sufficient to lead to flexible interactive agents. Okay, so basically the issue is that when you drill deep down, most, if not all machine learning today is relying on the idea that, that you're learning on a fixed distribution of data. Training and test data points are assumed to be independent samples from the same distribution. So we all know that if the distribution then shifts at deployment time, then the learner is not guaranteed to work. Now, a flexible agent has to be able to do all sorts of different tasks, meaning perform well on all sorts of distributions, for which people have invented various paradigms, which I would simplistically describe as distributions on distributions. And you'll see that a lot, I think, in Josh Tenenbaum's talk. So for example, in meta learning, you explicitly think about your learning on a distribution of tasks. In Bayesian frameworks, you're assuming that the parameters of the task distributions are drawn from a prior distribution. So in other words, the paradigm of machine learning needs inputs to come from a fixed distribution, which is the top turtle in this picture. And this top turtle may itself be resting on another turtle, which is another distribution, which in turn may possibly rest on another turtle, which is a distribution, etc. But at the bottom turtle that's holding this all up is some base distribution where you're taking independent samples from a fixed distribution. So that's the dominant paradigm. I'm not saying everybody in the field is doing this. And it's possible that this can get us all the way to flexible interactive agents, but maybe not. And that's what I'm suggesting today. It's quite possible there is a middle position in the debate that maybe this paradigm doesn't capture intelligence when training data is limited, as it is for humans, but maybe it does it for machines since they can learn from orders of magnitude more data. So I'm open about this, but I'm just suggesting that maybe we need a new paradigm. Okay, so that was the initial part of the talk, why we need mathematical understanding of deep learning. And now I will get to the main part of the talk, which is how to allow deep learning on your data without revealing your data. And this is joint work with this team, grad student Yangsibo Huang, colleague Danqi Chen, postdoc Zhao Sang, colleague Kai Li. And the first paper appeared at ICML, and all the authors except Danqi. And the second paper will be appearing in ENLP findings, and it includes Danqi. Okay, and I hope that this work illustrates what I said at the beginning of the talk, that where I hope theory can be useful is by being inspiring and thought-provoking, coming up with radically new solutions, rather than merely solidifying existing practice. Okay, so today's broader topic is artificial intelligence. And it is clear that in the near future, it's not due to androids or robots of movies, but the devices that surround us. And these devices that surround us are based upon a Faustian bargain, if you will, that we have to hand over our data to a handful of dominant companies, and then we'll enjoy a world customized for you. Now, this raises a fundamental question about privacy, which was in the title, which sounds oxymoronic. How can deep learning be done on my data without revealing my data? But that is indeed the question we'll talk about, that there's all these forms of data that we are interested in that's going to be input into the deep net, and the training here, which is this little hardworking blue man, is doing all this stuff, gradient and backprop through the deep net. and we want deep learning to be done on our data without making us reveal the data. And some of the candidate applications you can think of are, for example, hospitals want to train deep nets on their pooled patient data, lots of hospitals, and privacy laws prevent them from actually pooling the patient data. So they want to somehow train the deep net without revealing the data. Or say you want to customize Gboard, the Google keyboard, for user groups, and the user groups have their own chats, private chats, and you want to customize Gboard on that without revealing the chats to Google. Universities may want to customize the Slack forums using private conversations, etc. And of course, you may want to hold on to your data instead of giving it to Alexa and Google and so on, and Amazon, etc. Okay. So there's a lot of prior research, and federated learning is a conceptual framework to think about it. For example, imagine that hospitals wish to train this deep net collectively using their data. And in federated learning, the deep net is trained at a central server. Hospitals hold on to their data and actively participate in the training. Everybody maintains a copy of the deep net as it's being trained. And using their local data and backpropagation, they compute gradient of the loss and send only the gradient updates to the server. The server aggregates updates from all the hospitals, aggregates the gradients from all the hospitals, and sends back the new parameters of the net. And the training involves this back and forth between the hospitals and the server. So it's just a framework for thinking about distributed deep learning. Now, it turns out, even though the hospitals may appear to be holding on to their data in this framework, information leakage is occurring from the gradients that they are transmitting about using their data. It was shown by Zhu et al. Last year that any eavesdropper on the protocol can use an efficient gradient matching attack to reconstruct the hospital's data from their gradients. So in other words, we need some explicit method in this picture to protect the data. There are two standard solutions existing before. The first is differential privacy, which adds carefully chosen noise to the gradients. But its shortcomings are that the accuracy of the trained net plummets by a lot, 20% on CFAR10, and the accuracy drop is actually catastrophic on ImageNet, more complicated data sets. The second shortcoming is that it gives a very restricted notion of privacy. It's concerned with privacy loss due to the release of the trained model, that is proper use. And the reason it has to do with the fact that differential privacy was invented in a different setting, namely privacy of databases. So differential privacy gives no guarantees about side computations using the shared gradients, which is what's going on in this gradient matching attack. So the second solution that has existed for several decades is cryptographic. Just as cryptography can protect our online transactions, it can also protect every arithmetic operation in any computation, including the computations done in deep learning. But the shortcoming is that it does this encryption operation by operation, and deep learning just has billions or trillions of operations, and it's not very efficient, although there's been some progress in making it somewhat more efficient. But also the other shortcoming is that it needs finite field arithmetic, which doesn't work very well with the real value arithmetic in deep learning and requires special setups such as public key infrastructure. So it's currently not a very practical solution. So now we come to the new idea, InstaHide. It gives a way to encrypt images. So you take normal training images and test images, and you can encrypt them. Now you can input it into the same frameworks that you have, the same code, PyTorch, whatever, Keras, and it can be used in the same training, same little blue guy. And you train and test on encrypted images. And doing this training on these encrypted images has very minor effect on final accuracy, as we'll see, and very little effect on efficiency, unlike cryptography. So it's better than differential privacy in that it has minor effect on accuracy, and much better than cryptography or existing cryptography because there is almost no effect on efficiency. And we think it reveals nothing about data, but it's a new form of encryption And violating privacy here requires solving some computationally difficult problem. This is analogous to existing cryptography, but it's a new form of encryption. Okay, so I'll give you some idea of what's inside this new encryption. It's inspired by a technique called mix-up. This is a form of data augmentation introduced by Zhang et al. A couple of years ago. And we theorists have been trying to understand what's going on with mix-up because it's very counterintuitive. Let me describe what it does. Mix-up, well, the training is on images, but mix-up interprets them as vectors. And the labels can also be treated as vectors. Now, with vectors, you can take linear combinations, and that's called mix-up. So you take 0.6 times first image and 0.4 times another training image, and you get this composite image, pixel-wise addition. So you get this composite image. And mix-up involves training on these composite images. Now, the labels themselves are vectors. So this is standard in deep learning that the label is a one hot vector. It has zeros everywhere except one in the location corresponding to the label. In the first case, bird. In the second case, airplane. So the label of the mixed up image is 0.6 bird and 0.4 airplane. So you train on these mixed up images with these mixed up labels. And surprisingly enough, this improves training. The deep net is never trained on normal images. It's only trained on the mixed up images, and this improves training. And in theory, we've been trying to understand this because it's kind of bizarre that the nets which are so nonlinear are being trained to behave linearly. Anyway, I won't say much more about why mix-up works, but we're just going to use it at InstaHigh. So one idea is that we'll do mix-up, but turns out is not enough, as we show in the paper, to ensure any kind of privacy. So what you also do is you mix it up with images from a big public data set, like ImageNet or Instagram images or whatever. And those also, so there are these coefficients, 0.6, 0.4, et cetera. These are chosen from some simple distribution. And you mix it all up. So in this case, 4 images. You get the composite image. And then on that composite image, you flip the pixel signs randomly. So pixels are, in this case, scaled so that they are, say, between -1 and 1. And you flip the sign randomly. And you get something like this. Remember that pixels are colored. And so when you flip the sign, you will really change the color a lot. So you basically get this grayish looking thing. And that's the encryption. Why the large public data set? Well, because it's off the shelf, no special setup assumptions. You can just take any images out there. And large because this gives more security. This is formally, it's because the encryption key is the choice of images. And there are lots of choices for this in the public data set. And that gives more security. So formally, the general InstaHigh strategy is that you're going to take mix-up of 2 private training images as you do in mix-up, and then k-2, k is some parameter like 6 or 4 or 8, and k-2 public images from this public data set, followed by pixel-wise random sign flip. And you're going to train on these mixed-up images, which look like blobs. So that's it. And you also do the same thing at inference time and do the inference that way. And the conjecture underlying the security of this is that this is based upon intuition from the classic subset sum problem, that extracting significant information about private images from the encryption, this blob, takes n to the k-2 time, where n is the size of the public data set. So since n is pretty large in, say, millions or billions, this is fairly secure, we think. And we put out a challenge data set, which you can try to attack. So here you can see that InstaHigh has fairly minor impact on accuracy. MNIST, CFAR10, CFAR100, and ImageNet are standard image data sets. And you see that compared to vanilla training, InstaHigh doesn't have a very dramatic effect on accuracy. Computers have differential privacy. And the running time is not too different from vanilla training. So this is just a first cut. Maybe it can be improved. Robustness to attacks. This scheme has been out for a few months and people have suggested various attacks. We came up with some attacks. We've run them. We can't seem to break them. But there, as I mentioned, there's a challenge data set out there which you can try your hands on. Now I'll talk briefly about text data sets and how to apply similar ideas to text. So there are several complications. Number one, as you all know, images can be thought of as real valued vectors, but text is a sequence of discrete symbols. The second big difference, which is why it took some thinking, and it's a separate paper to do it for text, is that the current paradigm for machine learning on text is by fine-tuning one of these language models that I mentioned earlier. So you take this language model like BERT, which is pre-trained on a large corpus, and now to make it do some classification task, you take the embeddings produced by this language model, and you're going to input it into the classifier net. And you're going to train this classifier net using the label. And so now gradients are flowing back and forth, and training is going on. But there's two types of training going on. The classifier net is being trained from scratch, and the top net, the language model, is being fine-tuned. So where do you stick the encryption in this picture? You stick it in between the language model and the classifier net. Okay, so just in picture, going back to the hospital picture. So the BERT, or the language model, is sitting with the hospitals, and they have the secret text. And the classifier net is at the central server. And the hospitals are going to send over the text embedding. And the classifier net is going to send back the gradients. And the insta-hide kind of ideas are going to be used, what we call text hide, to encrypt these text embeddings and the gradients that are being sent. Okay, it's similar to insta-hide, but the analysis of security is completely different because it's being stuck in a different place in this pipeline. And it also has minor impact on accuracy on the standard benchmarks, as you can see on this. So I'll conclude here. We've introduced these methods, insta-hide and text hide, which are substantive advances on important technological and societal problem, how to allow deep learning on my data without revealing my data, and their potential applications to medicine, Alexa, Gboard, Internet of Things, self-driving cars, etc. You could easily imagine a sort of new kind of company built around privacy, which provides this kind of service and acts as an in-between between us and, say, Google and Amazon. All these methods are a direct plugin with a few lines of code to existing frameworks on existing softwares like PyTorch and Keras and so on, with minor effect on accuracy and on efficiency. And the power of these ideas may cast new light on other open problems in security, privacy, and robustness. Hopefully this fresh take will stimulate other works. Thank you very much. And I'm looking forward to more theoretical understanding of deep learning.
Thank you very much, Sanjeev. That was a wonderful talk. Let me now welcome Yejin Choi, an associate professor at the University of Washington and a senior research manager at the Allen Institute for Artificial Intelligence. Yejin, please unmute yourself and start on your presentation.
All right. Thanks, everyone, for having me here and joining the talk today. So I'm excited to share our recent adventure in cracking common sense intelligence. So why common sense intelligence when today's deep neural networks seem to solve everything, starting from object recognition, machine translation, and so forth? Looks as if we've done solving AI and we can all go home, or not. So the state-of-the-art models are not very robust when presented with adversarial examples or out-of-domain distribution, not only for computer vision applications, but for NLP tasks as well. So it looks as if right now we know how to solve a data set without really solving the underlying task. So why is that the case? Well, there's a fundamental difference between how humans understand the world and how machines mimic that understanding only through pattern matching in data sets. So how do we bridge this gap? It's good to think about how human cognition really work and then see what sort of major things we are missing out of that. So for that discussion, this is system 1, system 2, reasoning comparisons became quite popular thanks to Thinking Fast and Slow due to Daniel Kahneman, the Nobel Prize winner. But the downside of it is that it seems there's a major misunderstanding going on in the field that perhaps we figured out how to do system 1 reasoning with the deep learning, and we only need to figure out how to do system 2 reasoning. I dare say that that's a major misunderstanding. So Kahneman's earlier work actually talked about 3 cognitive systems, perception in addition to system 1, system 2. And perception and intuition together are the sort of the processes that are fast, associative, and automatic, whereas system 2 is the one that's slow and effortful. And then what's really interesting is that both the system 1 and system 2 require conceptual representations and require reasoning about past, present, and future. And both are important with respect to language. We cannot really do things that far without language. So we can think about what sort of applications correspond to these different cognitive systems. So for reasoning 2, system 2, we often think about solving puzzles, writing programs, or solving logic theorems, but also reviewing or writing scientific papers will require system 2 reasoning as well. Well, hopefully reviewers do require involve system 2 reasoning when reviewing our papers. So what we seem to be doing really well right now seems to be more belonging to this perception level system, like object recognition, image segmentation, and speech recognition, and so forth. In between lies this is something really quite interesting, which is all about intuitive inferences, reasoning about preconditions, post-conditions, what happens before and after, people's motivations, intents, and their mental states. We do this almost subconsciously every waking minute. So this is going to be the focus of my talk. And to make my point a little bit clearer, let me show you this Roger Shepard's monsters in a tunnel. What do you see here? It's not just two monsters in a tunnel that you see. You see stories, like two monsters are running as opposed to standing still on one foot. And one is chasing another as opposed to copying his body movement, or the chaser is hostile and the chaser is afraid, even though two faces are actually identical. We almost hallucinate all these stories, explanations, and imagination about what's going on in that particular image. So two important observations here. A, none of these inferences have to be absolutely true. The inferences are stochastic in nature. Everything is divisible with additional context. More importantly, a lot of these intuitive inferences are sort of common sense inferences, and a great deal of that can be best described in natural language. And when you do that, we cannot just do it with just words or graphs of words, but we need the full scope of natural language. I already showed you 3 examples here that are in natural language, but let's look at another example. So this is a snapshot from the movie Titanic. And so what do you see here? Well, if we ask computer vision state-of-the-art systems, you might get some set of objects that are correctly identified. But when you look at this set of objects, you don't really see what's going on. It doesn't really capture the gist of what's going on in this image. So then we might think, well, let's add more interesting words and then even create some relations between the two. And certainly we are heading to more informative direction, but still, when you look at this graph, do you really see what was in the original image? So that's where the necessity for full sentence description comes in. But if we just do state-of-the-art image captioning again, it doesn't really explain why this person is doing what he's doing. Is he having fun and trying to sail statue in the water, or try to save himself from drowning? In addition, we almost see dynamic context of this image. For example, what might have happened seconds ago, or what might eventually happen down the road. So in order to address this sort of reasoning about the dynamic context of a still image, we presented the visual comet at ECCV this year. And the gist of it is that given an image, we want to be able to predict everything, all these octopus tentacles at once. And this is really the nature of human common sense inference. So we annotated this for not only one image, but for many others. And what it culminates is this connected graphs where you can see nose like screaming for help, and then see in what sort of visual situations you might imagine to hear that auditorial sound that you cannot actually hear from those still images. And then crashing the car. So this is what might look after crashing the car, and this is the moment perhaps before crashing a car. Without really looking at that particular moment of crashing the car, we can still reason about before and after. So we have this new resource, which includes 1.4 million common sense inferences described in natural language over 60,000 complex visual scenes. whenever we have this sort of data, we can now throw in our favorite neural network architecture. Not going to go into any of this detail. Let me just highlight one particular qualitative example what this sort of a resource might enable. So here, person one is putting a platter on the table at an outdoor restaurant. So this person one, if you look closely, is a serving person. And what's his intent? Well, he wants to serve other people, have them eat. And then afterwards, he probably will get back to the kitchen to get more food. So by having this sort of resource, we can train neural network to mimic the sort of intuitive reasoning or common sense reasoning that we do. And in doing so, it's really important to realize that we need the full scope of language, not just words or graphs of words. And if you buy that, now interesting corollary to that is that reasoning becomes generative task as opposed to discriminative task. What I mean by that is that, I mean, you could insist that I'm going to consider 1 million possible sentence descriptions of common sense inferences and then try to take it as a discriminative task, evaluate all 1 million choices and then rank which one comes the best. But that's certainly how we speak and reason in real life. We tend to almost generate token by token, word by word in real time. And I think this is really interesting aspects of the efficient reasoning capability that humans have that we need to investigate more in current AI. So we have prior precursor works to Visual Comet, so Atomic and Comet, that I'm going to briefly describe. So Atomic was presented that last year. It's an atlas of machine common sense for if-then reasoning. And so this is all about text, and it concentrates a little bit more on social common sense. So given a center event like X repels Y's attack in the middle, what we can infer is like causes or preconditions of that event. So perhaps she wanted to protect either other people or herself. And we don't know which is true for sure, but these are reasonable predictions about her intent compared to, you know, she wanted to sleep. That's completely unreasonable. We can also reason about effects or post conditions, such as a result, she might feel angry, she might want to file a police report, her heart might race, he might fall back, and then either he might want to run away or attack back. So there are different types of reasoning we can do for the dynamic state changes of the world. Now, some of these inferences can be about static attributes, like a personality being skilled, brave, and strong, that do not change minute by minute. So this is more static in nature. So we had a lot of this. And in order to build this graph, you might wonder, can we just extract this knowledge from a lot of web data, because there's a ton of that. The problem with that is that there's a reporting bias. So people do not say obvious things, and AI might just think that, well, humans mother each other 4 times more often than we exhale, because we don't really say how often we do exhale. And so it's not going to be accurate enough. We decided to fully crowdsource the knowledge graph in order to see what happens. Before I tell you that, though, super brief remarks on how this differs from what you might have heard about. So for example, there's a psych, something called the psych, and then there may be other favorite resources that you're aware of. So there are 2 fundamental key differences that I want to emphasize. A lot of the prior resources focused on knowledge of what, or taxonomic knowledge, that penguin is a bird, but that's really not enough. We need knowledge of how, knowledge of why, which corresponds to more of an inferential knowledge. We do a lot of reasoning almost by memorized pattern matching, even as a human, and why not? AI shouldn't do that. So another major difference is this logical form. So not all, but a lot of prior resources were in this form. And when you look at this, even as a scientist, does this make immediate sense that it aligns with your common sense understanding about how the world works? It certainly does not speak to me right away. And so in our resources, we are going fully natural language. And this really aligns with what Sanjeev said earlier about how natural language modeling can be very beneficial for downstream applications. And as it turns out, that's exactly the case with the common sense modeling as well. In any case, we focus on causes and effects in order to better address this concern against deep learning, even though we still like deep learning. So speaking of deep learning, here comes common sense transformers, which starts with this question. So Atomic had 900,000 if-then rules, common sense rules or rule of thumbs about how the world works. Is this really large enough? Or is it just in a tiny little corner in this universe of knowledge that you and I share? I speculate that the answer is likely to be the latter. So then what do? Do we try to somehow extract more knowledge and store all of them explicitly? And my speculation is that we don't need to. So it's better to build a model that could generalize for knowledge that's not even stored. For example, if I ask you whether butterflies are bigger than elephants are bigger than butterflies, you don't have to store the knowledge a priori. You can just think about butterflies and elephants and then answer it on the fly. So that's what we want to do. In doing so, we are going to benefit from transfer learning from language to knowledge by starting with pre-trained language models and then continue train that your favorite transformers on our atomic knowledge graph after serializing atomic knowledge graph into a long string of text. So now this transformer keeps reading common sense descriptions, and then here's an online demo you can play with. But it turns out this comet generalized much better to out-of-domain examples than we realized at the time of publication. So here's some fun examples. Sanya rides into the sunset on a motorcycle after solving AI. Atomic doesn't have anything about solving AI. Also, Atomic doesn't have these people's names, Sanya. It's all about person X and person Y. But Comet doesn't mind, and it predicts seemingly reasonable predictions like maybe she was having fun, and then she might be seen as someone daring, brave, adventurous, and so forth. How about Gary breaks the world record for most controversial tweet? So Atomic doesn't know anything about tweet or controversial tweet. Doesn't know which Gary we're talking about, but it produces fairly reasonable inferences, like maybe he wanted to be famous, maybe he wrote a book, wrote a blog post, and might be seen as very famous and influential. Maybe he feels very accomplished afterwards, celebrate, tell everyone about it. So Gary Marcus, as we know, has some concerns about deep learning. So this is one of my favorite tweet messages that he wrote about how GPT-2 is not up to his expectation. So he gave this prompt. What happens when you stick kindling and logs in a fireplace and then drop some matches is that you typically start A, and then GPT-2 goes on to say some nonsense. But that's because GPT-2 is really language model. So try Comet, which is knowledge model. And it turns out it just works right away. So Gary wanted to start a fire, which is pretty good. So let me now share closing remarks and open research questions. So if you search common sense, the word common sense from ACL anthologies, so this is a repository of all the NLP papers. Most of them are either from 80s or from the past few years. So there's this curious void, significant void in between. And indeed, when I was thinking about studying common sense several years ago, many people in the field advised me, don't do it. If I want to be taken seriously, don't do it. Don't even speak the word, as a matter of fact. But the more I think about it, the past failures are inconclusive when they were based on weak computing power, not much data, no crowdsourcing, not strong computational models, like no transformers available. And then their conceptualization and representation choices were not quite right. It was too much of a logic focused. Whenever you play with the logical forms, there's a serious loss of information. So language is the way to go. Fast forward, it seems that the new generation doesn't know these past failures, so they're much more optimistic. So we held this first common sense tutorial at ACL this year, which to our big surprise was second most popular. So it seems that there are a lot of interest for common sense, or growing interest for common sense, but what is the path forward really? This is sort of like almost a moonshot research goal. And well, I personally don't know how to get there quite precisely just yet, but one thing for sure is that brute force larger networks with the deeper layers will not do it. By analogy, you don't reach to the moon by making the tallest building in the world 1 inch taller at a time. So let's just step back and really think about the current paradigm of how neural network solves leaderboards. So oftentimes it's, you give this lots of exam problems and then let it learn. But the problem, there's a really big problem with that, multiple big problems with that. One is that the neural network inevitably latches on spurious biases in the data set and pretends that it knows how to solve it without actually learning the fundamental concepts correctly. But let's really ask this question. Are we even able to do this? Like imagine taking a deep learning class, professor doesn't teach anything, but just to provide you with a lot of multiple choice questions with the correct answers, and you're supposed to figure everything out on your own. I don't think even a human can do that. Alternatively, let's just say, the professor just provides a lot of deep learning code so that it's a little bit more like self-supervised learning now. I don't think humans can really learn efficiently that way either. So we like taking classes, reading textbooks, learning from tutorials very, very early on in our education. And I think we really need to think about how to teach machines, AI, with the declarative knowledge in a similar manner. The other question to think more about is this evaluation paradigm. Multiple choice is very attractive because it's easy to evaluate. But what you cannot, as Richard Feynman said, what I cannot create, I do not understand. And one way to interpret that is that, well, unless you can generate the answer, you cannot really prove that you really truly understand. And it's also like assuming that some oracle always provide us with like 4 magical choices to choose from, of which one of them is guaranteed to be true. That's just practically not very useful assumption to make. So I'm beginning to think more and more that we need somehow a way to teach machines some concepts in a more direct way. And what I just presented in this talk is one way to get there. It's not the most perfect way of getting there, but Atomic is basically a textbook of common sense knowledge in declarative form, which contrasts with the observed knowledge that's implicit in lots of raw text that language models are trained on. And in doing so, we use language as the symbolic representation of knowledge instead of logic, because logic can state just so much. A lot of examples that I was using today are deliberately chosen to demonstrate how hard it would be to translate all of them down to some consistent logical forms. We need to focus more on causal knowledge. And then neural networks are really great for generalization to compositional and previously unseen events. I've kind of felt like Atomic and Comet together are so 2019 though. So we have this 2020 version coming up, which I'm not going to go much into details other than to say that, well, it just has a lot more new relations, even including how money might be used not only for paying repairs, but also folding origami, which is kind of cute, or what sort of events can be hindered by. So you cannot get your car repaired if the cost is too much, or the car is totaled so that it's just not amenable to repairment. So keep going on this so that we have plenty more. But skipping over all this, let me just highlight one thing about these likely questions that people have in mind. Doesn't GPT-3 by any chance solve all this on its own? So let me give you a little bit of context to consider though. So our model Comet, now it's based on BART, is much smaller than GPT-3. So it's about 400 times smaller. And GPT-3 is so big so that it's not easy to download it and fine tune it to customize it for your own downstream anything. So with that in mind, GPT-3 is doing really great considering how it's unsupervised off the shelf with a few shot examples, but still A, there's a considerable gap. B, it's too large, and whenever you can use a smaller one, why not? But this is for some of the simpler common sense knowledge that we evaluated on. But what about morality? Because we do worry about AI safety. So I gave this prompts last night. Running a blender at 5 a.m. is rude because you can wake up the entire neighborhood. You can only do it if you're making a thick smoothie and need to incorporate some ice. Wow, that sounds nice. I can do that if I do it. So it's a little bit confused, but not so bad. But how about it is okay to post the fake news if, and then GPT-3 says it's in the interest of the people. So I was thinking, I don't know about that. And then I tried once more, and then it says, ooh, it's even worse. So don't say that to me. So here the takeaway message, by the way, we have a new paper, Social Chemistry 1-on-1 for reasoning about social and moral norms to appear at EMNLP soon. And the paper might be on archive or will be archived within 24 hours or so. But basically, the idea is that we need to teach AI with descriptive ethics in the form of declarative knowledge. It's extremely unlikely that brute force large networks with some fancy schmancy self-supervised learning will be able to discover all this magically. Another really important point is that social moral norms cannot be really done without the full scope language incorporation. Compared to descriptive ethics, there's another more prescriptive direction where you might just focus on a few central dimensions of morality and then focus only on that. But if you do it that way, you cannot really translate that to natural language descriptions of a particular situation, like the way that I showed you here today. So we really do need to embrace language, which was sort of the recurring theme in this talk. Let me add just one more thing on top of this generative reasoning angle. It's not just me. It turns out that there are cognitive scientists who are talking about similar things. So The Enigma of Reason is one of my favorite books that I discovered the past year. And in it, it talks about how intuitive inferences are a great deal about extracting new information from the information already available, like a common sense inferences. But here, so reasoning, system 2 reasoning are used primarily not to guide oneself. Here, guide means making an important decision, but it's used in order to justify my decision in the eyes of other people or convince other people. So here, the position of these authors is that really reasoning serves the purpose of a communication. Language is really deeply involved in system 2 reasoning. And it's similar to how I might have made this intuitive decision already that I'm going to work on common sense, but how do I now justify my decision? Well, now I need to really involve system 2 reasoning. And in doing so, human reasoning is a mechanism of, or system 2 reasoning builds on top of intuitive inferences. It's not a separate thing. They're really integrated with each other. And conventional mathematical logic plays at best a marginal role, which also repeats in this Philip Johnson Large book on how we reason. Okay, so I'll stop here. I'm exactly at time. Thank you.
Okay, thank you very much, Yejin, for that thought-provoking talk. We'll see you soon for more discussion in the panel session. Our next speaker is Ord Oliver, MIT Director at the MIT IBM Watson AI Lab and co-director of the MIT Quest for Intelligence. Ord, you may now unmute yourself and share your presentation. Thank you.
Good afternoon, or good morning, everyone. Thank you very much for giving me the opportunity to speak today and attend the panel later. So while I was putting together this talk on incorporating insight from cognitive science into AI, I realized that since my freshman year at the university, which was over 3 decades ago, I have always combined knowledge from a different discipline. At the time, there was mathematics and philosophy, but particularly cognitive science, neuroscience, algorithm. And it started being difficult for me to separate those domains, where an idea comes from, as I really tend to think of a task or a solution really melting all those domains. And how to become a buy or thrilling role in different domains of science and technology is a training that I try to bring to my students. So I think it can give a richer and different view on the question of intelligence. So today I will present a few examples of the work we are doing in my lab at MIT, trying to use good ideas coming from cognitive science into AI model. So first I will describe some very concrete example of how we can leverage cognition for machine learning model. I will only speak about 2 or 3, but if you open a textbook in cognition or neuroscience, you will find hundreds of useful concepts. I still am one day to write a sort of integrative human AI cognition textbook, we'll see. And I will also share some neuroscience visualization about the human brain, which shows how the human brain is at work during seeing and hearing, which I think could really inspire the next generation of cognitive architecture. So one of the main projects we have been developing in my lab at the core of cognitive AI is how do we build a system that can recognize the visual world. And you can see here a few of the milestones from scene and activity recognition to common sense reasoning that actually are all inspired by a cognitive concept. I believe this milestone are needed step to bring cognitive capabilities of the model to the next stage and have the model being an interface that people can understand and relate to and communicate with. So which kind of cognitive concept did we concretely use in our study? So events in the world, just looking around, they unfold in time and they unfold at different temporal scale. So the question we ask is, well, if we want a model that is able to understand and recognize what's going on, what is a meaningful moment, a meaningful event that the model could learn and capitalize on? How long is a meaningful event? And then how long should the video be to train models that are going to be able to recognize what's going on? So we created the Moment in Time project at MIT that is led by Matthew Munford, which is a large-scale data set with 1 million snippet video of 3 seconds and over 2 million label currently. And this whole project started 3-4 years ago with a simple observation. 3 seconds. This is just enough time to size up a scene, to size up what's going on in an event. And 3 seconds is the short-term temporal window that holds meaningful action between people, object, phenomenon, things happening in the world. It's also a window of time evolved as humans face the physical and corporal constraint. It takes time to move, pick up an object, and so on. And in the experiment we did across neural network, 3 seconds seems to be enough to learn very robust video representation in order to transfer the representation learned in a model to of a task. So if you take a long random video and you cut at a long video and you cut at random segment of 3 seconds, you will have a very high probability that in that segment there is a meaningful event, and you show to people and people will say, oh yeah, this is what's going on. So in the Moment data set, all the cuts were actually originally selected at random, and then we labeled them in crowdsourcing experiments, which gave a lot of diversity to the data set. So if an action of an event is more than 3 seconds, well, 3 seconds is kind of enough to have the gist of it, so to train the model. And if an event is less than 3 seconds, then it's good because you have the event in context and you know a little bit of what's come before and after, which is going to be important for building model that will rely on causality at some point. So here are some example of what our model that were trained on those 3 second snippet for activity recognition are able to do when they are faced with new new video, and here's like the raw output of the model. In red are the zone of attention where our activity recognition model focus more in order to tell you what's going on and give you some of the words that you can see at the top left of the screen. So let's keep running this, boating, skiing. So you can access the work on our website or papers as well as download the dataset. So this was a very encouraging project, because if you have a backbone basic event recognition model that can give high accuracy and coarsely localize what's going on, it means that, well, there's this basic recognition of the activity that is checked. And our idea was, well, when this ability is developed, what can we do with it? What can we build on? And we actually build models that can perform abstraction by linking events that look very different, like the one you saw here, the event of cutting the tree or separating the papers. They both belong to the class abstraction. And what I'm going to show you, we were able to reach that level of abstraction in our model because we had a very strong backbone. So I do think that when you think towards going to a high level goal, a cognitive AI system, it certainly worked for us and our team to think into milestone and see when we achieve a milestone, how it can be used for the next step. So I speak about abstraction, but what does it mean, abstraction, for an AI model? So let's play a game. So here is an example of a game, and we had our model and people playing the same game. Which action best match the reference set? So if you look at the top row, there are 3 videos of persons sleeping and resting or doing some yoga. And the game is, you're giving another set of video and you have to choose which video best match the original set, here represented under the blue. And when we gave this to people, most of people selected, as you may see watching this, the little cute dog sleeping. So now the example on the bottom left. So we have going upstairs or also climbing. So that is the match set. Game is given a set of other video here too, which one those fit the best. The same concept, abstract concept of the top one. And when we run this, most people selected the chimpanzee clinging. So now look on the right at those additional examples. So the match set here shows some, there's some actually water that is falling down. And the other one is as well a cartoon also falling down. And so which one of the 2 videos in the bottom does match the reference set? And if you look closely, it's actually, well, it's a tricky question, but most of people we gave the task to responded this one. So not a trivial task, but a game that now model and people can play. So let's now have another game, which is very related. So now you have a set of video, 3, 4, 5. So let me play them. This one, this one, this one. And the game is which video or event does not fit the 2 other. So which one is the other one? So think a moment, look at those. And in our task, most people have selected this one as being the outlier. So let's see another example. So always water. Again, same task. Which event could be the odd one? Actually also a difficult one. Well, given this task, the higher responses that we got from people was to select this one as the odd one. So in all the example I've shown you here, we had people and our new model of abstraction playing the same game. And they choose the same image most of the time, about 75% of the cases. So what did we do to make the model playing pretty well at those two games? Well, we taught the model the notion of abstraction that we execute operationalize here as what is the common concept that connect a set of video, a set of 2, 3, or 4 video. So here is an example. What those 3 videos have in common? Think a moment. What can connect them at a higher concept, an abstraction level, a description of the activity? So people will easily understand that those actually depict the same some sort of competing. Current machine learning model struggle at inferring this abstract connection. Although we are seeing very fast progress almost every week or month. There's some nice breakthrough out there. So in the framework that we propose, this is a project that is led by Alex Andonian and Camillo Fosco at MIT that was just presented at ECCV in August. Our abstraction framework combined the visual features with natural language supervision to generate a richer representation of the action video have in common. And think about how you teach young kids about animals or things going on or concept. You actually speak to him or her all the time. So it does make sense that in order to build up representation that are going more further away, the exact depiction of the object and the scene and the things into a video, you speak to the persons. You had that language representation. And this is what we did in this work. So for instance, the model has learned that exercising can take many forms: running, lifting, and boxing. And its feature representation mixed with language can be used then to play those games or those 2 new tasks, which is find the event that fits, so set completion, or find the one that doesn't fit. So what I'm showing here is actually still a toy model. We actually produced 2 models, one based on moment in time data set and one based on kinetics for generalization. And so there are multiple dimensions that you could imagine people focusing on when they have to play those games to find what fits or doesn't fit. In this particular paper, we focus on activity, and we also told people when they were playing the game to focus really on the activity. So here actually very interesting sort of the other output is basically what was the type of information that the model of abstraction were using when it was taking the decision. So here are a few examples of just the raw abstraction output of the model, when we can also ask the model, well, if we give you those 2 videos or those 3 or 4 videos, what is the abstraction that is common to those? And here it shows some of the responses of the model, and some are kind of, they make a lot of sense, and some are really interesting, how you could make link with things that we might have not make links to. And the output also give you the sort of focus of attention, which is where the model can focus to produce a response regarding the type of activity. And what I think is very interesting in model that can take decision at this more abstraction level, and we start seeing quite a bit in the literature, is that it's a framework in order to perform a few short learning or even 0 short learning, which is generalizing to new classes with few or no example, as well as getting a little closer to human-like abstraction abilities, which has been a new experience into conceptual categories. So I just gave you example of a couple of projects and two cognitive principles. There are 100 out there, and it will be a really fabulous journey if all the cognitive, the computer scientists out there were starting reading the textbook in neuroscience and cognition, because there's a lot of gold literally hidden in every page. And there is more gold that you can find when you start working on the neuroscience of the human brain. So let's now look at what we could learn from the human brain that could start inspiring tomorrow's model that are more complex, which are architecture of cognition, because they could start taking into account a lot of the perception and thoughts that we do when we recognize or when we move in the world and so on. So one of the most important aspects of the brain, besides being a deep learning network, it's a dynamic deep learning network. The information that comes to us in the world and it's processed into the brain is processed in time. So temporal sequences, things that happen or that are processed in parallel or one after the other, is a very important element of human intelligence. And we do not know very well how to deal with timing and the right sequence of processing an artificial neural network in order to reach some more cognitive level AI and tasks that unfold in time. And if we want to understand human intelligence and see how human and artificial system could interact better, I believe we need to really have a good understanding of how things unfold in perception and cognition in the human brain. So capturing the temporal sequence of brain perception is not easy. There's a few methods out there, but this is another line of research in my group at MIT. And in 1 or 2 decades, this slide will really look like the cavern age of cognitive neuroscience. But these are the tools available to a lot of the neuroscientists today. So in our experiment, we have people doing the same exact task and experiment twice in 2 machines. One in MEG, and then they go in fMRI or the other way around. So MEG, or magnetoencephalography, is a functional neuroimaging technique for mapping brain activity by recording magnetic fields produced by the electrical currents that naturally occur in the brain when you look or hear at things. And it's using very sensitive magnetometers. fMRI, or functional magnetic resonance imaging, measure the brain activity by detecting the changing associated with blood flow. And these techniques relies on the fact that the cerebral blood flow and neuronal activation are related. So when an area of the brain is in use, the blood flow to that region also increases. So in this line of work initiated with Radosław Ciszy, we combine the data from those 2 very different sensors using different machine learning technique. And now let me show you an example of the brain responses to images shown for only half a second. So here is what half a second feels like. You see a lot, but it's kind of fast. All right, so here is our brain model, and you can see a timer. So when I start the movie, it's going to go fast. At some point, you're going to see some of the region lining up with different colors. And this is what we recorded. We put here together about 15 people, 15 brain to show you this. When we were showing a series of images for half a second each, as you saw in the little demo. All right, so we have this started, and we can start seeing some responses that start coming around, you see 70 milliseconds over here. And they start in the back of the brain. That's normal. We are showing images. There's no sound in the scanner. And it shows that, well, it's perfectly expected. Information goes into the occipital and we start seeing some responses. So that sort of study that was published initially in 2014, actually we did replicate a lot of the work, and since more have been replicated, recording things we absolutely know about visual processing. Oops. Which is that as we see and time unfold, information is envisioned and then it flows on both sides and on the temporal side of the brain, and then so on and so on. So I show you here a large visualization. But what the neuroscientists do is that they go and dig into the responses of every single brain region. It's like it's a map. We have a lot of modules, and we have a good idea of what each brain module does. So the one we will see, the one we will be used for imagination, and so on. It's really a journey to dive into the result, but it's a way to track down what's going on, and it could really inspire new architecture when we show all the type of activities. So in a similar vein, we also run those neuroscience experiments with sound, and we put people into the two scanner, and we had them listening to snippet of sound for half a second. So sound were represented voices, animal sound, objects like the telephone, toys, cars, and environmental sounds like wave, storm, and so on. So now let me show you what we observe. There's a lot to see here, and there's a few really nice new nuggets of information. So now it's sound. So the here are here. So normally all nice expected is start on the left and the right in the temporal lobe. So this means here that the information regarding the sound has been perceived. And then many other brain regions are going to start responding. And I'm going to stop here. And you see on the Y representation of the brain, you have in the front this region, this sort of isolated region. And this is actually a region that is more specific to process voices and animal sound. So when we go through those results, we see that within 150 milliseconds, there are many areas that are processing sound, and then those the area processing sound start really spreading to the area that are more visual area processing sound. So what this sort of visualization show you is that actually processing sound from the brain, when you compare to vision, is much more complex. There's a lot of regions that are being engaged either in a sequential or parallel manner, and we really are in the process of segmenting all this in order to have some more clear guidelines about how sounds are processed in the human brain for some future architecture of cognition. And I show you here vision and audition, but you can play the same game with tactile information or memory and so on. So I've shown you example of this incredible engine that's the human brain when it processes sensory input. But it's also important to characterize the bandwidth and the boundaries of human perception and cognition. Let me show you what I mean. So let's say you're in the street, you're just waiting a few seconds to cross the scene. You're not looking particularly anywhere. Maybe you haven't lost in your thoughts. Oh, well, did you notice anything? Let me show you. So here is basically what happened in front of your eyes. All those elements were changed literally in front of your eyes. And cognitive science has developed methods to quantify what we can see and not see, here and not here, to characterize our perceptual bandwidth, the boundaries and how flexible it is. And I think that many of those concepts of the cognitive bandwidth will be very informative to have systems that interact with people. Here is again the demo, if you just missed it. Yep, you did miss a lot. So to conclude, biological and artificial neural networks, they are like to me, the two faces of the same coin. Both biological and artificial can differ a lot in their architecture, their circuitry, their learning rules, their objective function or task, but they are both systems that use iterative optimization process to pursue an objective given a lot of data, and there are many common ground and principles between them. So I think that characterizing the bandwidth of human perception and cognition is very critical. And when you start digging into thinking about intelligent system, you're going to need to go and look at what's going on in those systems. And that may unravel a new field of investigation: cognitive, clinical, social, computational, experimental. It's the sort of synthetic neuroscientist that's going to really dig on and understand what's going on in the model. So as we see more interactive system, it's going to be important to study the implementation that works best for performing specific tasks, will help to explore the alternative that have not been taken by biology called system. And most importantly, I think that in all the system we are building, at the heart of this endeavor, we need to integrate decision about ethics, social responsibility, and the risk of AI into our pipeline. Thank you.
Thank you very much, Ord, for that wide scope from neurons to large-scale activity recognition. Now I'd like to welcome the final speaker of the session. Josh Tenenbaum is professor of Josh Tenenbaum is professor of computational cognitive science at MIT. Josh, you're already up, I see. So please start your presentation.
Okay, great. Thanks. It's a great honor to be here to talk to you about scaling AI the human way. I should say that, like many of the other speakers here, I've been working on this triangle and the bidirectional interactions between the science and the engineering of AI for my entire career. It's what I got excited about originally. It's what got me into the field. I'm going to tell you about the work that we're doing here at MIT in the Brain and Cognitive Science Department, as well as CSAIL, and in the Center for Brains, Minds, and Machines, and the Quest for Intelligence under MIT. But part of why I feel like it's such a great honor to be here is I really got my start in this field as a visiting undergraduate at Stanford in the summer between my second and third years as an undergraduate, where I worked with Roger Shepard and David Rummelhart, two people who've both been mentioned here before. And that's really where I got my basic idea about how to think about the mind, why it was so exciting and interesting, the connections between mind and brain, and how computation can enable those connections. Like many of the other speakers here, my work is fundamentally motivated by asking, why do we have all these great AI technologies, but no real AI? So why do we have machines that do things we used to think only humans could do, but nothing that has the flexible general purpose intelligence that you use to do each and every one of these things for yourself? What's the gap? Right. And again, like I think especially some of the discussions that came up in the early session and some of the things that Yejin was saying, especially to resonate with this. I think part of the gap is that we've made a lot of progress in AI technologies using techniques from machine learning, deep learning, and reinforcement learning that originally came from, just as Matt gave a beautiful history, right, from the psychology basically of animal learning. So studying very basic equations of like Pavlov's dogs, reinforcement learning in animals, or rats in a maze, right? So these, and I think we all agree that these can become powerful tools for finding associations and recognizing patterns when you scale them up in big data sets. But it's just one part of intelligence and maybe just one small step towards real understanding. So I'm interested in taking the next step, which comes more from a human-driven point of view, to say, well, in human intelligence, we don't just find patterns, but we build models. We are about understanding and explaining what we see. We are about imagining things that we could see maybe, but we haven't yet, maybe that nobody has. And then planning actions and solving problems that come up when you want to make those things real. And then learning as building new models of the world as we experience both our successes and our failures. So to reverse engineer this, to write down essentially the equations of model building, we're starting with young children because they're the original model builders. And again, like many of the other speakers, we're inspired by, could we build human-like AI that starts with just the basic kind of common sense that you see in these 1.5-year-old children? We're far from that. But imagine if we could do that, and imagine maybe longer term, if we could build intelligence that grows all the way into adult human intelligence, starting from the way babies start, right? This might not be the only route to human level AI, but many of us think it could be the best bet, because if you think about it, in our known universe, it's the only example we have of a system that reliably, robustly grows into human level intelligence starting from much less. And we know that even small steps towards this, could be big. Okay. So we're starting with the kind of most basic common sense that you can see in every 1.5-year-old, but no AI yet, like the intuitive physics that you see in this kid here, stacking up cups or playing with blocks. What is the knowledge that lets him, say, make a stack of 2 cups there and put it on top of a stack of 3 cups to make a stack of 5 cups? That is knowledge of objects, but also multi-object, multi-step plans. Or the intuitive psychology that you see here in the famous experiments of Felix Warneken and Michael Tomasello. The understanding that lets that 1.5-year-old kid in the back there literally read someone's mind, see this adult doing something that he's never seen before, but figure out what he's doing and why, and even how to help him. And you can see that here when the adult pauses and the kid does, well, exactly what you see him doing. Right? It's an incredibly sweet and cute moment, and it's also remarkably intelligent. Just think, if we could build robots with this kind of common sense and helpfulness around the house, it would be amazing. Now, we're far from this, and I think in order to engineer this kind of abilities in AI and to understand in engineering terms what's going on in these kids' heads, we have to face some hard problems of common sense. And here, it's going to resonate again with especially some of the things you just saw from Yejin. But this is partly my way of introducing what I mean by common sense. Okay. I also want to contrast our approach with the approach you saw, especially in the morning, from Matt, Dan, and Chelsea. I should say, I'm a big fan of all of them, and I'm grateful to have collaborated with all of them actually on papers, especially with Dan in some recent work that I'll mention here. Okay. But I think, in each of their talks, you saw fundamentally a sort of bottom-up, learning-driven approach, which really takes as the core driver of intelligence the tools of deep learning and reinforcement learning, and add some other stuff to it maybe, okay? But I think these hard problems of common sense just show us what some of the limitations of a purely bottom-up learning approach might be. Some of the ways in which, though we're making great progress there, we might be more, climbing trees or ladders and so on, rather than getting to the moon. Okay. Not that those aren't really interesting trees and ladders, and not that these techniques are also, as I believe, part of the bigger picture. I think very much they are. But think about these problems of generalization. Like as Chelsea put it, like if we want strong generalization, right? We might want to build systems that get broad training data so that they can generalize just as broadly. But the problems of generalization aren't just the strong generalization, as Chelsea was calling it, or Sanjeev was talking about, where we have, like, say, distribution shift, but what I might call super strong generalization. So generalizing to environments that are vastly different from training, with essentially no retraining or fine-tuning. Or generalizing to an infinite range of novel tasks with essentially no retraining or fine-tuning or examples of somebody doing the same task, because maybe you just invented the task yourself. So just to illustrate one of these strong problems super strong problems of generalization, think about this scene understanding task, understanding what's going on in a basketball game. So here's a typical image of a typical basketball game from the viewpoint that somebody who doesn't play basketball but might be watching from the side might see. Okay, and you see some images like this, or some scenes, and maybe some people tell you some things, and you understand what's going on. The objects, the balls, the players, the hoop, the goals, and so on. The teams, who's helping, who's trying to hinder or block others. Okay, but whatever understanding you get about these events from this viewpoint generalizes to this viewpoint, which, until you saw a camera put at the rim of a basketball hoop like this, you never would have seen this activity here, but you have no problem generalizing to this, even though it's very far from the distribution. But this is actually still an easy problem of generalization, because think about all these other kinds of ways of rendering the scene, for example, in a video game. So here's a sports video game where it's fairly realistic graphics, but different at all sorts of low-level pixel statistics, as well as some not so low-level things like that circular hoop you see on the player being controlled, which is just something that comes up in a video game, but you have no trouble sort of factoring that out. Or take this video game here with less realistic graphics and much less realistic physics. You see somebody making a slam dunk going much higher than any human basketball player ever jumped, but you have in some sense the physics of all of your experience. Or think about kinds of things which again are much less different or much more different at the pixel level. And this again resonates to me with what Matt was talking about, where in some sense common sense isn't just about pixels. So take Minecraft, where you can see a basketball game, but the pixels are so different, and indeed even the objects are quite different in their composition, but it's the same thing going on. Or take this really old classic Atari game of one-on-one basketball. So different, right? And yet you have no trouble understanding it. Or lastly, the really classic Atari game. This is the Atari 2600 basketball, where it's ridiculous graphics by today's standard, and yet you still have no trouble, and kids can play it just as well. And the first time you see it, you understand exactly what's going on. Basketball hoops, players, ball, shooting. In some sense, these are all the same thing, the same activities, events, objects, agents, places. So I want to understand what is the common sense that allows me to perceive and make sense of this. Okay. Now, I think this poses a severe challenge to a data-driven learning approach. And this is a challenge that has been highlighted since the beginning of the field, right? I mean, Turing, in his first paper, arguably the first paper on AI, the paper that introduced the Turing test, and which also famously introduced the idea of building a machine that grows into intelligence like a child, or that's taught like a child, emphasized this idea of basically starting with as little as you can build in. Little mechanism, little knowledge, lots of blank sheets. But we've learned now, and this is at least in the work that I do, a lot of the inspiration comes from developmental psychologists and developmental cognitive neuroscientists, like the people you see here: Liz Spelke, Rebecca Sachs, Alison Gopnik, Laura Schultz, Hyo Guan, who was a student of Laura's, also worked with me at MIT and is now recently tenured faculty member here at Stanford and one of the participants in the High Center. And if you look at them and many others in the field, they've shown us all these ways that the starting state and the learning procedures are much more sophisticated in their structure, their content, their mechanism than we might have thought. There are basic core knowledge systems, as Spelke has shown, for objects, agents, and places. Rebecca and others have shown how the brain systems that underlie these are largely taking the same shape, even in very young babies just a few months old. Or Alison, Laura, Hyo have shown how the learning algorithms, we heard about the child as scientist in the morning, right? And I think some of the work that Dan told you about is starting to take steps towards this. But the ways children build models, do experiments, form theories, get into an experiment theory building loop like a scientist, go way beyond what we've been able to do so far in sort of traditional machine learning driven AI. So I want to talk about the ideas, the formalisms that we've been trying to develop to capture these ideas, like what we call the game engine in the head, or the child as coder, or the child as hacker. Okay. Now we do this in our work in the context of several technical tools. One is the idea of probabilistic programs and probabilistic programming languages. These are new AI programming languages which integrate the best ideas of multiple eras of the field. Surya gave a really nice history of the field, which talked about Bayesian approaches as well as neural networks. But I think, and both of those are really important in the kind of work that we do. Bayesian inference for reasoning about unobserved causes from sparse, uncertain data in hierarchical probabilistic models. And Sanjeev formulated that very nicely as well as, and also how that relates to the neural network and pattern recognition function approximation toolkit. These are complementary and work nicely together. But I think what also gets a little bit of short shrift is the original and maybe best idea in AI, which is symbolic languages for abstract knowledge representation and reasoning. I agree with Yejin about almost everything, I think, except maybe I think that there's more value in actually having underlying knowledge representations that use symbolic languages like programming languages for abstract knowledge representation and reasoning. And I think by combining symbols, probabilities, and neurons effectively, or differentiable programs, then that's a very powerful toolkit together. Another idea is this slogan the slogan I use for it is the game engine in the head. The idea that the very fast approximate simulation programs for graphics, physics, and planning that are at the heart of modern game engines, and that have been increasingly used to train certain AI systems, especially in the sim to real paradigm, I think can be extremely powerful if you think about those as prototypes or examples of the kind of cognitive architecture, that the kind of common sense core knowledge systems that would be built into our heads, into babies' heads by evolution. So the difference is, this isn't about a sim to real approach. It's about a child who sees an object, sees some objects, thinks about a plan, thinks about a goal, like maybe I can roll this ball and knock those things over, and actually has the simulator in their head, which they use to perceive, think about, predict and make their plans, right? So that's why it's not the game engine as a training ground. The real world is the training ground, but the game engine is in your head. It's the basis of the models. So over the last 10 years or so, we've used these tools to capture a number of aspects of basic common sense in quantitative terms. So with Pete Battaglia and Jess Hamrick, who are now part of Matt's team, and core members of Matt's team at DeepMind, and continuing in all sorts of interesting ways that are related to this, we've used these tools to build models of intuitive physics, for example, in blocks world scenarios, to answer questions like, will the stack of blocks fall? And to capture here quantitatively people's judgments about how stable a stack of blocks are. But the same tools can answer many different questions without any retraining or really any training at all. Okay. In this system so far, there was no learning. There's just probabilistic inference running a few approximate simulations in a game-style physics engine. But that can let you answer questions like, which way will the blocks fall? How far will they fall? What will happen? How it will be different if one material is much heavier than another? Working backwards, if something surprisingly isn't falling, can you infer which is the heavier material? Or to do interesting kinds of counterfactual reasoning, right? In some sense, this connects to some of the themes that were raised when we're talking about Judea Pearl's work. But now the causal model isn't a graph, it's a physics engine program, which is necessary to reason about flexible, open-ended world of many objects and complex interactions. There's no single graph that describes how blocks interact. But if I want to answer a question like, what will happen if I knock one of these tables hard enough to knock some of the blocks onto the floor, will it be more red blocks or yellow blocks? Well, across these scenarios and an infinite range of others, we can capture people's quantitative graded intuitions of more or less red or yellow by the following sort of mechanism. We infer a 3D scene description, an object-based scene description, and run a simulation. That's a simulation of a small bump. Here's a simulation of a big bump. And we just have to run a few simulations, one or a few simulations. You don't have to run a high precision simulation, and you only have to run it for a few time steps to be able to capture people's intuitions on the grain of kind of quantitative precision and probabilistic approximation that you see in the behavioral data. In some particularly recent work, Kelsey Allen and Kevin Smith in our group, and I should say Kelsey is also about to join Matt's group under Jess Hamrick at DeepMind in a few months, just finishing up her PhD. And a core part of that is this virtual tools game, which you can see here. I'm just illustrating a few people playing this game, where the idea is you flexibly have a goal, which is to get the red object into the green region, and you try to achieve that goal flexibly by picking up an object and dropping it somewhere into the scene. And here you can see a few people playing different versions of this game. Okay, you don't have to learn to play this game. You use the physics knowledge that you have of the world, and then you can play any one of these levels, not perfectly, but across many levels. These are just a few of the ones we've studied. And here are some of the within level learning curves. People typically take 2, 3, 4, maybe 5, 6, or 7 trials. It's few shot, if you like, reinforcement learning, but people can learn to solve one of these levels on average in just a few trials, and a simulation-based few-shot model-based reinforcement learner using the approximate physics engine that we've talked about can capture pretty well what people do here. The same kind of models can capture and provided actually some of the first quantitative models of intuitive physics in babies. So babies shown scenes like these ones over here, which again, this isn't really like anything that the typical 12-month-old has seen. But seeing just a little bit of dynamics of a few objects bouncing around in one of these gumball machines, and then with an occlusion of either a very short period, but like on the timescales that Ode was talking about in the moments data set, 0, 1, or 2 seconds. In this experiment, you vary the number of objects at different colors, how close the objects are to the exit at different points as they're moving around randomly, and the duration of occlusion. And those have predictable effects on how likely an object of one color or another is to come out of the hole after occlusion. And infants look longer in a graded way when something is more surprising or lower probability, according to our model. So this probabilistic physics simulation engine was really the first model that we had that could quantitatively predict infant surprise. Okay. Bringing things back to the brain, we've together over in the last couple of years, together with Nancy Kamwisher and several great researchers in her lab, Jason Fisher, who's now at Johns Hopkins, and Sarah Schwetman, who's finishing up her PhD, have identified regions in the human brain that seem to underlie these kinds of judgments, including the prediction that we talked about, but also, for example, invariant representations of mass. This is a paper that recently came out in eLife, where you can, for example, cross-decode across all these different ways of perceiving whether an object is heavier or lighter based on its physical dynamics. It seems that this part of the brain is inferring and encoding that, and it also underlies the kinds of predictive judgments that we saw here. Okay. These brain networks in premotor and parietal areas, it's not like nobody's ever studied them before. They've been previously identified and studied in the context of action planning and tool use. And I think that's, as I hope you can see here, that all makes sense now, in a sense, that, I can tell evolutionary just so stories, and I'd love to try to study these in a serious way. But the idea that brain systems that originally developed probably to move our own bodies around and then to use other objects as tools and figure out how to use them to move other things around, they now can be taken offline and used in this very, very flexible way. I'd really love to understand at a neural circuit level how these systems work. And to do this, I've been working with a number of researchers, including and especially people in Dan Yamins' lab. So here, these are just figures summarizing two of the projects that Dan talked about. Damien's work on these hierarchical relation networks for particle-based physics, and Dan Baer and Xiaofei's work on these learned physical scene graph representations. And though we don't yet have direct evidence that the brain works this way, these are at least somewhat plausible models, especially when you confront the challenges that Dan was talking about, like the fact that graph networks are not exactly like neural networks, but you have to have some way of rendering them into a fixed finite size neural population. But this is the research program, and what I'm showing you is the top-down perspective on what I think, as you saw, is the bottom-up perspective before. So the optimist in me is that these perspectives can converge. Though we don't have evidence for those kind of models yet as being in the brain, we've identified where to look with fMRI, and the next step now is to see if those models actually can describe the encodings there, for example, and then maybe even the neural circuitry. But one example of this kind of approach, work that Ilker Yildirim recently published in Science Advances, is just another idea, basically using a neural network, a deep neural network, that's been trained to invert not a physics program, but a graphics program. And he showed that when you apply this to the well-known face patch circuitry that Doris Sau and Vinberg Freewald have studied in macaques in inferotemporal cortex, this kind of neural inverse graphics program provides really a strikingly good account of, for example, the patterns in similarity of representation of faces in different viewpoints and different identities. Here's the efficient inverse graphic network of Yildirim, and it does a much better job of accounting for multiple stages of representation in the primate brain than, say, VGG face, which is one of the standard state-of-the-art open deep neural face models that was trained not to invert a graphics model, but to do classification. So in some sense, this also gives a different interpretation of the function of the visual system, something potentially more generally like inverse graphics. Intuitive physics has been used and recently in these are just several collaborations we've worked on to try to put intuitive physics into robots. Some of these systems do various kinds of learning. So for example, Yunju Li's system in the lower left that's kind of making the sushi rice uses a very similar kind of hierarchical relational graph system to the work from Dan Yamins' lab, but then uses it for model predictive control. But the systems, for example, that Marc Toussaint built that like humans and even like some other animals, smart animals like crows, can learn to use tools that they've never really encountered before in flexible ways, even to use, for example, a tool to get another tool, or Nima Fazeli's work with Jiajun Wu, who's recently joined Stanford as a great assistant professor in computer science, building a system that can learn to play Jenga, or Yunming Hu's work on using soft body physics engines to learn to walk. There's relatively little learning here, or very, very simple focused model-based learning. And again, I think this represents the more sort of top-down structure-driven approach to how we might use intuitive physics in robots that can flexibly engage with a range of tasks that are not much like the experience they've come before. I just want to leave you with two highlights of where I think the future is. So one is, I think to really make this approach, go to the moon, it's going to need some rocket boosters. And for this, I've been collaborating with my longtime colleague, Vikash Mansinga, who runs MIT's probabilistic computing project, especially the work of Marco Cusimano-Towner, who recently got his PhD there, based on the system Gen, which is one of the newest state-of-the-art probabilistic programming languages. Really think of it as a AI programming platform that really nicely integrates probabilistic, symbolic, and differentiable, or if you like, neural network modeling and inference. This is an open source platform. It's, I won't go into the details, but it's Julia based. It also sits on top of PyTorch, and it really gives us ways to build flexible, scalable, very efficient, real-time generative models and a range of specialized inference programs that can let you do, for example, take the ideas of common sense object systems, but also agent systems and places systems. These are sort of the three classic Spelke core knowledge systems, and take game engine inspired symbolic geometric representations of scenes, but now across very different scales, ranging from abstract symbolic scales to fine scale 3D structures and many things in between, and do real-time probabilistic inference over these. I think that's what's going to allow us, for example, to really make good on this as a approach to scalable AI. I'll skip, because I'm just about out of time, how we're using this in the context of action understanding, but we can come back to this in the discussion. I've mostly focused here on intuitive physics, but understanding, for example, what makes a scene like this, how you understand what somebody's reaching for and that somebody else is trying to help them, versus a scene like this, where you understand that what somebody's doing is the opposite of helping, right? We think that these kinds of when we already have preliminary examples of these kinds of probabilistic programming systems being used in a multi-agent context with generative action programs and agent models, where the agent can basically try to maximize its expected utility based on its expectation of another agent's expected utility. That's a simple version of helping, where you make it a negative dependence and then it becomes hindering. This is a way to try to do the kind of action agent-based scene understanding that we saw, for example, in the Wernicke and Tomasello videos. The last direction I just want to talk about is learning, which is, if common sense is based on these kinds of simulation programs, then learning common sense has to be something like a program learning program. So we think of this as, what I sometimes call the hard problem of learning, because unlike learning in a neural network, it's not just about, there's not a smooth error landscape that you can do gradient descent on. The space of programs is much more complex. The search problem is much harder, yet somehow children solve it. Starting a few years ago in our group, we've been working on something that we call Bayesian program learning. So for example, in the thesis of Brendan Lake, he developed together with Russell Kudinov this omniglot data set, which for us is, for many people have used it as a kind of one-shot or few-shot concept learning domain, where if you look at all these characters in many different alphabets, each one represents a visual concept, a simple one that you can learn from one example. But the way we approach it is as a simple warm-up problem for program learning, because every one of these concepts can be described by a generative probabilistic program, something like a drawing program or an action program for how you put ink on the page in terms of strokes and substrokes. And that makes a template for how you would draw new characters. And then perceiving or learning a character from one example is a kind of Bayesian inference, running that program backwards to infer the evaluation trace that led to one example, and then you can sort of rerun it to produce, render, imagine, and classify new instances. And this idea of Bayesian program learning is one that we've been applying in a number of different settings, going beyond handwritten characters like 3D shape programs or programs that can interpret images, or even kinds of reinforcement learning simple Atari-like video games. This is from the thesis work of Pedro Civitas, where he's shown that the idea of Bayesian program learning and then using that in a sort of a model-based planning approach can learn to play new Atari-like games very, very quickly, hundreds of times faster than even the best deep reinforcement learning systems, and almost as fast as a person. So where this leaves us, though, is still with much harder problems of essentially program synthesis. To me, I think the rocket boosters that we need for learning programs is best encapsulated in this phrase, the child is hacker or the child is coder. Hacker is, around MIT, we're thinking of the good kind of hackers, the ones who just spend all their days making their code more awesome. But you could just think of any really, good creative software engineer, whose job is to produce code. What are all the activities of coding? All the ways you make your code better on a daily basis. So tuning parameters is one of them in existing code, right? That's kind of the coding version of what we do when we're running stochastic gradient descent or backprop on a fixed neural network. But there's many other activities which are structurally modifying the code, adding functions, extracting functions, debugging, finding errors, profiling, refactoring code to make it more generalizable, maybe more efficient, more elegant, adding new types, writing new libraries, writing whole new languages. And we think all these activities of coding have analogies in children's learning. And so if we want childlike learning algorithms, then we need coding algorithms or automatic program synthesis algorithms that do these kinds of things. Now, we're very far from doing that. And this childless hacker TICS paper just kind of sketches out the idea and makes the proposal. It's sort of a white paper. I'll just leave you with one example of another recent PhD thesis from our group. This is the work of Kevin Ellis, who just graduated this year, and he's going to be starting next year as a assistant professor at Cornell. In the meantime, he's working at a startup called Common Sense Machines, which came out of our group also, and is trying to explore some of these ideas in some AI sort of model building context. That's a story for another time. But what Kevin did in his thesis work is built the system, among other things, called Dreamcoder, which is, you can think of it as a system that doesn't just learn to write programs, but it learns simple programming languages to capture a domain of learning. It does this with a kind of wake-sleep learning in what is often these days called a neurosymbolic framework. So the basic things, at the heart of what it learns is libraries of coding primitives that then let it write new programs more quickly. But it also learns a neural network to guide the search. And it jointly bootstraps through two different kinds of sleep learning phases, the symbolic program library, as well as neural networks, which represent a kind of procedural expertise that help to guide the search for new programs. And just to illustrate this on some kind of more graphical examples, there's many different applications of this system. But like, let's say we want to learn to make various objects out of blocks or learn drawing programs. So for example, we can start off with a very simple minimal language for drawing, like logo, basically, right? Where you have a pen, you can pick it up and put it down, you can go in a line, or you can turn. But then we can learn a library of higher level drawing primitives, like circles, semicircles, spirals, polygons, or higher order ones, like take any shape and repeat it radially symmetrically some number of times, okay? And then that now lets us learn to draw many new shapes that we couldn't draw originally. The neural network is trained on these simulations that are drawn from the basically there's a probabilistic generative model that's this learned library. So we draw over iterations, we simulate random programs drawn from our growing library. And so over the course of learning, because the library gets more complex, the random simulations or the dreams become much more interesting. And that provides much better training data for the neural network, which helps it solve more problems, which helps it learn yet more new good primitives. So that's the positive virtuous cycle of bootstrapping that you can see in this algorithm. We think that's one way to start to capture some more interesting ideas of children's learning. Okay. There's a lot of other cool things like using this to learn languages of vector algebra and physics, or even learning basic functional programming languages. But check out the Dreamcoder paper on arXiv if you want to see more of that. So just to conclude, what I've tried to sketch here is both the toolkit we're using and a roadmap for how we might start to fulfill AI's oldest dream, building a machine that grows into intelligence the way a person does. And from the science side, really thereby come to understand better how our own minds are built. And it starts from revisiting the classic questions that come up in any approach to learning, which is what do you start with and how do you learn the rest? And recognizing from multiple decades of developmental psychology and cognitive neuroscience that human brains really do seem to start with a lot of structure, and learning procedures have to be, or we have a range of learning procedures, including things which are something probably like neural networks or like stochastic gradient descent in a differentiable program, but also much more structural kinds of learning and inference as we see in probabilistic programs and program synthesis methods. And when I talk about a roadmap, what I mean is something like this, okay? And I think this is where especially the work I've been talking about meets up with what Yejin is doing. Multiple phases of knowledge that start with that 1.5-year-old stage and then go into the next key stages of learning. So what's the next big stage after 1.5? Well, it's basically 1.5 to 3, when the most important thing that every child in our world learns is how to read, or language, and then how to read, right? And once you get that, then you have the stage of 3 on up, which is using language to learn everything else. First by talking, asking questions and answers, and then by reading. And that allows you to tap into all the knowledge that humans have built culturally that accumulates across generations. That's the real singularity. I think that's the basis for being able to build machines that humans can interact with the way we've always interacted with each other, in a true human-centric way. machines we can talk to, trust, and teach. And I think building, the kind of human-centric AI that HI is all about. And when I say this as a roadmap, I mean this quite seriously. I mean that by seriously studying each of these stages of children's cognitive development, trying to draw the kind of reverse engineering insights that we've tried to do in the earliest stages in babies, but doing that all the way along, building up with the engineering toolkit and the science together, I think that really is our best hope to build the kind of AI that we all would like to see. Thanks.
Thank you very much, Josh, for that integrative panorama. So at this point, I'd like to ask all the other speakers, Sanjeev, Yejin, and Aod, to come back and join us for the panel discussion. And I'd like to remind our audience that you can submit questions for our speakers on the event page of our website. Okay, I think we've got everyone back and live now, so let's start at it. As a prelude remark, Josh already observed that in some sense the morning speakers were more of a lump in that, I mean, if I very crudely group them, in some sense they're all happier with a learn forward from pixels perspective to life, whereas the afternoon speakers are a much more diverse crowd. But we really do hope and believe that there are a lot of different perspectives and a lot to learn in different ways, and actually understanding intelligence, both human intelligence and how to build it into machines. So I thought I might ask first Sanjeev a question relating to the first part of your talk, but it's a little bit of a tricky question, but I'll try you on it and see if you have a thought about this. In the morning talks, our morning speakers basically said, oh, neuroscience is useless for understanding how learning works or learning algorithms, right? That we just can't really see the details of the learning algorithm or come up with anything useful from what we can do with neuroscience. So if we're going to make progress in learning algorithms, it looks like it has to come from artificial intelligence. And of the three motivations you listed, so basically the second and the third ones were both related to learning algorithms. The second one sort of more narrowly on optimization methods, and the third one as to what we actually need to understand how we get flexible interactive agents like human beings. Do you think, right, so in the neuroscience context, there's been lots of discussion. People say that there doesn't seem to be anything like backprop, but there are certain kinds of feedback loops that are going on. Like, do you think there are possibilities for a theory first perspective to help us get more insight into how human learning works, or is that too much of a leap to hope for?
So I think one insight that we got out of some of the theory we did in the last couple of years is that you should the gradient-based learning that we do is at the parameter level, right? And and what we are interested in is the end-to-end functionality, the functions, and that seems to be some very different process. So, and you can't really infer the properties of the latter from the former. So, so right now we just understand that those can be very different, and you don't go in an easy way to understand the trajectory of the end-to-end function. So, yeah. So I guess my question about the neuroscience would be that the data is, as you say, very low level, and it's very fragmented. There's all kinds of things going on, and you see bits and pieces of it. And so, indeed, yeah, what we have an intuition about is the end-to-end function that's going on, and the mechanics of it. It's not clear that that's so important. I mean, there's some local update, and there's a network there, but not clear that that should be very important. So
Is
maybe we're on the right track and sort of inventing our own architectures.
Is possibly part of the answer to that the direction that Josh, you were heading in on wanting to emphasize the structure that is present in the brain? So rather than, I guess, most of modern neural networks, deep learning, well, there's some structure that networks, but in some sense, the role of that is minimized and the role of parameter learning is maximized.
Yeah, I mean, I think there is a connection, and I think it's one that I'd love to get a theorist perspective on, because I mean, there's again, Sanjeev mentioned this also. There's a long tradition of learning theory that shows that if you want to generalize in strong ways from small amounts of data, you have to have some kind of inductive bias or something built in. And the question is sort of, in what form is that built in? Or are there ways that in a meta learning sense, you can get other kinds of data that can inform what's going on? But one idea, I mean, here's a very relatively concrete theory question. I know actually we've talked about this with Surya. I don't know if Sanjeev, we've talked about it, but there's a thing that we see, we in the, let's just say the deep learning community sees. I see this in some of the deep learning projects I've worked on, where when you take a complex deep network that achieves some state of the art or great performance on maybe an engineering task or on some brain modeling task, the training matters, but it doesn't matter as much as you might think. If you take the architecture and just kind of randomize the weights, so start off with small random weights, often it kind of still works, not as well, but often still kind of works. And networks, if you compare architectures, different architectures with their initial weights, there's often the same relative performance. The ones that are really good after training or better after training were also better before training. And one more thing that we see, and I've seen this in vision projects we've worked on, as well as language projects. Like there was this project that was mentioned earlier by Martin Schrimpf and Ev Fedorenko, which I played a small role in that project on using GPT and other transformer models for modeling language in the brain. We see the same thing there also, which is that if you take, again, an untrained sort of random weight network, but you do just a little bit of training, like on the last layer, like you build a linear decoder, that often works pretty well. So I wonder, what is the possibility, or what are the prospects for an approach to understanding how brain development and inductive bias might work, where most of the inductive bias is in the architecture, with a little bit of learning kind of at the end. So you don't need to do backprop if all you're doing is building putting a single layer on at the end, or again, it might be different brain networks that effectively act as a maybe very structured layer looking back at another one, but the amount of learning could be local and limited, and there could be a lot of inductive bias in the architecture. Can we understand theoretically like why that often works pretty well? Does that resonate with you guys at all?
Yeah, so I guess I'll mention a few random things and see if it works. So there's this study of over-parameterized nets, and one of the things people have studied are these neural tangent kernels. That you take an architecture and take its infinite limit in width. And that's sort of like what you're saying, that you're basically training the last layer in some sense. And there's a strong inductive bias, which is a neural tangent kernel for that architecture. And those actually do reasonably well. And these were always called, I mean, these are related to what the Europeans used to call liquid state machines. They've been studying those for several decades.
But these could be, but those are like where there's like basically random weights, and even like a random.
Right. So what happens is that when you go to the infinite limit, the training is basically very minimal as well.
Right.
Basically you're seeing something related to the architecture, not so much training.
It's interesting that again, like the transformer architecture was clearly a big step forward, right? Even if it's not enough, it's clearly a big step forward. And GPT has some nice architectural properties that are different from the BERT style models. And it's interesting that maybe what we see going on there is like a cultural evolution recapitulation or analog of biological evolution, right? Where like the culture of deep learning driven by the massive energy of the tech industry and all of all of the things you're saying we want from our technology leads to a process. Again, it's a kind of code evolution process that produces architectures that have really interesting properties. And maybe that's kind of analogous to what biology did, where again, a lot of the work is being done by evolution, coming up with a certain architecture which has certain inductive biases baked into it.
So I want to actually make a quick point about that. So what you call architecture actually comes with an algorithm, training algorithm.
Right. That's right. Just as in biology, right?
Yeah.
You're saying in biology, they're both
right.
exactly.
Yeah.
Right.
Yeah. So there's like a simple paper, like a cute paper we have out as well, and like the difference between convolutional nets and fully connected nets. Like, how do you explain that convolutional nets are better? And you cannot do it by traditional learning theory because a fully connected net contains a convolutional net, right? You could always train it by ignoring some of the connections and enforcing weight sharing. So somehow the algorithm, training algorithm plays a role in the difference. So now actually we have some theory that shows it. But so yeah, there is definitely an algorithm at the back of your mind already when you talk about architecture.
I wanted to dive in. Yeah, so Sanjeev, yeah, we've also looked at these neural tangent kernels, and we actually show that in narrow networks that are used in practice, if you train for a little bit, you have a trained tangent kernel that picks up a lot of important features in data, that then if you learn with that one, you outperform the usual neural tangent kernel quite a lot. But so I wanted to go back and ask a question in general, I think an integrative question about learning, right? So on the one hand, we've been talking about common sense learning, Yejin and Josh talked about that. And then on the other side, we've been talking about self-supervised learning. So these are kind of two related questions. I'll just ask the first one for now. A key theme and arising in learning powerful representations that spans multiple talks is sort of self-supervised learning without labels, where you try to predict one part of an object from another, like predict a word from the rest of the sentences, or predict different views of an image, whether they're the same image or not. And in odds talk, whether three action sequences were, which one was the oddball action sequence. So why is it that these simple auxiliary tasks, self-supervised tasks, actually yield powerful representations? Can there be a theory for that? Can we have a guide the rational design of auxiliary tasks for bootstrapping powerful representations? From a neuroscience perspective, I find this very interesting because the first thing the retina does is parcellate the world into 20 different visual representations. For example, one of them is black and white and one of them is color. And we know from AI work that predicting color from black and white yields somewhat powerful representations. So maybe evolution figured out a way to parcellate the world into different subparts, and then it predicted the parts from each other in a very powerful way. And what we haven't quite figured out is what should we predict from what else, right? So I just wanted to seed that and see what you think.
We go to Odd first for some thoughts.
Yeah, Odd. This was inspired by Odd's talk, actually.
Yes. So to me, if a model is self-supervised or whatever literally the learning method you use to build your model, as a cognitive scientist, I will ask the model to show me beyond the performances of recognizing, for instance, object, is actually the error and the mistake that the model can make. So what we do is we go by our life by actually comparing something with something else and so on. So in a very simple way, we have those distance metrics, and the distance between things represent the type of mistake we do. So we could take an apple for an orange. So there's a long metric that can characterize the mistake. Now, one of the open questions in neural network, whatever the learning method you use, is let's say you have two networks with very different way to learn that produce the same sort of mistake. Does this mean that the representation they use is the same or not? And a lot in human cognition, we have this hypothesis and assumption that when the mistakes are very similar, then the underlying collection of representation of calculation are also similar. True or not, those are assumptions. But I see with the very fast development of a whole species of neural networks that we could be in cases where the output looks like something we could do. The range of mistake makes sense. Take the tiger for the cat, that makes sense. take the tiger for the car that does not make sense, the kind of, but have different representation. And that will be very informative to show how artificial networks with very different principles end up in the same same result. And that will be a way how AI can actually make cognitive scientists back to think.
Interesting. Yeah, that's interesting. I just wanted to contrast that with like the second question I was thinking of. And I do want to return to the self-supervised learning versus common sense reasoning. So the second question was about common sense reasoning, inspired by actually Yejin's talk. So I loved, Yejin, your example of visual question answering data sets, right? Where, you know, the professor doesn't teach and the professor just gives you a whole bunch of multiple choice questions and gives you the right answer, right? And then can we learn structured representations from that kind of a professor? And I sure couldn't, and I don't think humans can. And so you said we need to evaluate machines more generatively. We need to teach concepts more directly. And so what do you think the most promising pathways are there to doing that? Is self-supervised learning up to the task? Is it not? You know, what do you think about that?
Yeah, so I was going extremely fast over that slide than many others. But my current thinking is that self-supervised learning is a really important and powerful substrate to have. But in answering your question, I would like to also throw a theory question to Sanjeev, sort of going with, you know, all your vibes about, you know, asking Sanjeev some like interesting theory question, because when we look at these self-supervised language models, it's quite curious why GPT-3 can write really amazing quality life blogs. So, you know, there's this Berkeley kid who used the GPT-3 to produce a lot of life blogs, life advice, I meant. And I've done some of these experiments myself, and it's unbelievable how good the coherence is. There's like initial planning about what I'm going to tell you today, and you know, it maintains this long-term coherence. It's able to make some book recommendations relevant to what it's saying. I go ahead and check all these books, they exist, authors are correct. And then I went ahead and checked that it didn't plagiarize anything, and it did not, because I know it couldn't, because the way that text is generated is through random sampling. It's not entire random sampling, it's either nucleus sampling or temperature sampling. But in any case, it's curious why it's so good at seemingly harder tasks, and then it cannot do something so simple like, you know, common sense queries. And then, you know, you're supposed to say something obviously true, but GPT-3 spits out things that are so untrue and confused. So in some sense, it's very easy to break GPT-3 with much simpler tasks. And on that note, for example, we cannot still do paraphrasing or much easier lower level task that we would assume that someone who can write that nice blog post should be able to know about everything in language. But on a similar ground, it seems that machine translation is much harder, easier task compared to reading comprehension. And even the way that we currently, quote unquote, solve machine translation or reading comprehension is by converting everything into sequence to sequence models, under which it almost looks a little bit like a self-supervised learning. It's not, it's a supervised, but just the way that it's all about, you know, predicting the next token correctly. The objective function that seems being recycled by all these powerful transformer-based sequence-to-sequence models are again, somehow formulated technically, very much like a perceptual task. So when I was presenting this perception system 1 and system 2 reasoning, even for such higher level cognitive tasks like machine translation and reading comprehension, we move that into perceptual level stuff, and then that's how we do today. And it seems that this is really curious whether there's any theoretical way to say something about why writing blog posts is so much easier than being able to learn trivial common sense knowledge that every human knows about. And then I do have a speculative thought that's not theoretical, but more practically speaking. I'm drawing inspiration from cognitive science in this regard, that Josh talked about these core concepts. Is that the right word? Speck has core cognition concepts, like the way that humans learn about concepts, treat objects differently from actions, which are different from maybe forms, and time is different, and location is different, and the functions are different. These are all different fundamental concepts. Today, we treat everything as just same vector. And it seems that that's sort of the key challenge. And when I think about concepts, basically it's the ability to abstract away what's the sort of stuff Josh is doing, for example, and Odu was also presenting, where there's some like abstraction that is happening, but I don't know how far we can push by just using only one method. We might need to just broadly search, which might require really rethinking about the current paradigm of learning, whether supervised or not. I feel like they're both very narrow, although I love self-supervised learning.
Okay, should we get some comments, Fenstein and Sanjeev?
Okay. Yeah, so we've been studying self-supervised learning in my group for several years. I think Chris was very influential in helping me in the early days. Yeah, so I think the way I phrase self-supervised learning is more generally that there's task A and task B, and that you learn to do task A and it helps you with task B somehow. And the distribution may be very different and so on. So that, in a sort of black box way, will not happen very generally. I mean, unless the tasks and the distributions are fairly related. So it seems quite clear with a few toy examples that the inductive bias of the architecture is very important, what Josh was referring to as well. And I guess, yeah, Surya also referred to the architecture. So, and the architecture, I think, includes the algorithm, the training algorithm. So those are some of the basic things to say. And so then in terms of what we can do, I mean, saying something about what happens in training 100 billion parameters is currently a very difficult challenge for deep learning theory. So we have relatively toy models. But using those, you can sort of start teasing apart these things, like I indicated for language models, like, is it, I mean, there's some benefit to just, GPT-2 is a better language model than GPT-3 is a better language model than GPT-2. So you can see in some toy settings that epsilon, how far it is from optimum, helps in the task B. But then to answer your other question, why is it bad on some things? It's possibly true that learning the distribution, which anyway, to begin with, Chomsky's objection, all that, I mean, it's a shaky assumption that language has a distribution. And so if you're just phrasing your task as learning a distribution or predicting, then maybe there's only a limited number of things it implies, and it doesn't imply some of those other skills you want. Yeah, and those are all great questions for theory.
Can I comment on that? Yeah, I mean, that's along the lines of the way I think about it too, right? I mean, I think for many self-supervised algorithms, you can think of it as like learning a distribution, right? Like people who liked graphical models or Bayesian methods should be very happy with these, right? I mean, GPT is explicitly framed in that way. It's a lot like, the way, like, when I got into the field, the way we would approach unsupervised learning from a graphical models or Bayesian perspective is we define some latent variable model where there's some latent structure. I'm going to try to diagram it. Some latent structure with some prior, and there's some arrows coming down to the data. And, classic probabilistic language models, whether it's hidden Markov models or probabilistic context-free grammars, can all be framed in that way. And you could view what you're doing in, let's say, self-supervised learning in GPT or BERT. They're kind of variants on this. They're not exactly the same, obviously, and they're not exactly what I'm saying, but GPT is close to this, is like, assuming maybe relatively little explicit structure of the latent variable space, maybe a lot of implicit structure, which we don't fully understand, but you're basically, you're training a generative model, and by training many different, predict this condition on that, and this predict condition on that, like each word on any possible previous context, or in BERT, like each held out word or small chunk of language condition on everything around it, right? Like that's, I think mathematically one should be able to show that is similar to, maybe even in some cases exactly going to be the same as, as maximizing likelihood in a traditional unsupervised learning sense. But it has an extra bonus, which is that it's not just learning the latent structure. and the prior, but it's doing a kind of amortized inference, as Noah Goodman and others have called it, right? Like, because it's learning both a latent space that assigns high probability to data, and an encoding or recognition model that can estimate those latents from some other data. And maybe, and in some ways, like there's some nice work. I'm thinking of Richard Turner's group, I think, has some work on this. Many people have looked at this, where you might see meta learning algorithms and other kinds of algorithms like this as basically like they're jointly learning a good prior, but also sort of an amortized posterior, and you're learning a latent space that has multiple good properties. And then maybe what makes some architectures and algorithms better than others is not just do they capture the structure of the domain in some implicit way that can support good predictions, but do they, are they running the inference network in the right direction? And that, clearly, I would say, we would all say that's why GPT, or that would be related to why GPT is so good at generating long-range coherence, because that is the direction, in forward prediction, that's the setting it is trained to do that. So, maybe in some sense we shouldn't be surprised by that. It is, just like in earlier work with GANs in vision, it's surprising how much you can capture in these learned generative models and how much they can look like the real world, even things you haven't seen before. But also, just like what you were saying, Sanjeev, and I think what cognitive scientists would say, well, in some ways, going back to Chomsky, we shouldn't be that surprised that while there might be statistical structure to language or to images, right, that's different from it's maybe a consequence of the structure of the world, and the cognitive systems we build, having those kind of predictive statistical models are probably an important part of our real-time processing and how we use our knowledge, but it isn't the same as the knowledge, right? It's not the thing that supports counterfactual reasoning, imagining things that are vastly different from anything we've ever seen before, whereas the kind of common sense core knowledge that Spelke and others have studied in infants might be that, right? And then some of the things that we build when we build more, or at least my view is when we build more layered, structured, symbolic representations in natural language and others beyond that, also, again, give us the ability to think about and talk about and learn about things that are very different from our experience. And
should we maybe give Ord a chance?
Sure. Yeah. Sorry. I started going into my yeah. Right. Good.
Like I was just listening to Josh.
Well, I'll just say one more sentence and then shut up, and then it just closes off, which is just to say, imagine if we could do self-supervised learning, but with a more structured latent space, basically, that has the kind of common sense core things. That might be a way to get the best of all of these worlds, and maybe would lead to systems that that would have more of the properties we're talking about. And maybe that's what Comet is even in some sense starting to do. I'd like to understand it better there.
So is there anything you would like to add, or should we go on to a different question?
Different question. I was really listening, going into what was said.
Siri, do you want to?
Yeah, sure. Let's stick on this topic of common sense. So it's easy to point out examples of common sense, right? And we all kind of have a common sense notion of what common sense is. But it's perhaps a little bit more difficult to come up with a precise objective function that one could optimize to teach a machine to exhibit common sense. And so the question is, how might we as a field work towards that goal? I mean, Josh touched on this a little bit at the end of this talk in terms of, program learning programs. And so can there even be an algorithmic optimization-based approach to learning common sense, or might evolution have found some more common sense approach to imbue us with common sense, whatever that might be, and how might we exploit that to teach machines common sense?
Yeah,
I think Yejin and Josh probably have the most to say, but yeah, go ahead, Yejin.
Yeah, I love this question. It's a really interesting, almost a philosophical question, but practically speaking, it is true that it's really difficult to define common sense knowledge, and it's really surprising how much we actually know as common sense knowledge, as well as how much it actually does not really align exactly. So you and I could have a different quote unquote common sense knowledge. It's aligns well enough so that, we probably will not get into fist fight anytime soon. But it's it's similar to language, though, in that, what is the true definition of language so that you can really define and incorporate everything that people ever say? Well, today we kind of implicitly define it by just, here's this bunch of text that people spit out, and let's optimize for the perplexity during training, or log likelihood, whatever. So similarly, this is how I view, except that the challenge is that there's no natural corpora where people spit out common sense descriptions, which is why we had to start with this atomic knowledge graph as a symbolic small subset of common sense that a lot of crowd workers seem to share. But similar to language, also when we write papers, reviewer too always do not understand our perfectly written paper. There's nothing confusing about it, but they didn't understand. So that's how I also see common sense is like that. People might have a little bit different interpretation, but that's okay. And that shouldn't deter us from studying this as a scientific topic, just like how it's okay to study language, even though reviewer too never agrees with us. So for now, I didn't have any better way to do this other than directly optimizing for this atomic corpora for the time being. But what's wonderful about it when it's mixed in with self-supervised learning on language itself is that it's learning significantly more than what I could ever imagine. So when giving this online, giving these talks and then doing online demo, oftentimes I was given like adversarial examples and I would tell the audience that, oh, this is not going to work. And then I try anyways, just for your viewing pleasure. And then it does do better than what anybody would have expected. So this happened multiple times. I'm not saying that this is a perfect system, but it's very interesting how much it can generalize. And then I'm seeing that the stronger language model is, the faster the generalization actually happens. So it's now I'm starting to speak things that's not in public space yet. And that's very exciting, but I don't have, ideally, I really wish that we didn't even need atomic or anything and some magic arises from neural network to figure everything out. But I do wonder whether it's even reasonable wish to have if we only have current learning paradigm set up either for optimizing likelihood on a lot of raw text or solving this QA problem right. I think we somehow need to have an entirely different objective function, which might be even harder to write than writing the objective function for common sense. So I don't really have an answer other than some shreds of speculative thoughts.
Yeah, go for it.
Is that what's very good about common sense is that the concept is so elusive that we basically don't know how to give an operational definition, that a lot of people are going to use it and do things in a different way. That's very good. So there's going to be a lot of the word used. I don't know how to define it. It might be defined depending on the task and so on. But the way I think about it is it's too far. I don't know how to do it. So I need a smaller goal, except that the smaller goal is enormous itself. It's the notion of analogy. We always speak and see and think about analogy. And analogy is a space of possibilities. You can have analogy in space, in time, in concept, in mathematics, in relating colors and so on. So analogy itself is a huge research endeavor. I find very interesting that we were talking about GPT-3. Okay, it was based on an enormous amount of learning, but it can perform a very simple level of analogy with one or a few short learning. So analogy is like if you say ABC is to PQR, what's ABD is to PQ, and you have to finish it up. And I think analogy is a fundamental things to model. Go ahead, Sanjeev. I'm done.
Well, I can go next. Okay, so let me follow on with another question.
Can I say something about common sense before we leave that topic?
Yeah, Josh, you had a concrete approach in terms of programming programs, but
well, yeah, yeah.
How would you
I just want
function to optimize common sense? That's the question.
Well, so I just wanted to say, I think I'm more of an optimist, I think, about, I mean, I hear what Ode is saying, and people use the word common sense in all sorts of different ways, but I think there actually is a core meaning behind both the classic way it was used in earlier AI and the way Yejin is using it and the way I was trying to use it. And I think we can, and I think what Ode is saying too, and I think we can work on that. It's something like, you know, common sense knowledge is like all the things that we all know that nobody ever talks about. So, right, it used to be common sense was like all that you need to know in order to be able to read the newspaper. The newspaper never writes about it. It's just what the background knowledge you need to know to read the newspaper, or maybe to read Wikipedia, right? And it's why it's hard to get from data, because nobody writes about it, so you can't just mine it from lots of text. The Spelke or developmental approach, the infant approach, is it's like all the stuff you know before you know how to say anything, right? But that early language builds on. And it's kind of in there, especially like in syntax and semantics of verbs and how phrases are put together. So like, the word, the word object or the word agent, those are common sense concepts, but they're not actually words that young children learn, but they are there in sort of the way nouns and verbs work, right? For example, or common sense notions of space and time. Those are also things that verb syntax and semantics, for example, the work of Beth Levine here at Stanford is really the seminal work showing this. It's sort of in there in how we learn about how verbs work and meaning form correspondences. So what that suggests again is it's sort of like, basically think of this common sense as multiple stages of knowledge, starting with what babies have, and then what you have when you first learn language, and then what that comes to enable, which are like basically building languages of thought. It's the stuff, as Steve Pinker calls it, like the stuff of thought in his book of that name, right? It's not the stuff you talk about, but it's the stuff you need to know to form new thoughts, and then to form new sentences, and then to use those sentences to form yet more complex new thoughts. Yeah. So there's not really a metric that you optimize other than basically trying to solve a bunch of problems of the right sort, and then building whatever is the language of thought that supports flexible, open solutions to that flexible, open-ended class of problems, right?
Yeah. Let me ask
each
a
corresponding
question to Ode, which isn't exactly common sense, but sort of heads in the direction, well, of some of the topics that came up of having prior models and of the world, right? So you emphasized these 3-second activity scenes and at least what I took away, that you primarily motivated having these sort of 3-second snippets in terms of, humans responding in the natural visual environment, that they wanted to get a quick snippet of things. But I mean, I was thinking in my head, well, so there's an obvious advantage to seeing some movement rather than just a static scene. You obviously get this enormous amount of extra value from seeing a little bit of movement in there. But beyond that, is a lot of the secret of the effectiveness of these 3-second scenes not sort of the human hunter on the prowl or something, but it really has much more to do with humans have these really rich models in their heads, and as soon as we've seen a second or so of video, well, we can predict backwards and we can predict forwards, and it's much more a story about our very good models of the world, both from priors and learned, that's going on there.
Well, the 3-second is it's just a number in order if you want to train a model. What we were looking after is that the way our brain conceptualize the world is there's a certain dynamics to it. So if I want to pick up an object, it takes some time. And there's a lot of the activity that are meaningful to us that unfold within a few seconds. So then 3 is just an average.
Sure.
And the thing we observe is that if you train a model on shorter or longer video, or then if you train on on shorter video, you will miss information. But on the sort of 3 seconds, there is enough information in order to develop robust features. And Also, it's the kind of this average length of short-term memory, or things you do, you put in memory, you think about something else. So we have a big time, time module over here, and it's at several scales. And it was something that just make our model works much better. It's a good number.
It seems like a magic number, though. I mean, in a good way, right? Like, people have proposed 2 or 3 seconds as a magic number all over. That would be an interesting paper to write. I don't know if anyone's written that paper, but I'd love to see, you know, what is it about, like, the length of a sentence, the length of an activity, the length of a professional football play, or even a basketball play. You know, there's something about, like, the brain that makes that the length of human activity at the micro scale, or at the basic kind of single sentence level, right?
The autocorrelation of the movement of prey, the time it takes to turn, and while you're chasing it.
Well, yeah, I mean, for mammals at least, maybe. I know, I think they're faster, but but you know, at the level of it's easier for me to think of things like sports, whether it's baseball or basketball or football, because they kind of unfold at that time scale, you know. But that's I don't go hunting, but I don't know. But, yeah.
Well, the other thing is the human brain will have certain buffer related to things you hold for a few seconds. And if you want to remember something after 20
the remembered present,
after, let's say, 30, 40 seconds, it's another structure. And those are neuroscience results.
Yeah, exactly. There's something fundamental.
It's like at some point you switch.
Right, but yeah, it seems like there's something fundamental about the fact that we're talking about human activity. So it's like the time scale of human activity planning and execution is going to then turn into the time scale of where perception is most meaningfully. Yeah. And again, that speaks to the generative model perspective. So, yeah.
I guess I have a question for Yejin, actually. So in the first panel discussion and the talks in the first session, the issue of embodied cognition came up a lot, right? And we know that in the brain, language areas like Broca's area and Wernicke's area, they talk in a very strongly coupled way with other parts of the brain that both represent and drive action in the world. But you've gotten a lot of mileage out of discovering good causal representations and knowledge representations just from language alone, or language plus static scenes. Do you think that we need embodiment to sort of create powerful AI systems, or do you think there's a lot more we can do without resorting to embodied systems?
Yeah, awesome question. Yes and no. So I didn't talk about it very much about my other grounded research, but that's how I studied, actually, thinking about common sense. I was thinking, oh, I'm going to just extract knowledge from images. And then I realized that, wow, computer vision is really hard. I thought the language is hard, but computer vision is not only hard, it's also very slow. So after processing so much data, all that I got was like hundreds of knowledge. Then I'm impatient person. So I wanted to go very large scale, very fast. And it seemed that language is going to allow me to go very large scale, very fast, covering a lot of broad scope of things. But I certainly do not believe that alone will be sufficient, especially for systems that might want to interact with the people through like robotic bodies, or even computer vision, because you do need to somehow translate what you know about the world in language with like intuitive physics, the sort of stuff Joshua was showing earlier in his presentation. And that's really a huge missing link. And so that's why I think embodiment is important, but there's something really dissatisfying in the way that current language and vision research works, which tends to focus more on the sort of like conjunctive subset of concepts between what's in the image and what's in the language, as opposed to being able to really unify everything and then be able to learn everything in a more meaningful way. Another concern so I'm currently playing with 3D environment as one of the work in progress, but it's really frustrating how basically the world is defined by some engineers who built the 3D environment, and I cannot get out of it. And I don't know how the robust generalization will easily happen between that world and in the world that I presented in the images. Like, people might crash the car, or drown in the ocean. And I certainly do not need to experience any of that in an embodied environments in order to understand what it is like crashing the car or drowning in the water. So yeah, a lot more research to be done really, but I do like embodied research direction quite a bit.
Yeah, let me ask one last question. We'll go a couple of minutes over time since we started this session a little bit late, but this will be the last question, which actually I'm going to start with Yejin again, but I think it's one that other people can also have interest in. So I liked where Yejin began with sort of talking about Daniel Kahneman's System 1 and System 2. And I guess there's been a lot of talk about that. One of the most prominent recently was Yoshua Bengio at his Europe's 2019 keynote talked about System 1 and System 2. And I think a crude version of what you're meant to take away is deep learning has nailed System 1. And so now we can work on conquering System 2. Whereas you pointed out, there's somewhat more nuanced version where there are three things of perception, intuition, and reasoning. And so, well, maybe deep learning has nailed perception, but that then still leaves two things left. And, I was wondering what kind of models and methods we really have that are good for intuition, because, some of the other things that were mentioned, such as probabilistic programming, that sounds a lot more like the reasoning level to me, and some of the other talk about sort of neurosymbolic architectures, the symbolic part is kind of on the, seems like it's normally at the reasoning level. And well, what have we got for something like intuition? Well, Josh mentioned the metaphor of the game engine in your head, but I'm not quite sure that's really right for intuition. I mean, I was actually thinking of the example Josh gave of the Jenga game. I mean, I kind of think, whatever the flaws of your average game physics engine, I think it's 100 times better than my head is at working out the physics of what happens with Jenga blocks when they fall. But somehow I have enough vague intuition, I can play Jenga okay with my kids. So what should we be doing about intuition?
Yeah, that was such a nice summary, and it's true that I was opposing what Benjo said. But so what I realized about intuition as I read more into this non-CS Coxeye books is that, wow, there's so much going on in the intuitive level that humans are extremely powerful about. So I mean, probably don't you always also have this experience where you have an idea about new algorithm, but only intuitively that you have a hunch that this could work. You don't know why. You don't know why yet, but you just know, and you believe it very strongly. And then you look for some solutions to it. And then, eventually you do system to reasoning in order to figure everything out. But there's something really powerful about intuitive reasoning that even goes beyond the common sense type intuitive inferences. But today I was focusing more about the easier pieces, which seemed just simpler to target first. But other than admitting that I don't know the full answer to this, but this might be something really important to pay more attention to as an AI field, because this is really fascinating about human intelligence, and this might be something neural networks are very good at for some mysterious reasons.
Have ideas on what ways forward at the intuition level?
But I mean, we do need to.
Can I raise a cog-sci perspective on this, and then just to frame the discussion? So cognitive scientists don't study intuition, and they don't, for the most part, really work on System 1 or System 2 either. Like those are, System 1 and System 2 is kind of a convenient summary of a whole bunch of different distinctions that is helpful for people outside of psychology to maybe understand, but it's not very helpful within psychology. Do you know what I mean? Like there's no part of the brain that's System 1 and part of the brain that's System 2. And there's many distinctions that are wrapped into that. And what individual people usually do is unpack those and study particular ones. And likewise, intuition is not just one thing. It's, you know, maybe for people who are in AI or neuroscience, it would help to make an analogy to learning. Like if someone asks you, how does learning work in the brain? Well, you know, there's so much that you know, do you mean reinforcement learning? Do you mean classification learning? Do you mean learning at this time scale? Do you mean at this and that? You know, there's so many things going on. But there are some things we can say about what I think the common sense intuitive notion of intuition is, and the ways cognitive scientists approach this, which fits with just what you were saying. So I might just put it out there, right? Which is like, often what we mean by intuition, I think, are unconscious computation. So we're not conscious of the computation or much of, you know, which includes the representations and the algorithms, but something pokes into consciousness and it often has a kind of a probabilistic character. So we can have a strong intuition or a vague intuition. I can have intuition that that's right or that's wrong or that's good or that's bad, and I can't say why, right? So a lot of the things that we pack into the word intuition are of that sort. And I think actually, if you look over different areas of cognitive science and computational modeling, people have had success at capturing different things, different aspects of that with different tools, but they all come down to some kind of approximate probabilistic inference, or at least the ones I know. And that includes some, you know, that's at least a way to render certain kinds of analogy models, because like Ode was talking about, sometimes there are analogies where it's like, I don't really know about this, but I think it's like that. So like high level similarity, where you can say, I think it is likely that what was true there might be true here. Or some of the Bayesian models that I used to work on earlier in my career, or like some of the neurosymbolic things, like when I was talking about Kevin Ellis's work there, or a lot of other work that people are doing in like neurosymbolic program synthesis, where you're basically, or you know, training a neural network to suggest, not to like write code, but the way we use it is it sort of guides a search. So it suggests to a search algorithm that's searching through this space of expressions in some programming language, where are the more or less promising ways to go based on the data that I've seen and maybe what I've done before. So
I agree that intuition is an imperfect word for the stuff in the middle.
But like, but let's just say like approximate amortized probabilistic inference, basically.
I'm tempted to throw to Sanjeev and say, Sanjeev, when you have an intuition as to how to go about solving a problem, do you think you're doing approximate probabilistic reasoning in your brain?
Yeah,
I'm not quite sure that's.
I'm less interested in your intuition about how you do intuitive reasoning, but
so, I know we are running out of time, but if I may add a little bit. So I love a lot of what Joshi says, and I keep following his talk. But minor bits that I may not necessarily completely agree with here is that, so I don't know, like, you know, I didn't read too many Kokusai books. In a year, there's limit to how many you can take a look. But it seemed that this contrast between conscious and unconscious inferences is a thing that people do talk about a lot, even like maybe not for reasoning, but more for like, you know, emotion-based research that focus just on emotion. They also seem to
or moral. You mentioned moral judgment.
Yeah,
a lot of those are also, yes.
You know, we could just think intuition equals unconscious, a fast associative reasoning thing that it seems that there have been such research, but
it's not always associative. I think it's it's usually
may or may not. So I agree with you that these things are very complicated in actual research, and these things are very much modeled up, and it's hard to separate that out. So that I totally agree with you.
Things that are fast and unconscious, but that can have a lot of computational structure.
About the probabilistic nature of it, I don't know if I can marginalize any of what I actually feel and assign, oh, this is definitely an idea in which I can assign 0.81 versus 0.78. I really don't know.
The probabilities are approximate too. I mean, you know, cognitive scientists
maybe we
usually
just know how to score things in a very inconsistent manner, though. I suspect we are very inconsistent.
So I wanted to ask one quick question. So intuition is being sort of equated with fast reasoning, but I think the more fascinating intuition for me, and probably everybody on this Zoom call got this at an early age, the subconscious thing, right? You're thinking about something, you sleep over it a night or two, and suddenly it's clear in your head. There's something else going on there.
Yeah, during sleep, you're dreaming about it. And then
No,
you
but it's not just sleep. Also, just you go about, go to the gym, whatever, right? Do other
Or so, yeah, sometimes exercise can do it too, right? Like,
but all kinds of
Just-
things, right?
yeah.
Play with your kids, whatever, right?
Yeah.
We could definitely talk a lot more about this, but I'm afraid I think we're out of time at this point. And really have to move on to the final session, I'm afraid. So I'd like to thank all our speakers. It was a wonderful discussion. I think we could have done another 40 minutes of it, but unfortunately,
thanks to you guys for a great day and great discussion.
So we can say thank you and goodbye to those speakers, and then we're going straight into the final short session where we're being joined by Bill Newsome and Michael Frank.
Thank you very much.
Okay, I'd now like to open our final session of the day and to welcome two guests. First, I'd like to welcome Michael Frank, Professor of Human Biology and Director of the Symbolic Systems Program at Stanford. And then secondly, there's Bill Newsome, who is the Director of the Stanford Wu Tsai Neuroscience Institute. Let me first of all start with you, Mike. Symbolic systems, that's a sort of strange Stanford thing. I know we're not unique. There is another university that has a symbolic systems program, but it's not such a common thing. So maybe you'd like to tell us about the symbolic systems program, and you better mention somewhere, how do you cope running a symbolic systems program in the middle of the neural revolution, I guess?
Well, yeah, thanks for having me. And I'm so glad that SimSys could be a co-sponsor to this really fun day of talks. Like you said, we're an undergraduate program at Stanford that's a fairly unique interdisciplinary mix. So we try to give students an education in computation, in formal methods, in philosophy, and in empirical cognitive science. So the idea is a student comes out of our program not only able to jump into building exciting new projects or participating in research kind of hands-on, but also able to understand the projects and the things they build in a broader theoretical and social context. So I'm hugely biased. I'm an alum of the SimSys program myself, actually, but I think we've got evidence for our success in this amazing broader list of alums, which includes founders from Silicon Valley companies like LinkedIn and Instagram, and also a wonderful list of academic alums doing research everywhere from neuroscience to philosophy and law.
Do you want to say a sentence more about how you think that comes together? Because, I mean, obviously the challenge in any interdisciplinary program is the students learn less about any particular thing than they could have if they had majored in psychology or majored in philosophy.
I mean, so one way of describing the major is Stanford's take on cognitive science, but honestly, I think that's not quite right. We call our introductory course Minds and Machines, and that's really the guiding relationship that I think is at the core of SimSys. So it's all about these different relationships that you can put minds and machines in. How to use machines to understand minds, that's neuroscience and cognitive science. Minds and machines interacting, that's human-computer interaction, and of course, building machines with minds or that approximate minds as an artificial intelligence. So I guess I think of SimSys as a jumping off point for the ways that relationship between minds and machines can get construed and can lead to future research.
Well, thanks, Mike. And also to turn now to Bill, can you tell us a little bit about the Wu Tsai Neuroscience Institute and yourself?
Yeah, happy to, Surya. Like Michael, I'm thankful for the opportunity to be involved in this symposium today. It's been a really rich set of talks, and I regard both HAI and Symbolic Systems as wonderful partners here on this campus to neuroscience. Neuroscience has been praised at some points during the day today, and it's been denigrated at others. I believe that trash was a direct quote. So it's been fun to kind of sit on the sidelines, and I have lots of reactions. But I think that we have a lot of mutual agenda here, and I really look forward to working with HAI and with Symbolic Systems going forward. The Wu Tsai Neurosciences Institute was conceived about 8 or 9 years ago by a couple of guys named Hennessy and Etchemendy. I think most Stanford people are familiar with those names, our former president and provost. who thought that neuroscience is one of 2 scientific disciplines on campus that had the potential to create a campus-wide community of scholarship, ranging across multiple schools, multiple departments, multiple conceptual approaches. And I think they were very far-sighted in that respect. And so the WuSci Neurosciences Institute is campus-wide. It does not sit under any one school. It sits under the Dean of Research. And so I interact with deans and department chairs from all over the university. And that is because neuroscience is so inherently interdisciplinary. All of the subject material we have been talking about today is definitely highly related to neuroscience, and yet we could go talk with a non-overlapping group of people, which we will be doing tomorrow morning in a symposium on the neurobiology of disease, and it would be equally relevant to neuroscience. And we have contributions coming from applied physics, that's Surya's home department, from genetics, chemistry, statistics, engineering. And it's important for people to understand that this isn't just icing on the cake for neuroscience. This is bread and butter. This is the future of brain science. The brain is too big of a problem to be solved by any one discipline, any one set of experimental techniques, or any one set of concepts. And we've all got to come together and work in tandem with each other and energizing each other and educating each other in order to solve this problem. And that's what the Institute's about. It's about doing that. And we do that by investing in people, hiring faculty, creating interdisciplinary fellowships for postdocs, for graduate students. We do that by investing in research through our Big Ideas in Neuroscience internal granting program, along with some seed grants, and a NeuroTranslate grant program, translating neuroscience ideas out into the real world. And we also do that through a new undergraduate education program that we started, a neuroscience interest group.
Thanks, Bill.
So we're in there, and we're doing this thing, and it's a natural ally to HAI and to SimSys both.
Yeah, thank you, Bill. And those remarks you've just said are really minimally a very good introduction to the next question I was hoping that people could address. But let me focus a bit more on linkages. That I think one of the feelings that we had in setting up HAI was that there was really a lot of connective tissue that needed to be developed to really get the synergies that we're hoping to see between research in neuroscience, cognitive science, psychology, and artificial intelligence. So let me maybe start with you, Mike. I mean, how do you see the prospects and the key things that we need for creating that type of connective tissue at Stanford? What are we doing, or what should we be doing? Perhaps, even, you focus quite a bit on the undergrads' interest in this space. What's the secret to connective tissue?
One little claim that I would make in response to Bill is that we're also kind of connected with HAI and our DNA, since John Etchemendy was actually one of the Symbolic Systems founders as well. But we're really working to expand that connection. So for example, we just rolled out a new concentration, which is a specialization track in Symbolic Systems for human-centered artificial intelligence. The idea behind that is to guide students towards the intersections of AI, science, policy, and ethics that I think really characterize the HAI vision. So that's kind of one intersection. But more generally, I think where this comes together is in undergraduate research for symbolic systems. And talented undergraduates do an incredible amount to advance research. So one of the most fun things for me as a working scientist in the lab is to host undergrads in the lab over the summer, where they put their full attention on the problems that we're interested in and really make big contributions. And so with support from HAI and from WuSci this last summer, we actually had the biggest ever group of SimSys undergrads embedded in labs, getting full earnings replacement to be able to really devote themselves to research. And that's precisely the kind of experience that motivates folks to go to grad school. And one last kind of stop along the way before grad school is honors research, where we're really seeing this kind of integration happen already. So our Firestone Medal winner last year, Nyani Crawford, won a university level prize for work investigating face recognition in CNNs. really this kind of very HAI topic of trying to understand the linkages between neuroscientific representations of face features and what's going on in the training data for networks. So I think we're really trying to build these links and getting students involved in research, getting them the tools they need to get kind of placed in labs early so that they can go on to do honors research and eventually to grad school is the track we want to encourage.
Great, thanks, Mike. Bill, I guess the same question for you. You're less of an undergraduate institute, more of a research institute. So I was wondering, how do you see the intersection between AI, cognitive science, and neuroscience going forward as a research field and through Wu Tsai? How do you see these fields working together?
Yeah, so we've given that quite some thought, Siri, as you know, because you've been part of the process. And we think that this interface is actually embodied. We embodied it in the design of our new building, the Stanford Neurosciences building here, which has a theory center inside it. And one of the principles here is that neuroscience going forward is going to go forward more rapidly and with deeper understanding and more incisive impact if theorists, data analytics specialists are embedded cheek by jowl with the experimental labs. It's important for both groups to work together, designing experiments, analyzing data. That theory center, when it is fully staffed, will have 6 research groups in it. Surya and Dan Yamins will both be there, as well as Scott Linderman, a new hire in the statistics department. And I would say that research in that center and then filtering out to all of our experimental labs will involve theory, Surya being a classic theorist who really wants to identify general principles of operation and ideally that you can write down in closed form equations. But there are neural network people who are really impactful. Dan Yamins being a classic person who's working hard with the deep convolutional networks. And there's high level data analytics that are so important to neuroscience because we, like many other fields, are getting these floods of large, very sophisticated data sets coming into our field due to advances in technology. And a traditionally trained neuroscientist like myself just is not prepared or competent to deal with these data sets. And Bob Laughlin, a physicist here at Stanford, once warned me, the biggest danger to your field is that 10 years down the line, you're going to have disks and disks and disks full of data, and you're simply going to be 10 years older. So the point being that understanding is really what we're after, right? And that's the goal of theory and computation and network modeling. And that's where we will have the closest interface with HAI going forward. And I would love to do, these interfaces have to be embodied in people. They have to be real embodied people. I'm all on the side of embodiment, by the way, in your previous discussion today. And hiring joint faculty, I think, is something that we really need to do. So these faculty will build the bridges. The students are already there. The students love this area, and they love the connection between neuroscience and artificial intelligence. And every faculty member we have hired is instantly glommed onto by a dozen students wanting to work in their labs. So the students are ahead of the institution at this point, and we need to do some hires together, to faculty level hires together, to create the environment where this can really go forward.
Let me continue a little bit along that theme and just see if there's any other items that people mentioned. So yeah, we've said quite a bit about the great programs, departments, and institutes at Stanford we already have. But there are always opportunities to build a more perfect union. And so Bill sort of mentioned the idea of how the students are already ahead and we just need to have the faculty there for them to work with. But for both of you, and maybe I'll start again with Mike, are there things you see as to how we could really do a little bit more to take things to the new level in really building the synergies between these 3 areas?
What I think is going to be a success here, but that hopefully we can replicate more. So one thing that is amazing that HAI has done as an institute is launched the Hoffman-Yi program. So this is through the generosity of Reid Hoffman, who will claim as a SimSys alum here. So this kind of moonshot project is bringing together interdisciplinary teams and getting them to work together to try to accomplish really large scale projects. So Dan Yamins leads one of these teams, and Chris, your colleague, Chris Potts from Linguistics leads another that I'm involved in, where there's some SimSys students already starting to do some work. But that's kind of that starts with the moonshot, and that's an important thing. But creating a broader ecosystem of opportunities that brings faculty together, even when that's not the most convenient or easy thing to do, is really critical. So that kind of community building that brings the faculty together and maybe is also led and leads the students, as Bill was saying, towards this intersection is really what we need. So there's a combination of faculty and also opportunities for interaction, because the work of getting these conversations going is fun, but it's hard, and it's not the first priority for a lot of folks, especially younger faculty. Right. So as we've seen in some of the discussions today, there are foundational issues that we disagree on. And so for each of the projects I've been involved in, you really have to have people sitting down again and again to hash out the vocabulary that allows them to have the interdisciplinary conversation. And sometimes you need people that are really trained in that conversation in order to be able to contribute. So creating those spaces is, I think, the next frontier for HI and for these affiliated programs.
Yeah, Bill, did you have any further thoughts you wanted to share on this particular issue of moving to the next level in terms of building connections? Or
yeah, I think really focusing for WuSci on the faculty level interactions is really important. I think that though, we have discussed Syria within the Institute, and I don't know how much this has been discussed within HI, that building interdisciplinary postdoctoral program would be a really good thing to do. I mean, Surya himself came out of string theory and physics for his PhD, and it was only as a postdoc that he got interested in biology and did a detour through yeast and biochemistry before winding up in neuroscience. But giving postdocs that extended kind of bi-disciplinary training and the freedom and time and money to explore a second area, I think, is a critical thing for us to develop the leadership of tomorrow, because tomorrow's leaders can't be somebody like me, who's a traditional neurophysiologist and I know how to do one thing well. But fortunately, I've been open to some good new ideas and having good collaborators. But the future really belongs to people who span these boundaries intellectually and practically and can speak the language already. I mean, as Chris or Mike, I think Mike was saying, having these conversations across disciplines, it's really hard. Just at the beginning, you're using the same words and you're meaning completely different things when you use those words. And just speaking a common language is so difficult. So the earlier we can start on that, the better.
Great. Well, Mike and Bill, you're not only program leaders, you're both also very accomplished scientists. So before the time runs out, I wondered if you have any thoughts or takeaways related to our theme and sessions today. So Mike, for you, earlier on, there was actually a cameo appearance of your SACAM project. And I guess by background, you're actually more of a developmental psychologist, but as things are going like this, you're either willingly or unwillingly sort of heading more in the direction of cognitive psychology, I think. What are your thoughts?
Because my interest is always in development and growth and change and learning, I was really fascinated by this morning discussion about sample complexity, about how much data it takes to learn something versus how much data it should take. And of course, right, if we want to trot out these examples, if you look at GPT-3, tremendous success by some, but not all measures, it takes 5 orders of magnitude more data than a 3-year-old. And I think it'd probably beat the 3-year-old on a lot of tasks, but my 7-year-old, which has got only about, she's got about double the data, is probably going to win on a lot of those. We heard a lot about interesting ways to improve transfer and efficiency today, but I guess my personal interest is in learning from other people. So, Chris, you mentioned scientists in the crib, and Josh talked about the child as hacker. I guess maybe I'm primed by undergraduate education, but I think about a slightly different metaphor, which is the scientist is actually the undergraduate student working in the lab. They do discover things. There are absolutely valuable discoveries that come out, but there's also a lot of coursework in reading, right? There are a lot of people around providing the scaffolding. And I think that that's an important insight that I'd love to see talked about more. You know, my colleague Hyo Gwon has really, explored how many cases you can get kind of really rich information transferred by just a simple social situation that sets up kind of a very, very subtle inference in a child. And that's the kind of inference that deep learning systems don't tend to make. A lot of AI systems are, you repeat the same thing over and over again, rather than inferring a tremendous amount from a single gaze or a single utterance. And so that kind of social learning, I think, is something that I'd love to see kind of integrated here.
That's a great point, and that's also one that I vibe with as someone who works with human language. I tend to feel like in a lot of discussions, both artificial and human learning, there's a real overemphasis on a single brain or a single computer, rather than thinking about the way that humans work collaboratively and gain so much from their interactions with other people.
And Bill, you mentioned you had some strong reactions to some of the neuroscience aspects of today. Do you have any takeaways you want to share?
Oh, I had a lot of reactions, Surya. Many times together, it was fun. It was a very provoking set of talks and thoughts. So many, but I guess just the one that I would call out is I was really interested in sort of both what was similar and what was contrasting between the talks of Dan Yamins and Chelsea Finn this morning. What was similar about them is that they're both interested in agents and agents interacting with an environment. But Dan is doing it virtually, simulating it in a computer. And Chelsea's actually doing it physically with robots, right? That actually move in the world and physically interact with things in the world. And I found my gut leaning more toward, that Chelsea's approach is probably going to, in the end, lead us to something more like animal intelligence than perhaps the digital simulations. And that's not to disrespect Dan's work at all. I admire his work tremendously. But there's something about interacting with the physical world, and I think that's what builds these physics engines, that Josh Tenenbaum was talking about at the end of the day. Chris, I even think it's relevant to the intuition point that you raised right at the end of the previous discussion, because if you really look at babies, a lot of interesting things were said about babies today. One of the most astounding things is their urge to move and their urge to interact with the environment. I mean, right from the get-go, right? First using that hand and then struggling to sit up and then wanting to stand up. And if you watch the baby, my mind goes back to J.J. Gibson. It's affordances. It is, when I touch that thing, what happens? Does it just stand there like a rock? Does it fall over? Which way does it fall over? And they're constantly experimenting with their bodies. And I think they're building premotor structures, Chris, in their brains, in motor, premotor cortex, that are being connected with sensation. So to say that AI maybe has solved perception, but now needs to work on intuition and whatever the other one was, I think that the connections between perception and action are far too deep to be segregated that nicely. So I think that was maybe the thing today that I had the strongest reaction to. And you can tell I'm a biologist because I want to see an organism in front of me, right? I want to see an actor. It's not just digital, zeros and ones out there in the world.
Yeah, I think that point of connecting perception and action is just a really important point that
yeah, I also agree.
I think we talk about at the start of the AI class, but very little of the work that's being done outside of certain areas of robotics like Chelsea's is actually doing it.
Yeah, no, I think it's super exciting. And also the way we design neuroscience experiments should deeply intertwine those. They shouldn't be separate fields in neuroscience. But anyways, it looks like this is all the time we have for today. I'd really like to thank you, Bill and Mike, for joining us here and for helping HAI as a co-sponsor of this important event. I'd also like to thank all our speakers for today for fantastic talks. To everybody out there in the world, we're going to make this entire broadcast available as a recording, which will be live following this event on our website, on our YouTube channel. Videos of each individual session will be available within the week. If you're on our HAI mailing list, or if you register for this event in advance, you'll receive a link as soon as that's available, as well as a survey. We'd love to hear from you about your thoughts about this event, about this field in general. Thank you for making the time to hear about this important research. Bill Newsom alluded to the fact that I was a string theorist before, so I used to study the physical world, but I shifted to this field. And I think this intertwined quest for both understanding biological intelligence and creating artificial intelligence may actually be one of the most exciting intellectual adventures of this century. Whereas, you know, physics was an extremely exciting intellectual adventure where we made a lot of progress. I think this is to me right now even more exciting. So have a great rest of the day, everyone, and thank you everybody for joining us.
Okay.